It is time to get started, everyone. Can you hear me? Welcome, welcome. I'm Steve Zdanswick, this year's POPL General Chair. Is the audio okay? Is the audio okay? They had it. Great. Welcome, everyone, to POPL 2025, and welcome to Denver. This is going to be and has been an amazing week. We have had, if you're just joining us today, you're joining us in the middle of a very full week of events. If you've been here for the first half of the week, you know that we've had a lot going on. This is the bird's eye view of the conference. We have 3 co-located symposium and conferences. We had 9 workshops, 5 tutorials, many student events, many social events. The ones highlighted in yellow are still to come, so please do join and experience all of that. These were the planned events of the week. We also had a couple of unplanned events, including a polar vortex that made much of the weather across the country significantly colder than we expected. So thank you for bearing with that. You'll also notice that we had some construction going on in the building because yesterday morning at 1:20 a.m., there was an accidental triggering of the sprinkler system on the 4th floor of this conference building, which did its job and flooded the 4th floor, but also consequently the 3rd floor of the event space. And so we had to adapt. So thankfully, everyone, the hotel, the police, were able to work together to juggle the rooms, figure out how to reroute people through the other parts of the building, and we were able to hold all of yesterday's events more or less on time. And so I have immense thanks to offer for the entire organization team, the hotel staff. Let's give them a round of applause now. And as you can see, the hotel cleanup crew has been working around the clock to try to keep things dry and safe for us. So we'll just have to bear with the situation. Speaking of thanks, I have many people to thank for this event. Rather than spend the next 10 minutes naming them all individually, I'm going to highlight a few. So particularly the staff helping to organize. You see them at the registration desk. The Curtis Hotel folks have been immense pleasure to work with and very accommodating. The many organizers working tirelessly behind the scenes to make sure that everything runs smoothly. We have all of these faces. You will see many of them here at the conference. Please thank them. I especially want to thank the AV team, who has done an amazing job, especially having to reroute all of their setup yesterday at a moment's notice. Basically, they worked through the night yesterday to make sure that everything could go on as planned. And of course, the immense team of student volunteers who also worked tirelessly throughout the day. You'll see them around in the conference t-shirts. This group has been absolutely amazing, so thank you all. I also want to give a special shout out to the local people from UC Boulder who were very helpful in accommodating equipment. They provided storage and transport and have helped to make things run smoothly. And of course, the technical, the program committee, Armando, our amazing chair, the associate chairs, and the many people who helped make the technical program you're about to participate in. We have many sponsors. Some of the events are sponsored by these folks, and they also help keep the registration costs down. So let's give all of these people a round of applause. I have a few more logistic sort of announcements. So first of all, just a reminder that we do have a code of conduct here for the events. And basically, we don't tolerate unwelcome behavior. You can read the full SIG plan code of conduct at that URL. And I would just ask that if you have any concerns or want to raise any issues, you're welcome to come talk to me about that. And there's another option, which is SIGPlan Cares. We have 2 members of SIGPlan Cares here, Alexandra and Stephanie. You're welcome to come to them if you have any questions, concerns, or want some advice. Finally, a few more logistics. There are going to be 2 tracks at POPL. One of them will be here in this room. The other is downstairs, more or less directly below. The flow is a little more complicated than we anticipated because of the construction. There's a set of stairs kind of hiding behind the stage that will take you straight down to the 2nd floor, or you can take the elevators where you came in. Today, lunches will be here on the 3rd floor. The general lunch will be over in the in the Foursquare ballroom, which is just back there. And the mentoring lunch today will be in Hopscotch. We'll have signs for that. We're going to figure out the lunches for the next few days and announce them as they need it. Finally, a couple of events to note tonight. 6 o'clock, we'll be having a reception also in Foursquare, and that will be going on in parallel with the SRC poster session, which will be out in sort of the hall space, so please join for that. And if you're joining for the women's dinner, that's tonight at 7:30, which will depart around 7:20. Let's see. Finally, there's one more set of people to thank, which is, of course, all of you for submitting your papers, making this a vibrant place to have discussions and conduct research. And so please enjoy the amazing technical content, have some great discussions with your colleagues, and let's hope this is a very memorable experience. So, welcome. And now I'm going to turn it over to Armando to introduce our keynote.
Thank you. Welcome, everyone, and welcome to our first keynote. So our first speaker today is going to be Loris D'Antoni. He is the Jacobs Faculty Scholar and Associate Professor in the Department of Computer Science and Engineering of the University of California at San Diego. And his research focuses on helping people write code that they can trust. And he has won lots of awards. He has won an NSF Career Award, Microsoft Research Faculty Fellowship, Google and Facebook Faculty Awards, and the Philip R. Creighton and Gary D. Sandford Letters and Sciences Distinguished Faculty Award, and the Maurice and Dorothy Rubinoff Dissertation Award. But we all know him mostly for his great contributions to our field. And so please help me welcome Loris.
Let's start again. Can people hear me? Yeah. Okay. Hi, everyone. So yeah, today I'll talk to you about some of the work I've been doing in the last few years. And the premise of why I started working on what I work on is that there is a lot of people who want to write code. And the good news is that you are in this room probably because you want to help them. We have now 30 million people paid to write code. And we have actually a lot more that they want to learn how to write code. This is like all data about enrollment in CS classes here in the US, but basically lots and lots of people want to take CS classes. What's more interesting that lots of people that are not in CS want to take programming classes and they want to learn how to write code. And so there are all these people that want to write code. Can we help them? Well, if you're here, probably the answer is you think is yes. And what can we do about it? Well, we can do a lot of things, but what I've been doing for the last several years is working on this field called program synthesis. And if you don't know what program synthesis is, basically the high-level idea is that people have some intent in mind. They have something that they want to realize. And in this case, for example, they want a program that sorts an array and does not violate array bounds. And synthesis will magically take this intent in some formal form and give you back a program that does the thing. Let's say bubble sort. And after many years, you might have a question you're wondering about, which is, does synthesis work? So I have very good news for you. We have synthesized bubble sort many times. In fact, you can read so many papers that have synthesized bubble sort. So it works. But besides bubble sort, kind of like the new wave of synthesis started around 10 years ago, 12 now, well, I guess 14 if you count the paper, when Sumit Gulwani wrote this paper on using program synthesis to help people fill in spreadsheets. So the idea here is that people gave example of what they wanted to do in a spreadsheet, and this tool automatically came up with a program that matched examples and filled it for you. And this paper was particularly relevant because it kind of started a paradigm shift in how we thought about synthesis. We were like, oh, maybe we don't have to solve these very hard problems like explaining what bubble sort is and whatnot. Maybe we just need to come up with synthesizers that can solve everyday tasks or more simple programming tasks. And this led then to many, many papers. I'm just picking a couple of recent ones that I really like on, for example, synthesizing robotic controllers or synthesizing 3D CAD models. So these are really cool works. And my group also did a lot of work on using program synthesis for various tasks. So this is, we did a lot of work on synthesizing, for example, network configurations. So it turns out that people sometimes get these configurations wrong. And when they do, the internet goes down and we don't like it. So can we somehow give these developers some tools to specify what this configuration should do and then just magically synthesize them? And my student Kaushik, the one that together with me and Aditya Kella did all this work, he's now at Google, and he says that he's kind of using some of the things he worked on. So this had some kind of impact. And we also work on some more like unusual applications of synthesis. For example, we started looking at many things as programs. And in particular, you might have heard that programs in the form of models, machine learning models, are used to make important decisions about people's lives. And so these models can have biases in them. So for example, they can prefer one group over another in a way that is not fair. And so we did some work where the intent was the model should not be biased, and maybe we get an initial model that is biased as input, and we come up with a new model that is not biased and has similar accuracy. And even these had some kind of technology transfer, because I ended up working with this data science company at T451, where they were very interested in using these technologies in their products. But that's not what I want to talk about today. So synthesis does work. We've seen many examples that basically have shown us that they can do interesting things. They can synthesize interesting programs. We can synthesize interesting programs. And one interesting thing is also that for most of the examples I showed you, we are still safe from LLMs for a few years, because those are things where I probably wouldn't use LLMs. And so will synthesis be made obsolete by LLMs? So it seems like for those cases, probably not. And I think the answer is no. In fact, it's a great time to work on program synthesis. So Francois Cholet, I think, timed it with my keynote 6 days ago, said, I'm starting a company. So I don't know if you know who Francois Cholet is, but he's the biggest machine learning library out there. And he did a bunch of other things. And he just started a company called India, where I'm not giving an advertisement, but basically their focus is deep learning guided program synthesis. And he says the path to AGI, which is not clear exactly what it is, but is what these people call artificial general intelligence, is not through incremental improvements in existing methods, which is what data-driven methods are doing, but it's something that requires a new paradigm. And the good news is that we know what that paradigm is. It's program synthesis. And so they're hiring people working on program synthesis to shape the future of how we use things like LLMs to generate code. So synthesis is not dead. If anything, is kind of a great time to work on synthesis. And so you might wonder, now that I gave you all this spiel about synthesis sort of working, how does it work? What is the big idea here? So this is this very nice characterization that Sumit Gulwani gave in 2010, where basically you can think of synthesis as having 3 dimensions. In program synthesis, we have the behavioral constraints, which are basically the input that the person gives us, telling us what they want the program to do. Okay, so these can be examples of input-output specifications. They can be assertions, they can be types, and the community has kind of explored many of these possible behavioral constraints. So this is how we express our intent. And then we provide the search space. And this is actually a crucial part of program synthesis. So at the high level, the search space is what programs are you interested in? So this could be network configurations, Excel macros, Python programs. But it's actually a little bit more than that. A lot of the success in program synthesis has revolved around designing search spaces for which synthesis is easier. So that's kind of one of the tricks that you'll learn along the way. And the final thing, which is the most important part, is how do you search for the program? So what is the search strategy that will get you to find a program in the search space that satisfies your behavioral constraints? Okay? So fundamentally, synthesis is search. And there have been many approaches to do this search. Like you can read all your favorite Sigman papers from the last 10 years, and there is going to be a lot of approaches. And really the challenge that all these approaches solve is figuring out how to guide the search towards the program we want, okay? So we want to find the program in the search space that satisfies the constraint, and we have to figure out how to get there. And just to show pictorially why this is a hard problem, typically you have a very large search space that has a few programs that work, maybe more than a few, but you're starting from a little corner there, well, from a side, and if you do the naive thing of just exploring the search space systematically, you don't get very far because there are too many programs, okay? And so what synthesis boils down to is avoiding bad programs, okay? So there is going to be a lot of programs that you can easily prove that they're bad, and you just don't want to send your search space there. And the more of these bad programs you can find, and the more of them you can avoid systematically, the farther you will get in your search and hopefully get to the program that does the thing, okay? So synthesis, as the title of the talk says, is about finding good programs by avoiding bad ones, okay? And the hard part of synthesis is avoiding bad programs. So this is the part that a lot of people spend effort in coming up with techniques that will help us with. Okay, and how do people do it? So historically, the way this has worked is that you take a synthesis domain, like whether it's network configurations or whatnot, and you design a pruning strategy. And people have come up with many pruning strategies, but basically these are techniques to avoid these bad programs. And people have worked with type systems, abstract interpretation, constraint-based approaches, but these are all techniques to basically figure out which part of the search space you should not explore. And a few years ago, I got really annoyed about the domain specificity of a lot of these approaches. So I got really fed up that basically every domain required reinventing some synthesis technique. So the state of affairs was that like, you want to build a synthesizer for some domain, you study the domain, you build the synthesizer, you come up with some clever pruning strategies, you ship it, and now somebody comes and they have to start from scratch. And so I started asking, is there a fundamental question here we can study and solve that will get us out of this sort of domain specificity? And so I basically asked this question. What does it mean to prove that a set of programs is bad? What makes a set of programs bad? How do we define what is the set of bad programs so that we can avoid them? And if we go back to our picture of what synthesis is, basically, synthesis takes behavioral constraints, takes a set of programs, and typically will give you a program. But you can also think that in some cases, if your set of programs is all bad, this picture should include a new element, which is basically the ability to prove that all those programs do not satisfy the behavioral constraint. So the key idea of pruning is basically that you want to show that the set of programs is all incorrect, does not do what you want. And this goes by the word of unrealizability, because basically it means that if you're in that smaller search space, you cannot realize a solution. You cannot build a solution. So we want to prove unrealizability. And so today's talk, I'm going to basically take you on a little bit of a journey on the work I've been doing with my group on figuring out what's unrealizability. And we started with kind of like some ad hoc techniques that worked on very small domains, and then we lifted them to more complex domains until eventually we finally understood the problem and we were able to define a sound and relatively complete program logic for unrealizability. And I will also tell you how unrealizability is the key to getting PL to help with LLMs. OK, let's start our journey. So this is an important subtitle here. So I'm going to talk about our work on understanding unrealizability. And specifically, there is these subtitles, which is, or alternatively, our work on verifying infinitely many programs at once. Because basically, what we're trying to do is to prove that all those programs satisfy some property. In this case, they're all wrong. So let me just fully connect the dots here on why unrealizability is sort of the key to understand, to make synthesis work. And so the idea here is that when you do program search in synthesis, you encounter pieces of programs that look like the one on the left. So basically, you're building pieces of programs, and you haven't finished the red part, so that part you're still working on it, and you have a behavioral constraint you're trying to satisfy. And basically, unrealizability tells you, hey, if any program you can build in that red zone will not get you something that satisfies the behavioral constraint, you can throw away all the programs that have that structure. Okay, you can just throw them all away. And so that's pruning. And interestingly, we came across unrealizability from a different angle. The reason we started working on it was that we were trying to help people synthesize best programs. And in particular, imagine this setting where you have a search space of programs and the specification, and you found the program, the one with the star, that you claim is the best one. According to some metric, it's the best program in the search space. So what you can do is that you can define a new search space of programs that are better than that one. So you can define a new space that says it only accepts programs that are, by that metric, better than the one you already found. And that's what got us to work on unrealizability, because if this new problem you have defined is unrealizable, it means that that star was the best solution you could have found. So anyway, it seems like it's a powerful primitive we should understand, so let's understand it. So what is the problem definition? I have a behavioral constraint. So I have, in this case, some formula I want to satisfy. So this is kind of the hello world of program synthesis that you find in many papers. This is basically a weird logical way to define the max of two numbers. This is saying I want a program that takes as input x and y and returns always either x or y and always returns something that is greater or equal than both. And you're given then a search space, which for the sake of this talk would be a grammar, a regular tree grammar of terms. And you want to ask, you want to prove that for every program in the search space, so for every program derivable from the initial non-terminal, there exists an input that falsifies the specification. Okay? And here, you can convince yourself pretty quickly that no program in that grammar computes the max of two numbers. Okay? Okay, why is this hard? So there are two reasons why we had to spend a lot of time working on this. The reason number one is that the grammar will likely contain infinitely many programs. So you can't just take them all, verify them separately, and be done. Or prove separately that they're all wrong. So that's problem number one. Problem number two, which is the most interesting aspect here, and that's kind of what led us to many false starts and eventually to understanding the problem, is that for all these programs in the grammar, they might be wrong on different inputs. So not only there are infinitely many programs, they might all be wrong on infinitely different inputs. So basically, you can't just find the test case and say, oh, they're all wrong on this test case. You need to somehow build proofs that are parametric on why each program is wrong. So the example here is that you have three programs, x, y, and 1, and you have three examples, and each of them is correct on two of the examples, computes the max on two examples, and is wrong on the other one. And you can build cases that they degenerate to basically having a full diagonal there, so requiring infinitely many different counterexamples. OK, let's start. So how do we prove unrealizability? Our first idea was like, whenever you start with something, the first approach you should try is, can we reduce to something that we already know how to do? Okay? So this way, we don't have to implement anything complicated, and we can move fast. So for this particular technique I'm going to show you, you can assume that the specification is given to you just through some examples. In this case, there is these 4 examples. And you have a grammar of expressions. So expressions meaning programs without side effects. And what I'm going to do, I'm going to show you that you can build a program. And the program has some assertions. And the assertion will always hold if the problem is unrealizable. So basically, I'm reducing this to something we already know how to do, something that I can throw to an existing program verifier. What is the idea? The idea is pretty simple. So I'm going to write a program that takes as input my, let's say in this case, one example, the example 1, 0. So it's supposed to compute the max of 1 and 0. And so the trick here is that I'm going to use non-determinism to explore the space of all possible programs. So I have this non-deterministic function fstart that basically uses non-deterministic calls to choose which production of the grammar to trigger. And when it calls a production, it will execute that production on my inputs. So in this case, if it says, hey, I'm picking the first case, that should return 0, therefore return 0. The third one says, oh, you're picking the x production, therefore you should return the x part of the input. And if you pick the binary production, the one of plus, you non-deterministically produce its children by calling the function recursively, and then you return their sum. And what you're going to assert at the bottom is that you want to prove that all these programs are wrong, meaning they don't return the correct output. In this case, the correct output is 1. And you want to prove that all those, no matter which non-deterministic path you take, you are not going to return 1. OK? So this assertion is always true if the problem is unrealizable. And in fact, it's false only when you find the path that corresponds to a program that solves the problem. So it looks like we solved one of the challenges. We were able to essentially deal with the infinite set of examples by using non-determinism to explore all possible paths. But I haven't told you what to do if you have, in this case, I'm assuming that that particular input falsifies the specification for all programs. And that's, in general, I told you that's not the case. So we can try to do the naive thing here, which is I'm going to call my program on one input, and then I'm going to call it again on another input example. And this is not quite right, because I'm going to get that the two assertion 1 will fail if some program is right on the first example, and the other assertion will fail if some program is right on the second example. But what I want is that I want one assertion that fails when the programs are, the assertion will fail if some program is right on both the examples, okay? So I don't care about just being right on one. Basically, I want the assertion to be true if every program is wrong on at least one of the examples, not on both. And so the idea here is a pretty small modification, but basically you need to run your non-deterministically generated programs on all the examples at once. You need to make sure basically that you execute your inputs on the same program. And so the idea here is that instead of taking just one example, you will take both and just execute them in parallel. OK. And so this was our first solution and kind of got us to understand a couple of key principles. And in particular, it got us to understand this key principle that you needed to run the examples at once on each input. You cannot run them separately. And we were able to prove a few things automatically. So basically, we built a tool that encoded the problem as a reachability problem, called a reachability solver. And we were able to prove that you cannot compute the max without if then else's, or you cannot compute the XOR if you only have AND and OR, and a couple of other cute things. But then at this point, OK, we did the low-hanging fruit of trying a verifier. Can we come up with something that just solves the problem we are solving, which is unrealizability? Like, can we avoid using a closed box tool? And this led to the second work. And this brought us to a better understanding of what was going on. So let's say you have this very simple grammar. So here you have a grammar that generates basically x plus x plus x plus x a number of times plus 1. So if you look at it semantically, the programs in this grammar look like 1, 2x plus 1, 4x plus 1, and so on. And let's say I want to show that there is no program that has this behavior. Basically, I want to show that no program in this grammar on input 1 returns 5 and on input 2 returns 6. So one way I can think about it is that I can try to describe the input-output, the set of outputs that programs in this grammar can produce. So in this case, I can introduce this new relation E of 1, 2, a function really, E of 1, 2, that returns the set of all possible pairs of outputs I can produce. So in this case, it will be 1, 1, 3, 5, 5, 9. And then the idea is that if I can build a representation of that relation and show that the output 5, 6, the one I want, is not in there, then the problem is unrealizable. So if I can prove that none of the outputs is the right one, I'm done. And so what is the idea for proving this? Well, the idea was to build an invariant about this set. So in particular, an over-approximation of this set that we could prove was an over-approximation. So in this case, I'm going to show you kind of one way to do it. But the idea is that we can use an abstraction to say, well, it's hard to build exactly that set. But it's pretty easy to convince yourself that it always produces a pair of odd numbers. So I can use an abstract element there, odd, odd, to say that I can over-approximate this big set as just being pairs of odd numbers. It's not exact, but it's enough to prove that our output 5-6 is not a possible one. Because 5-6 is odd even, and is not an element of odd-odd. And how do you do that? Well, the good news of working with my colleague Tom Reps is that he knows all the papers from when I was 5 years old. And so he told me, I think this feels like grammar flow analysis. And so we started looking at this technique called grammar flow analysis, which is basically data flow analysis, but over grammars. And the idea here is that you can write a set of equations over your abstract domain that basically mimics what the grammar will do. So in this case, it says that the set of elements I can produce from 1, 2 is the abstract interpretation of x, which in this case is 1, 2, is my two inputs. Again, plus 1, 2, plus what I'm trying to solve for, join the abstract interpretation of 1, which is that 1. And some of them are constants, so we can solve for them. We can turn them into odd, even, odd, odd. And now all we have to do is to solve for the unknown. And any solution for the unknown, which is this E#, 1, 2, it's an invariant about this search space. So once we can solve that, in this case, odd is a solution. And once you plug it in, it's trivial to see it's a solution because everything cancels out. You're done. And then the last thing is to just show that it doesn't contain your output. And so this was cool. And so we built a tool based on this that was faster than the original one. But what was really cool is that actually with this technique, we could actually describe the problem exactly. And we were able to prove that some fragments of unrealizability are actually decidable. In particular, for linear integer arithmetic. And if you only have expressions, you can show that you can come up with an algorithm for solving this. So this was great. But basically, we were only working still with expressions. OK, so expressions are great. But sometimes you also want to write actual code. You want to write programs. And so here comes this student, Jin-Woo Kim, who joined my lab as a PhD student. And he came to me when he started. This was like on day one. I was like, I want to design an approach for proving unrealizability that can be applied to every synthesis problem. And by now, we've been working for 2 years on figuring out expressions. So I told him, OK, that sounds cool, but it's probably very hard. To which he rightfully replied, I don't care. So OK, let's work on this problem. So we spent a few months, a few dead hands on crazy, not crazy, but like, let's say, abstract domains that caused me a few more white hair than I was hoping at the time. And eventually, we started understanding the problem better and better. And actually, Jin-Woo came up with this idea, which was quite clever. Basically, let's try to understand what we are doing. So expressions are nice. What is nice about expression is that the value of x never changes. So when you write these equations, you can assume that basically the interpretation of x is always 1, 2. You don't need any context. And when you work with, let's say, imperative programs or your favorite stateful programs or effectful programs, this is not true. And in particular, let's say you want to try to show that, so that grammar describes programs that will compute basically powers of 2. Assuming you get as input 1, this produces 1, 2, 4, because every time you double. And so if you try to use grammar flow analysis, the technique I just showed you, to describe the set of possible outputs, you will get stuck. Because you're going to say, what are the outputs that I can produce on x equal 1? Well, I can do 1 plus 1, but now x has changed. So I need to know the value on x equal 2. Because basically, there has been an update, x equals x plus x. So now I need to solve for x equal 2. OK, so let's solve for 2. But now you need to solve for 4. And you get where this is going. So this doesn't work. You cannot describe what imperative programs do in this way. And so the solution was that, of course, I mean, in hindsight, it's pretty obvious, is that you need to talk not just about the outputs and the inputs separately, but you need to capture their relation. So you need to capture which output correspond to which input. And so the idea here is that you want to, instead of having this unary relation S of the input, you want to have a binary relation that tells you sum of I/O holds if there exists a program in S that when run on I produces O. And how do you define this relation? And this was kind of the key clever part that Jin-Woo figured out. Is like, well, you can describe it using semantics. But how do you do that in a way that makes logical sense. And well, the idea was to use constraint or clauses. And so this is a formal way that you can automate to describe the semantics of a programming language. And so here, this rule will say, oh, if you're trying to describe the x plus x example, you will say, well, C1 can produce, on C1 I can produce C3 if C2 is equal to C1 plus C1, and running some program in S on C2 produces C3. So this is just like the operational semantics definition of this, okay? All right, so we can define it. And then we stumble upon another problem. And this is kind of like, sort of like when you learn programming languages, this is how programming languages is taught. Like, oh, there is expressions and life is easy. But now you have effects and life is hard. And now you have loops and you cry. And so that's essentially the story of this research project. And then we were like, OK, you just have to capture these relations. And we came up with this way to capture these input-output relations. And then loops came. And you're like, OK, what is the relation that describes repeating A twice? So in this grammar, repeating A twice, it means that either you repeat x plus equal 2 twice, or you repeat x plus equal 3 twice, right? This is a set of programs we are describing. But if you do the naive thing of composing this relation with itself, you don't get that. You get the intended behaviors, but you also get, basically, you capture executions that change the loop body across iterations. And that's, if you remember, that's how we started. We were like, oh, non-determinism is the key. And now here we were like, well, if you do things non-deterministically, you're going to lose precision, because you're going to basically allow programs that you're going to include in your search space programs that don't exist, programs that can change throughout the execution. And so, well, again, the solution here was to look at how do you define the semantics of loops. Well, you can't ignore the program itself. You can't just define it without considering that different loop bodies will lead to different iterations. And so the solution here was that on top of capturing input-output relations, we also need to remember which program is responsible for those input-output relations. And so if you do that, you get basically the typical operational semantics you will teach in one of your classes. And essentially, you just write, if the Boolean guard evaluates to true, then run the loop one more time and repeat. And again, you can write this using a constraint horn clause, which means you can throw it as some kind of solver. OK? So this actually led Jimbo to defining this new framework for defining synthesis problems, where the idea was that like you get a grammar like we've been used to throughout this talk, but you're also responsible for providing me a semantics of programs in this grammar defined using constraint or clauses, and then you give me specifications. And our synthesis or unrealizability here boils down to showing that, let's say unrealizability, that none of the programs in the grammar, all the programs in the grammar, when executed according to their semantics, are wrong on the examples. And the beauty of all of this was that once we did everything with constraint or clauses, building the solver was one line of code. It was adding a query to our constraint or clauses that says, if you can find something that on 6-9 produces 15 whatever, you have solved the synthesis problem. So basically, synthesis so constraint or clauses, you should think of them as a proof system. And certain things can be proven, which in this case is like actual semantics of programs are provable in your system. And solving this query boils down to, if you can derive realizable in this system, it means you have solved the problem. And this actually led to more than this paper. It turns out that this framework was the lens we needed to study synthesis in purely abstract terms. Because up to now, we kept kind of building tools for various applications. So this particular way of looking at synthesis led to this framework called Sengus that then led to many works on kind of really study synthesis from a purely generic way. Like basically, how do you solve synthesis if you know nothing about the language you're synthesizing for other than its semantics written in logic? And so we wrote a lot of interesting things that you're welcome to read, but that's not what I'm talking about today. I'm talking about unrealizability. So with this new technique of constraint or clauses, we were able to prove new things, unrealizable. So for example, that you cannot swap two numbers unless you have auxiliary variables. Well, you also have to remove some other operators. But we were able to prove some things about imperative programs that before we couldn't do. OK. But then we were back to basically relying on closed box solvers. So we started with, oh, we can just call a program verifier and get unrealizability. And then we didn't like that. And now I'm just calling a different type of solver and getting proofs. But I don't like it, because what we really want is actual proofs. We want to be able to figure out a way to build proofs of unrealizability. And so this was, again, Jimbo went on an exploration mode and started trying to basically, he took the results that we were getting from the constraint or clause solver, in this case, a spacer, the Z3 one, and tried to parse the proofs the solver was building to figure out how they corresponded to what we were asking. And he somehow decoded in one case that the solver had proven that this particular problem was unrealizable as follows. So you don't need to understand this problem. It's kind of saying you cannot compute the XOR of two variables in this grammar, because you only have AND and OR. But the solver came back and says, no matter what term you give me, and no matter what term you give me, when you run this term on these two inputs, you cannot set the third bit to 1. And in this particular example, the third bit was, no, you set the third bit to 1, but we needed it to be 0. And so we're like, so how did he build the proof? So the way he built the proof, it was by building an invariant about all the programs in the search space. So this invariant is not quantified just over the input-output. It's quantified over T. T is all the programs derivable from S. And that was the eureka moment. At the point we realized, this is what unrealizability is. We need to build invariants about sets of programs. Not invariants about one program or about program execution, but these invariants that are true for sets of programs. So the induction principle for unrealizability is by doing induction over sets of programs. And that was the thing that kind of made us realize that we were doing something wrong, but then led us to finally really understanding the problem and to kind of the grand finale of unrealizability, which was like we came up with a program logic for expressing these proofs. So in the same way Hoare logic gives you proofs that you can inspect visually and mechanically that a program does something, this new logic we came up with called unrealizability logic allows you to inspect proofs of unrealizability. And actually, it's a bad name. You can use it for things other than unrealizability, but we cannot rename it. You can ask for an errata about a POPL paper, but not for the title. So, so anyway, basically, the logic has this slightly funkier parenthesis, and it says, this triple is true for that set of programs if the corresponding Hoare triple is true for every program, essentially. OK, so I gave you the definition. You can probably see you can use this logic to prove unrealizability, because you can just say, no matter what the input is, the output is not the one I want. You can write a triple like that. But how do we write proofs? And so the idea, as I said, was to have invariants about sets of programs. So in the logic, you can have these triples on non-terminals in the grammar. So basically, you can say, for anything derivable in this grammar E, if X and, let's say in this case, an invariant is that if X and Y are both even or both odd, the output is the same. So if X and Y are even, the output is also even. If X and Y are odd, the output is always also odd. And this was kind of the invariant to prove the XOR case. But basically, you cannot flip the sign of the output. So, but the logic needs to let you use these invariants. And so how do you prove that this is an invariant about that set of programs? Well, you do it by induction, right? You start with the base case. It's true for X and Y, right? I mean, basically, if you output X, the output is X. And therefore, the parity is the same. If you output Y, the same. And for the other cases, you proceed by induction. So assuming that this invariant is true for the two E's, for the two expressions, can I prove that it's true for the composed expression? So assuming it's true for E, can I prove that it's true for E and E? And you can convince yourself that that's true, but you don't need to convince yourself, because we have a logic that shows you how to do it. Basically, in our logic, you can build these derivation trees where you introduce invariants into this context, and then you can apply them as induction hypotheses when you get to the leaves of the tree, and you can use them to basically build your proofs. So here, really, the key intuition here was that you can load this induction hypothesis about the search space, and when you get to need in the induction, you can apply it. In this case, when you get to E and E, now you assuming it's true for E, you can apply to prove E and E. And once we had this type of treatment, we could finally build solvers that kind of acted like normal program verifiers, where essentially you can create verification conditions and frame the problem of synthesizing these invariants as a synthesis problem, and then you can generate proofs of unrealizability. So of course, proving unrealizability boils down to synthesizing something. So it's synthesis all the way down. And then actually, Shan and Jinwoo, the two students working on this, once you have a logic, you can start asking even more interesting questions, which is what makes the logic sound and relatively complete. And in particular, we have this upcoming paper where you actually need to change the semantics of your programs. You need to change the semantics of programs and the corresponding triple if you want to get a relatively complete logic. Like traditional program semantics doesn't work, because if you remember, you need to capture how different programs produce input-output relations. So there is an upcoming work, but basically the more information you track, the more you can prove, until you actually don't need the syntax of programs, you just need the semantic relations. But yeah, it gets pretty complicated. But I don't want to talk about this. So what are the challenges in automating these logics? That's kind of where we are at now. It turns out that I kind of made it look like Hoare logic, but I hid a lot of details. And in particular, some proofs here require abstract domains that we don't have yet. In particular, domains for reasoning about sets of programs, so domains over abstract data types, over terms. And we need good solver for infinite arrays. I didn't show you here, but in this logic, you can build proofs that require reasoning about how each program treats infinitely many possible inputs. And the way you do that, one way to do that is with infinite arrays. And we haven't figured out how to go beyond traditional imperative programs, like, non-procedural programs. So some of you might have noticed that the trick I did with invariants is quite similar to how you do Hoare logic for recursive programs. But now I already used that trick. So now if I also have to do recursion, you have to do two things, and we are not quite sure what that is. OK, so I started with this. Millions of people want to write code that meets their intent. Can we help them? And I gave you a very interesting talk, in my opinion, about verifying sets of programs. But I haven't really quite delivered on this, right? I haven't helped millions of people. In fact, I probably helped mostly tens at tops with this particular talk. We don't work that has helped some people. But OK, so basically, where synthesis sits, regardless of what I just talked to you about, is up there. So we have beautiful correctness guarantees. And these are, I would say, you can put your favorite PL technique actually up there. Like beautiful correctness guarantees. How often does it produce a program or a result at all? Not so much, OK? So always correct when it terminates. Terminates, not so often. And now we are in a beautiful world where, so this is helping hundreds and maybe thousands. Like it's helping a lot of people program synthesis. And we can make it better. So people have been working a lot on kind of improving search, and so that we can make this technology more available. And I would say some things out there are helping many, many people, OK? Some techniques, they work really well. And then we have the elephant in the room, LLMs. They're helping millions with the quotes. I think actually without the quotes. They're helping millions. It's just like not the way we like, but that's OK. Like, you know, they're wrong, not us. Yeah. No. So, OK, but they're helping millions of people, and but no correctness guarantees. And so what I'm going to show you is that a little bit of PL goes a long way, and we can really push this thing up a little bit towards correctness if we put ourselves to it. And we can start forcing some guarantees. OK? So what is the key idea? So what are LLMs? If you don't know what LLMs are, don't worry. After this slide, you will know most of what you need to know about them. So if you open this website called chatgpt.com, you can generate the slides for this talk, for example. But you can also ask questions like, give me a binary string of length 5 that ends with 1. OK, you can ask this. You might say, I know how to do this. I don't need ChatGPT, but you can still ask. And an LLM will start from the beginning and says, OK, based on this question, I have possible characters I can choose from. They call them tokens. They're actually slightly different than what we call characters. And it will say, oh, these questions should be answered by picking either a 0 or a 1 with approximately equal probability. You can also pick something else. Because sometimes when you ask ChatGPT, instead of telling you 0, 0, 0, 0, we'll tell you, of course I can help you producing a number, and we'll tell you all these things. So you ask, OK, I want that. So it says, OK, let's pick 1. And then it says, oh, now I can choose 0 or 1. And each of these things will have a probability, and it keeps going. And in this case, you will get, let's say, 1, 1, 1, 1, 1 with probability, some probability. There are a lot of strings of length 5 that end with 1. So you might also actually get a wrong one with typically with a lower probability. So these models kind of understand something. So they will still, everything is producible in these models, just with very low probability. So 0, 0, 0, 0 is not one we like, but it's possible to produce it. And in fact, as I said, you might also get something that is not a binary string at all, like it starts with other things. And that will have some probability. So our goal is, how do we get the LLMs to produce something that satisfies some constraints? Okay? So they're producing all these random things we don't like. We want only to produce things we like. So you can do one thing. And this is, this is basically one of the key ideas out there. Is just generate a lot of stuff and hope that one of them is right, and keep the ones that are right. So basically, generate and check. And so this actually, it sounds naive, but that's how a lot of normal synthesis works. We just generate a lot of programs and keep the ones that work. We try to stir the search, but at the end of the day, most of what we generate along the way is wrong. There is one problem with doing that with LLMs, is that whenever you generate a program, it affects your bank account. Okay? So every program you generate costs money. If you use a fancy model, it's like cents to generate actually a larger program. And it can be very slow. Like we're used to enumerating in synthesis hundreds of thousands of programs per second. And now, like if you use not the best hardware in the world, you might get like a program a second sometimes. OK, so that's not a super good idea, especially if you most often get things that don't satisfy the constraint. So what should we do? We should avoid bad programs, right? That's what this talk is about. So if we can avoid those programs in the black regions, or dark gray regions, we can spend our money that we saved to generate more programs and hopefully get the ones that we like. So as much of the kind of as many of the naive mistakes we can avoid, the more likely we are to get to something that satisfies our constraints. And so if you remember, unrealizability was the essence of pruning. Well, surprise, surprise, unrealizability is the essence of pruning in LLMs as well. So let's say here you have that constraint you want to force, that you want a binary string of length 5 that ends with 1. Well, let's start with just enforcing that at least it gives us a binary string of length 5. So we can basically take some parts of this exploration tree and just cut them off. Just say, OK, all these things that you're trying to do, those will not lead to valid solutions. So you should just not go there ever. OK? And so if you can somehow detect these early on, you can just prune those away and just focus on the good generations. And this is not that hard, because in LLMs, you kind of get this one token at a time. If you know that the token is not going to get you to the right answer, just throw it away. Okay? And let me show you why this is unrealizability in a way. So let's say we're doing it for programs. So this is a toy example, and nobody probably should build this because it's a bit of an overkill. But let's say you've asked, give me a Python function f that always returns its input. So you're asking for the identity function. So the constraint is that this should return the identity function. And you can start, ChatGPT will tell you, of course, starts with this, the def function. And then let's say it gives you, among the tokens it proposes x equal 1. We know that this is a bad idea. This is deleting x. You cannot return x anymore if you've deleted it. Okay? And so unrealizability will tell you, yeah, if you go this way, you're out. None of the programs that continue from here will work. And so if you can build an unrealizability checker for this type of checks, you can throw away this possible token. Okay? So that's kind of the key idea. Is like we can avoid taking paths that will not lead to success early on. and it will save you money and time. So are we doing that? So we need to start with baby steps. So the baby steps here is, let's start. So if you take a compilers class, you're going to learn that there is the syntax, and there is the semantic analysis, then there is a lot of stuff along the way. So we are starting from the beginning here. We are starting with, can we at least get something that parses? Okay? And this is actually, LLMs are pretty good at this for the languages they've seen a lot of, but not for more niche stuff. So in this example here, this is a Cygos problem, is a synthesis format, where you provide the grammar as input, and you say, I only want solutions in this grammar, because, I don't know, my device I'm going to run it on only supports this grammar. And the LLM gave you something that is not in the grammar here. So can we force at least the output to be in a grammar? And the answer is yes, and there are lots of implementations that you can find out there. Most of them, turns out, they don't work, but because it's a very hard problem, actually. And so I think this is a very exciting opportunity for us. It's like how to get implementations that they work right and they're efficient. And so the idea here is that you provide the grammar as input, like let's say a subset of the Python grammar, and you say, I only want programs that are in this grammar. And you can use ideas for parsing to basically force this. You will force the output to be in the grammar. Okay, you just generate the usual parser table, and you follow it to make sure you never exit. Can anything go wrong? And I'm going to show you some of our work that shows that if we do this naively, there are some issues. So let's go back to our question. Give me a binary string of length 3 this time. Let's say the LLM is perfect. It has figured out the perfect distribution here. It will give us every binary string of length 3 with probability equal. Okay, with probability 1/8, it will give us all of those. And what can happen is that maybe because of some other constraints, we're going to add an extra constraint that throws away some parts of the space. So what can happen when you do that with the techniques I just described, this idea that whenever you find a bad path, you avoid it, is that you will see here, it's kind of subtle, but you will see that, this is kind of important, these probabilities have changed now. Because now there isn't 2 choices here anymore. There is only 1. So you're going to take 0 with probability 1. And so if you do that, what happened is that you made the LLM not smart anymore. Because now, it will produce that one string 100 half of the times. It's the only string on that side. But when taking this first decision, that 0 or 1 should be taken with probability 0.5, the LLM doesn't know that you have put some stopper here at the bottom. Okay? And so the way to recover from that in our work is that when you do your constraining, you should also learn how much probability you've taken away from the LLM by doing the constraint, and redistribute that probability up the tree. And so we built a decoding technique. You can go and find it that basically will fix this for you and give you the right probabilities. And this is a simple Cygos example, but basically the black line is the actual probability distribution you want to have, which is basically the conditional distribution of the LLM given the constraint. And our technique converges to that. It gives you the right samples versus naive constraint decoding doesn't recover. OK, so what's next? So I'm going to wrap up real quick. Basically, I've showed you, I got into this journey of studying what makes a set of programs bad. And we studied sort of a lot of that and came up with some techniques. And then I showed you the same key principle. Once you take this fundamental principle, it applies also to LLMs and new things that come along. It's kind of like teaching a new dog all the tricks here. I guess that's the analogy. But the point is that basically strong foundations transcend trends. If you study fundamental problem like parsers, they lead to this grammar constraint decoding. Unrealizability and static analysis are going to be the way to force LLM to basically follow rules. And again, it's time for a new paradigm. And the good news is that we know what it is. It's program synthesis. So I'm not the only one saying this. Also, I think this person has a few extra zeros than my bank account. So I think you should trust him. OK, so synthesis is search. And how do we guide it? And basically, it's about guiding search towards the program we want. So I asked ChatGPT to generate an aphorism about my talk. And he says, LLMs inspire the journey, but programming languages techniques secure the arrival. So So if you don't trust me and François Cholet, at least trust ChatGPT. Okay, and programming languages will play a strong role here. So grammars are sort of, as I say, is the baby step, is step 0. Now we need to go all the way to your favorite type system or your favorite static analysis and tell LLM they should only produce stuff that passes them. And this sampling issue I described very briefly, that we get to the wrong distribution, this is a PL problem. It's an algorithmic problem. To do this research, you don't need to understand anything about machine learning. Okay, a little bit. But most of it is just like, it's a new way of producing programs where programs come to you one piece at a time. And what is the best analysis you can do when a language is written that way? And we know a little bit how to do it from things like autocomplete, but now it really just comes from the left. Like, we don't have much context. So lots of applications, I think, in probabilistic programming, automata theory. And my colleague Nadia Polikarpova gave a keynote at PLDI, last PLDI. We also need to accept that people need to use this stuff. So this is an HCI plus PL problem. So we need to figure out, nobody's going to give us specifications written in logic in this new world. So we need to kind of trick them into do it. And so we are doing some work on kind of synthesizing the specifications for them and then giving them in a friendly way. And also, how do we communicate possible program choices? And the last thing, maybe there is a space for designing new programming languages for which this is easy. So maybe we can just change our languages so that we make them friendly for this type of analysis. So I'm going to thank a few people. So the first person I want to thank is, so Mariangela Dezzani, she was my undergraduate advisor, and she's the reason, basically, why I'm here today. She picked me up many years ago, and she introduced me to research. She was when I was invited by Armando to give the keynote, the first thing I did was emailing Mariangela to thank her. So yeah, you know, if for the faculty in the room, try to be the door to research to as many random first-gen students like me. And I want to thank Rajiv. So this is the story of how my PhD started. So Rajiv told me, I just got a lot of money to work on synthesis. And I was like, no, I don't want to work on synthesis. I want to work on automata. And then I graduated, and I started working on synthesis for 10 years. So sorry, Rajiv, but hopefully this makes it up. And then the people who actually do the work and the ones who paid for it, thank you. Okay, that's it.
Thank you. So we have maybe a little bit of time just for a couple of questions.
Thank you for the journey. This is Tom Ball from Microsoft Research. So it seemed to me if you took the specification for synthesizing a program, there exists a program, blah, 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 for that such for inputs, and you negated that, you would quickly find that you have to search over all infinite programs. It was a long way to get to that. You see what I mean? I mean, if you started with the spec, you would realize just another, right? I'm
gonna try to. I'm gonna try to understand. So the point is like, yeah, we're just negating the definition of synthesis. But the question, it wasn't like, yeah, of course you need to find infinitely many programs. The question is like, how do I build a machine checkable proof that all those programs have this bad property?
Okay.
So just the theoretical problem was clear from from Manna 1980.
Right.
But it's like the practical question was a little bit.
Got it. Okay. The other thing is Michal Moskal has been working on a framework, very efficient, state of the art for doing constraint decoding for grammars, and anything else you can write in WASM or Python. So there's a lot of work for efficiently doing constraint decoding for grammars that you can just build on today. Yeah. All open source.
Yeah. It was, I think. It's like
hi, so wonderful talk, really I learned a lot. One of the things that I think I learned at the beginning of the talk was that a solution to your synthesis problem was to take the set of all programs and encode it basically as a single program, and then you can apply conventional techniques because you just have a single program with non-determinism. But then at the end of the talk, you sort of discarded that idea and looked at a Hoare logic for sets of programs. And so I'm just kind of curious, and you probably explained this in the talk, but can you take that idea from the beginning of the talk and take that set of programs and transform it into a single program and then do conventional search for invariants over that single program? Or does that not work?
Yeah, that's a great question, and I get it a lot. And it's a valid way to do it. So you can encode everything as a single program, but this means that basically you're going to have a variable that it's an infinite array of choices that models which program you're going to pick. And now your invariants need to be over that really weird variable. So you need you're essentially encoding all of the non-deterministic choices into some integer or something, and now you need to build invariants about those, and we don't know of a logic that will give us nice invariants for that. So instead here the goal is like, how do I do things? I kind of didn't say this, but the goal is compositionality. I don't want my proof to be one massive first-order formula describing all the possible continuations of this number. I want a formula that gives me a proof that says all these programs are wrong because. So it's pushing as much as you can on the input-output relation rather than on the structure of the programs themselves.
Thanks.
Yeah. Next time you pick the seat, think first of the talk.
So I asked ChatGPT, write an OCaml program that concatenated two lists. I got it right.
Okay.
I asked to my class, half were n2 and n square instead of n. Then I asked GPT, give me a proof. It was correct, a bit long. I asked to my class, half of the proof were wrong.
Yeah.
So the trick is that ChatGPT incorporate the knowledge about program that you can find anywhere on ChatGPT, in books, and in your synthesis by grammars and so on, you have no way to incorporate this.
Correct. That's why I think we need to constrain it from the outside. So that's a great point. So the question is, these LLMs are very good.
No, it's not on LLM. I say LLM incorporate this, but in your method by grammar generation, you don't.
I do, because the point is that I want to basically follow I want to still use the wisdom of the LLM, but I just want to cut off things that I know for sure are wrong. And so the idea here is that, like, so in the specific, I think there is a point that there are things that LLMs are very good at, and there are the things that they've seen a lot of data for. And we also need to make them good at things that they haven't seen much of. And so this is one possible way to do it. And for your question is like, am I basically forcing the LLM to do things it's not good at? This last thing I described where we want to recover the right distribution, that's exactly what that is doing. I'm like, I want to force a constraint, but I don't want now the search to be biased towards my view of the problem. I still want the LLM to be good at things. I just want to remove the obviously wrong things.
Okay, thank you.
Yes. So I come from a slightly different community where we also do synthesis. That's reactive synthesis.
Mm-hmm.
So in reactive synthesis, when you have a spec and you throw your spec to a synthesizer, to a synthesis tool, you either get realizability and the controller for the system, or unrealizability and the controller for the environment, which are exactly the same animals. They live in the same world.
Yeah, if you pick a decidable logic, life is good. That's
But what I mean is that here, it's a little bit less satisfying that your programs and the programs for the environment, your proofs, live in a completely different world. So,
correct.
It's just an observation. But then that leads to the question, which is, why don't you limit your counterexamples or your environment in the same way by giving a grammar, and then you use similar techniques to search for counterexamples? You may lose determinacy of your game setting, meaning that you may not be able to prove that none of your programs work, but you may bootstrap a tool where you chop a lot of the search space.
So, I'm not 100% sure I grasp the question, but the idea is like, can you do something cheaper that is not building these complex proofs? And it's kind of like, that was synthesis when we started this work. It's just like, oh yeah, I mean, if you know that this side is obviously wrong, just cut it off. Like there were many heuristics that people have built to prune search spaces. So this is more like how to build a theoretical understanding of what that entails. Like what are you trying to actually prove with these pruning techniques? But the connection with unrealizability, yeah, is like unrealizability is usually played over a very friendly logic. And here, actually, you can show that these are in two different decidability words. Like proving unrealizability is computationally harder in the computability sense than proving than synthesizing.
So we're starting to eat a little bit into the coffee break. So I think we should thank the speaker again for a great talk. And if you have any further questions, you can always ask afterwards.
with 4 papers. Whoa, and I'm live. I don't need the mic, but they need it to record. Hi, I'm Tom Ball from Microsoft Research. I'll be your session chair. We have 4 papers on temporal properties and automata. And Arthur will take it away with his talk.
Thanks a lot. So hi, everybody. My name is Arthur, and today I'm going to be talking about, oh, the mic is not working? OK, great. Is it good now? OK, good. So yeah, I was saying today I'm going to be talking about co-inductive proofs for temporal hyperproperties, and this is joint work with Professor Bernd Finkbeiner. And before I present to you the contribution of this paper, I'd like to talk a little bit about the task of specifying programs. So if we want to specify programs, one way to go about it is to focus on what is it that the program should compute. Examples of such specifications are, for example, P should compute the factorial of its input, or P terminates. Now, this is not always enough. Sometimes we don't care about what the program computes. We don't even care whether it computes something meaningful at all, but we're more worried about how is it that the program is computing. Example of such specifications are, for instance, P is deterministic, or P does not leak private data. So if we want to specify what to compute, it generally suffices to consider each execution of my program individually. As an example, if we want to specify termination, it suffices to look at each execution of my program and state that each of them is finite. Now, if we want to specify how to compute, looking at executions individually is not enough. What we need is we need to compare multiple executions. We need something a little more general. And as an example, if you want to formally specify the notion of determinism, one way to do it is to say, give me 2 arbitrary executions of my program P that are sharing the same inputs, and you should prove that they also have the same outputs. This is a relational property. So hyperproperties are exactly the framework that allow us to do that. And they have many applications, in particular to security. OK. So in the context of this talk, I'm not only going to talk about hyperproperties, but I'm more specifically going to talk about hyperproperties of reactive systems, which are programs with the following features. So I would like input and output. I want non-termination, so I'd like to talk about programs that run forever. And I would like to have non-determinism. So those are very interesting features, in particular if you want to model applications like UIs, web servers, operating systems, which are all applications for which security requirements are very important, in particular security requirements that can only be expressed as hyperproperties. OK, so one little remark about such systems is that in this context, executions are infinite sequence of input-output events. So we'll need specific machinery to specify relations between infinite sequence of events. And usually such specifications require the ability to be to universally and existentially quantify on traces. So this is going to be a critical feature. OK, so let's look at the little example. We have a small program that runs forever, fetches user input, and adds some non-deterministically determined value to it, and then output the result of the sum. And I claim that this program doesn't reveal the exact value of the input through its outputs. And the way we would formally specify that is we start by fixing some dummy value lambda. And what we're going to say is, for all trace of this program, there should exist a trace where we have fixed the inputs to be the predefined constant lambda, and yet the outputs are indistinguishable in between the 2 executions. So if we think a little bit about it, what this specification means is that the effect of the input of an arbitrary input is indistinguishable from the effect of the specific input lambda, and therefore, from the point of view of an observer of the system, we can't really infer anything meaningful about the inputs just by looking at the outputs. OK, so just as a remark, we have quantifier alternation in this specification, and we have here the temporal modality globally, and we need that to be able to inspect the content of the execution over time. All right. So this is all very nice. We have a framework for specifying hyperproperties of reactive system, but now how do we prove them? And I have bad news for you. So it turns out that such for all exist temporal hyperproperties are very difficult to verify, and even more so if you want a fully automated approach. And unfortunately, there is still no clear interactive proof technique targeting such hyperproperties. So automation is still relatively out of reach, and interactive proofs are or deserve a little more exploration. So what are the challenges? Why is it so difficult? So if we take a step back and look at the general problem we're looking at proving statement of the following form. For all trace tau1, there exists a trace tau2 such that the two traces together satisfy some relation that is our specification. Now, if we want to do a direct proof of this statement, the first thing we need to do is to explain how we instantiate the innermost existential quantification. So typically, in a constructive setting, we do that by giving a skolem function that is producing some execution based on some input trace. So once we have done that, which, by the way, might be a very complicated task, like specifying such an object as a function that reasons about infinite sequence of events is not necessarily trivial. But once we have done that, there is a second step. We need to show that it produces feasible executions, feasible traces. So that's the second step. Might also be complicated to prove. And once we have done that, there is still a third step. We need to prove that the trace produced by our function are actually compatible with the specification. Okay. So this is a very tedious and time-consuming process. And in particular, if we made a mistake if we make a mistake in the beginning, if we have a wrong choice of a function f in the beginning of the proof, this mistake can only be revealed at a later point. So for example, it could be revealed very late in the process of step 2 or very late after step 3. And this is not very desirable. It's going to be difficult to do a direct proof in that way. So instead, what we would like to have is a more incremental proof technique. And by that, I mean that we would like to progressively construct the witness for the existential quantifier and simultaneously prove that it's a suitable witness as we go. And another aspect is that we would like a local proof technique. And by that, I mean that reasoning about objects like big object like infinite sequence of events is complicated and not very intuitive. Instead, we would like to reason about much smaller objects like state and events. So the contribution we present in the paper is exactly going in that direction. What we're proposing is we're presenting HICO, which is a framework for deductive proofs of all exist temporal hyperproperties. It is mechanized in the Coq proof assistant, and it has support for incremental proofs via parametrized co-induction. Okay. So let's give a quick tour of HICO's core. So at the very core of HICO, we talk about labeled transition system. So we have a set of state, S, and a set of events, E, and a transition relation that explains how to move from state to state. Maybe we have some initial state, I. Okay, so very general setting. And specifications are going to be expressed as relations between infinite sequence of such events. So again, very general. We're not making any assumption about how the specification are expressed. We just take arbitrary relation between a sequence of events. And now how do we connect systems and specifications? We do that by introducing proof quadruples. So how are they looking like? So in the middle, we have two states. So on the left-hand side, it's going to be a state that belongs to an execution that is universally quantified. On the right-hand side, we have a state that belongs to an execution that is existentially quantified. And at the very right of the quadruple, we have a trace relation, or little specification here. And the important thing is what is on the very left. It's a context that consists of a state relation. So it can also be viewed as a set of pair of states. And if I want to be a little more precise, actually, there are two kinds of quadruples because the context is controlled by guards. So the first kind of quadruple is telling you that the context is protected by a guard, and this is represented by this solid box around it. And the second kind of quadruple is telling you that the context can be used in the proof, and this is represented with this dashed box. Okay. So something important to notice is that the definition of those quadruple is co-inductive. And in particular, the definition of the dashed one depends on the definition of the guarded one and vice versa. So it's a cyclic definition. Okay, so I'm not going to present the definition, the exact definition, because that would be very long and boring. Instead, I'd like to explain how the system can be used for the specific case of relational invariance. So I'm going to focus for a bit on specification that can be expressed as globally some relation between events should hold. And we're going to look for a bit at the proof rules for this specific case. OK. So the first rule, the most important one, is actually the soundness theorem of the framework. What it says is that if you want to prove that a transition system satisfies a property of the form for all exists globally phi, then it suffices to show that initial state of the system are related by a quadruple with an empty context. So that's the first thing. Now, how do we actually prove such quadruples? So the main rule is the step rule. And what it says is that if you're focusing on two states, S1 and S2, what you have to show is that for all way to transition out of S1, there is a way to transition out of S2 such that the events emitted by those transitions are satisfying the relation. And then the targeted states are, again, related by a quadruple. Now, the important point is that the context is released. The guard around the context is released when we are making a step. So now the question is, how do we make use of the context? And the two following rules are explaining us exactly how to do that. So the invariant rule is explaining to us how we add things to the context. And what it tells us is that at any point in time during a proof, you can extend your context with a relation H prime that contains the current state you're looking at. And the cost to pay to be able to extend the context is that the proof resumes with not S1 and S2, but arbitrary S1, S2 in the new relation that you added to the context. OK. Another very important note is that contrary to the step rule, the guard is not released by the application of the invariant rule. Otherwise, we would be unsound. OK, and now the final rule is making use of the context. And what it tells us is that whenever the context is not guarded, we can use it to discard the current proof tree. To close the current proof tree. So it suffices to show that the current states are in H if H is unguarded. All right. Perfect. OK. So I just want to make the point that this satisfies our original goal. It's a local proof technique because we only refer to state and events, and incremental reasoning is achieved with the invariant rule. So unfortunately, because of time reason, I cannot explain to you how to use those rules on a concrete example, because this would be a little bit too long. But I want to make the point that this also applies to more than just globally phi. Actually, it applies to arbitrary safety relation via the notion of property derivative. I think there is a talk about that in the session, actually. But so yeah. And as a corollary, you can also derive some useful rules for other temporal modalities, like, for example, weak till or the next modality. It also applies to programs written in a programming language. So if you give me a small step operational semantic of your programming language, you can instantiate the framework and derive some very nice syntactic rules to reason about your programs. And it also generalized to for all star exist star. So I only talked about the specific case where you have one universal quantifier and one existential quantifier, but it also works for n universal quantifiers followed by m existential quantifiers. And it generalizes in a very natural way. OK, so what about limitations and future work? So completeness. We proved soundness, but the system is incomplete. There are very easy counterexamples to that. And of course, it would be nice to have completeness. But my intuition, having worked on this for a long while, is that it's not possible to reach completeness if we want to preserve as much incrementality and as much locality. Or at least it's very difficult. It's not clear to me how to achieve that yet. One research direction is to look at prophecy variables, which would be a way to make the system more complete, but I'm not sure that it's enough to be really complete. OK, another interesting question is non-constructive aspects. So it turns out that the soundness proof of this logic is non-trivial, and in particular, it requires a relatively subtle use of the axiom of choice. Now, the natural question is, can we drop this? And the answer is no, we cannot. I have formally proven that. Another interesting research direction is probabilistic treatment of the existential quantification. So this framework focuses on properties of the form for all exist, but in some cases, we not only care about existence, we care about existence with a high probability. So this would be very interesting to look at. And last, combining this framework with separation logic in the style of simularis, for example, would be very interesting. And in particular, it would allow us to leverage the very nice reasoning principle of separation logic to specify heap manipulating programs. All right. So if you want to know more, want to learn how to use this system, look at example, look at the proof of soundness, all the details are in the paper. The Coq formalization of the whole system is also available on my GitHub, so please have a look if you're interested. And otherwise, I'll be around for any question.
Great, thank you. Thank you very much, Arthur. We have 5 minutes for questions, and please raise your hand, and we'll get you a mic.
Yeah, so I have 2 questions. So for finite cyclic structures, we know that for all exist box hyperproperties, you have completeness with a finite number of prophecies. So
yes.
What's different in this setting? And the second question is, okay, I'll ask the second question after.
Yes, so that's a very valid point. The problem is, I think you're referring to a paper that says that you can add prophecy variables and then you recover completeness, but the problem is that then the property that you have to prove is no longer a safety property. And I think you cannot prove it by co-induction only. You need something a little more specific. So I'm working on extension that would support that, but it's very non-trivial.
Yes, it's not safe.
Yes.
They're not safety properties. They're local to each trace, but they're not safety. Yes.
Yeah, exactly.
Okay, and the second question is, since you're going to an interactive proof system, why to restrict yourself to synchronous hyperlogic instead of an asynchronous one?
That's a very good question. So for the purpose of this talk, I acted as if everything was synchronous. Actually, you can very much deal with non-synchronous systems. This works equally well. Yes, and there are various ways to actually weaken the underlying co-inductive relation so that you have very nice reasoning principle in the case of asynchronicity.
Thanks.
Okay, thank you. We have another question over here.
Yes, thank you. I had 2 questions, but I think you answered one of them, so I will answer the other. This Havoc example you had in the beginning,
yes.
How should I think of that? Is that like plain non-deterministic choice? Like, are you proving there exists a non-deterministic choice that makes it work?
Yes.
Because that sounds like something that's not preserved on a refinement where I can make concrete the choice. And then if this is a security property that relied on all the non-deterministic choices being realizable, and then I refine it with an implementation that always makes a concrete choice, now I lost my non-interference or something like that. So is this just out of scope, or like what is? I'm
no,
not sure
it's not out of scope. So it's just. So I think one way to understand it is that there are many examples where you could specify the usual notion of non-interference, and it's a for all hyperproperty. But this is way too strong a requirement. You cannot even prove it, and yet you have the intuition that there is something that cannot be leaked. So the whole point of having this style of existential quantification is to weaken specification and still be able to prove something meaningful about program. So arguably, I agree with you that it weakens drastically the specification, but it allows you to specify things that otherwise would not be provably non-interferent. So it is still very useful in that sense. And I think it also connects to the comment I made about a probabilistic treatment of existential quantification, where we probably want something a little bit stronger, where you say, okay, there is a very high probability that things work out. So just very quickly, another way to look at it is that this existential quantification, in a security context, this existential quantifier can be interpreted as there exists a way to confuse an ill-intentioned observer of the system, essentially. So I don't know if it answers your question completely, but yeah, we can.
Any other questions? I have one question. Why don't we let the next speaker get set up? I'll ask. So my last question is about incrementality, and is that related to derivatives? The use of derivatives, where does it come from?
It does not. So not directly, actually. So derivatives are used so that you can actually reformulate the problem of proving the hyperproperty as a co-induction question. So in that sense, derivative play a role. But incrementality is really about doing the proof itself by accumulating knowledge while you're stepping through the execution of the program. So it is not. It has a link, but yeah,
okay.
not directly.
Okay. Thank you very much. Thanks again. Okay, so we are going to hear more about derivatives from Yongwei and their use in symbolic execution. Take it away, please.
Hi, everyone. I'm Yongwei Yuan from Polo University. Today, I want to present derivative-guided symbolic execution. This is a joint work with my colleagues at Purdue, Joe, Julia Bielkova, and Suresh Raghunasan. Before we dive into derivative-guided symbolic execution, let's first look at a common mistake when we manipulate linked lists. When we try to remove all nodes of value x from a linked list, we might make a mistake and accidentally have one node to have two parent nodes. Well, how can that happen? Let's remove this element 1 from the linked list. To do that, we start from the beginning of the list, we iterate over the list, find the element 1, and then we remove element 1 by making its next node 2 the second node in the list. While this effectively removes node 1 from the list, it does not prevent this element 1 still accessible elsewhere. So this is problematic. How can we catch this bug? Let's use symbolic execution. And before we dive into how this remove function is implemented in OCaml, let's talk about how we can represent it. First, we will use two key value stores. The first one is called n, which maps each node to its next node. The second key value store is called v. It maps each node to its value. And with this representation in mind, let's look at our function. The function has three main cases. First, if the list is empty, then we simply return the list unchanged. If not, we look at the value of the first node. If it's of value x, we simply return the tail of the list. Otherwise, we iterate over the rest of the list using a loop. And we remember our position using the previous node. At each iteration, we look at our current node. If we already reach the end of the list, we exit the loop and return the list. If not, we inspect if it is of value x, we remove the current node by skipping over it in the linked list using this put operations on key value store n. This put operation will create the invalid list structure we saw from the previous slide. We'll talk about it shortly. But whether the current node is of value x or not, we continue iterating through the rest of the list by return to the start of the loop. We will use this execution tree we just built to ground our discussion in the rest of the talk. And we will following the symbolic execution convention that we will use symbolic variables like n0 and 1 to represent the first node and the second node in the linked list as we traverse it. And we also need to finish the execution so that they terminate. And now we have two execution paths. The left one from the program point D, it involves the put operations on n, which, as we discussed before, it will create the invalid list structure. The right branch from the program point D, though reaching the same depth in this execution tree, it is safe because it merely traversed the linked list without modifying its structure. So really the question here is that which path should we take at program location D? At that point, we haven't explored the rest of the execution paths, but we want to have an idea of which branch do we take, which one is better. So let's talk about how can we guide the path exploration in a principled way. And our idea draws on the concept of derivatives from the formal language theory. And let's first define what are derivatives, and specifically, what are derivatives in our setting? Well, let's say we have a set of safe executions of the program. And the derivative of this set of safe executions over a program action is defined by the safe continuations following this program action. And using this derivative device, we're able to categorize the safe continuation at each program point as we traverse, as we explore the path in the program. And then, as an example, this is a execution we might observe as we execute the program. And this execution, it's merely traverse the linked list, right, using those get operations. So obviously, it's safe and included in the set of safe executions we saw on the last slides. And as the program inspects the first node in the linked list, this using a get operations on key value store v, we notice that this program action, it matches the first action in the safe execution. Therefore, the derivative will contain the postfix, the corresponding postfix. And as we continue exploring the path until we reach program D, we keep track of the derivatives and update it. And now we have two possibilities again. The left branch, again, it makes a put operations on key value store n, which does not match. Interestingly, it does not match the safe action in our execution. Therefore, the derivative becomes empty, indicating that no further actions are safe. And on the other hand, the second branch of D, it simply returns to the start of the loop, so the derivative remains unchanged. And when we look at those two derivatives, it becomes clear that we should take the left branch because it will definitely give us an unsafe execution down the road. With this intuition of derivative in mind, let's talk about how we can represent it. And we represent them using symbolic finite automaton. And let's start by constructing an automaton that recognizes the executions of the program. Let's say we start the program execution with two nodes A and B connected initially. What are the safe operations under this state? Well, it's obviously safe to reconnect A and B, or modify other parts of the linked list, or does not modify the structure of the linked list at all. It is also safe to first disconnect A and B using a put operation. And then, once we disconnect them, we're safe to perform whatever operation on those two nodes. On the other hand, there are also unsafe operations. If without disconnecting A and B first, if we assign B a new parent, then this will create the invalid list structure as we discussed before. And because we want to prohibit such invalid list structures throughout the program execution, we consider all future events to be unsafe. With this automaton structure in mind, it not only allows us to succinctly represent safe executions, it also allows us to represent their derivatives. As an example, initially, the initial state Q0 represents a derivative that contains a safe execution like this. It first disconnect A and B, and then assign a new parent to B. If the program indeed first disconnect A and B, then the derivative will update and suggest that, well, now it's safe for you to assign a new parent to B. On the other hand, if our program directly assign a new parent to B other than A, the derivative will correspondingly suggest no future actions are safe. Notice that automata here refers to those free variables like A and B, which is quite unusual for automata. Please see our paper for how we formulate this as a symbolic variant of derivatives. Now that we understand, well, safe executions and their derivatives can be represented using symbolic finite automata, let's return to our original path exploration problem, and see how we can make the right choice. And we return to our same old execution tree here, and let's see how we can compute derivatives for various program points. As we enter the program, the derivative can be represented by Q0 from the automaton, because Q0, it represents all the safe executions the program is allowed to perform. As we follow the execution path to program point D, we iterating over the linked list and inspecting the elements in the list using those gets. And those get operations, it will match the self-loop transition in the automaton on Q0. Therefore, the derivative at program D is still Q0. The right branch of program point D, it simply returns to the start of the loop. Therefore, the derivatives remain unchanged, and which is still Q0. On the other hand, the left branch, it will make the put operations on N, which attempt to remove the second node from the list, which is on1. And this put operation, while it will match both the left transition from Q0 and from Q0, we will prioritize taking the transition to the left, because that will give us more chance to find an unsafe execution. And the derivative at the left branch can be denoted by this best state Q2. We omit details on how we can generate constraints over A, B, N0, and N2, which are essentially path condition in symbolic execution. Please refer to our paper for details on how we generate those. But what really matters here is that with this derivative computed for both branches of program D, we're ready to make a decision. The left branch, the derivative suggests that, well, no future actions are safe. So we should definitely take the left branch, and indeed, we can find the unsafe execution towards left. By making this decision, we avoided wasted effort on exploring the rightmost execution path of the program, which essentially is iterating over the linked list without removing any nodes, so that it is not making any progress towards the violation of our unique parent property. So we avoid exploring that unproductive path completely. To evaluate our derivative guided idea, we implemented in UCaml a symbolic execution engine that is called Hatch. We compare Hatch with two baselines. The first one is a naive symbolic execution engine implementation that does not leverage derivative. The second one is a recent work on whole automata type that is essentially a verification idea, but it's against a similar style of specification as we. We run all those tools on 10 abstract data type implementations that are implemented using various libraries, including key value store, list, set, tree, and graph. Among those abstract data types, we introduced 30 artificial bugs that will violate complex safety properties like the unique parent. And we observed that Hatch is able to find most bugs in 1 to 2 seconds. More importantly, Hatch is able to find those bugs faster. So the first two benchmarks are quite challenging, but still we are able to perform orders of magnitude faster than the two baselines. More importantly, there are more challenging benchmarks where both naive approach and the verifier either times out or runs out of memory, but Hatch is still able to find those bugs within seconds. To conclude, we we recognize that the safe executions of the program can be captured using symbolic finite automata. And the structure of the automaton allows us to compute the derivatives, which in turn categorize the safe continuations at different program points as we explore the path of the program. And those derivatives, in conclusion, provide principled guidance for path exploration in symbolic execution. And with that, I'm happy to take any questions.
Thank you. So I'll start with the question. So it seems like you use the automata to divide the state space, and you, in some cases, if you're fated to fail, like on the left side, then you want to go that way because whatever you do, you're going to be unsafe. And on the other side, well, you might stay in the safe space, but you still have the potential to fail. But what happens when, like, you have some red on both sides? Do you do some counting scheme, or do you like toss a coin? I mean, because you're not always fated to fail, I guess. You might have like more red states on one side, or
Yeah, that's a very good observation. And indeed, like you can even go back from a red state to a green state, right?
Oh, sure.
Yeah. So what we did in this work is we measure because each program point now have a corresponding to automata state, and we can measure the shortest distance to a bad state in the automaton. And we use that to prioritize, okay, which should we take?
Okay, so if going one way gives you a potential shorter path to a failure, you'll choose that. Okay, awesome. Okay, other questions? We have one in the back.
Thank you for the nice talk. So I'm going to ask a kind of provocative question. In the keynote this morning, Loris's keynote at the end, there was this idea about if an LLM is generating a program, it goes token by token, right? And it seemed like watching your talk, sort of from a high level, it seemed like you could apply these techniques in that context because you're receiving one token at a time, and you can sort of apply the symbolic execution on the fly with derivatives. Do you think that's an interesting idea, and is that something you have thought about?
Yeah, that's a very interesting observation because indeed, I think the idea of using derivative is not new at all. Like there are a lot of work on runtime verification, which essentially they have automaton which serves as a specification, and as our new events produced, you simply compute the derivatives over the specification. But I think it's certainly it will be if indeed if the specification can indeed be represented as an automata, and we can certainly use it as a guardrail to guide large language model. Yes.
Okay, good answer. Thank you.
Another question over here.
So thank you. My question is, what kind of semantics are you using for your language, and how do you have any correctness specification of this decision procedure? Well, not this algorithm.
Yeah, good question. So indeed, we are our setting is it's kind of specific where those operations like put and get, their specifications are also defined by pairs of those automata. And so with that, I mentioned briefly to answer the second question, which is do we have any guarantee of this algorithm? I mentioned briefly in the evaluation that we have a naive implementation. So in the paper we have two set of semantic rules. The first one is the naive one, which does not use derivative, and it's pretty straightforward. That operates over those automata. And then we have a second set of operational semantics rules that leverages derivatives, and we show that they are the derivative guided ones are sound and complete with respect to the naive ones. Does that answer the question?
Okay, great. Thank you again.
Thanks for all the questions.
All right. The next talk is by a colleague of mine, Margezianis. And in a strange twist of fate, I happen to be a co-author on this paper. So if somebody wants to double check my timing, I'm trying to be very accurate, you're welcome to do so, but I am going to hold him to the same set of constraints as the other authors. Take it away.
So thank you for the introduction. And so, yeah, so this is work together with Thomas Ball, the same Thomas Ball who's also the session chair. So I have this unique opportunity. If I get difficult questions, I can delegate them to the session chair. Anyway, so and Gabriel Ebner, who's a collaborator here, and then Yekaterina Zuchko from Tallinn Technical University, who's been working on this with us. So let me start by giving you a little bit of history about regularity, omega regularity, and derivatives. Now, derivatives, this word has appeared at least twice in both talks. So let me give you a little bit of background. I go rather quickly because it can take a long time here. So from regular expressions introduced by Kleene, roughly 10 years or so, a decade later, Rzhowski introduced this notion of derivatives that actually applies to the regular expressions in extended manner. So you have also intersection and complement there. This was actually inspired, so this work inspired Thomson's algorithm. Although he didn't support the other operators, just the standard regular expressions, but he explicitly sort of says that in his paper from '68. It took a while. There's a bunch of work on derivatives, but not in the sense of matching or regular expression work, until partial derivatives were then introduced by Antimirov and then used a lot also in other contexts in '95. And then it was then in 2009 that Owens and other people then realized that a bunch of the theory that Rzhowski initially introduced has somehow been forgotten. And in particular, that you can actually very efficiently deal with complement and intersection in the context of regular expressions and get it to work fast. So this work was actually then, we investigated it further in the implementation of Z3 regular expression with Caleb Stanford and Nikolai Björner, and integrated this idea, and well, we generalized these derivatives to a symbolic setting where conditions can be arbitrary modular theories conditions. And this work later then also affected the implementation of a new non-vectoring engine in .NET, and it was recently also formalized in Lean. Now, if we look at the parallel track of Büchi automata, we have omega regularity, then the core work of relating the Büchi automata to regular languages by McNaughton, and then the introduction of LTL, or linear temporal logic, in '77 by Pnueli, and then the study of LTL and tableau methods by Wolper, but also noting that LTL is not expressive enough for certain very common properties. And then at the same time, alternation elimination algorithm or roughly at that time, from alternating Büchi automata to non-deterministic. And then Pnueli also wrote a seminal paper where noting that omega regularity is really something that is needed in general purpose temporal reasoning. And but also Emerson proved some correctness or precise theoretical result in that line of work. And then finally, I'll stop here by saying that then one of the sort of really foundational insights by Vardi was this way of taking a formula and incrementally transforming it into an automaton that we call Vardi derivatives here. And I will make precise what this notion means in a few slides from now. So the motivation for our work here is looking at omega regular properties and using them in a context where we realize that LTL in itself is not sufficient. In practice, you need regular expressions to describe omega regular properties, as pointed out. Often you also need modular theories to work with a large alphabet. And this is something we studied with Loris a while back. And there is a summary paper that I point to here. Then modular theories have played a crucial role in many contexts, like temporal stream logic, the symbolic execution work that we just heard about, and then also in the next talk, which is on reactive synthesis, again, it's LTL extended with yet more powerful techniques, but also modular theories. So there are many applications, numerous applications to both linear temporal logic and regular expressions and automata algorithms, but typically not for the full class of ERE. Essentially, what I mean by ERE is extended regular expressions with complement and intersection. And we realized that symbolic derivatives that I will introduce, at least through examples here, provide a really powerful framework, a unifying framework, both going from regexes in Z3 up to actually really fast matching algorithms. So I'm really encourage you to attend the talk on RE Sharp tomorrow in the syntax and editing session that is really about that topic as well. So we introduced in this paper a logic called RLTL modulo A. That is a combination of regular expressions with linear temporal logic, but modulo theories. And this whole sort of framework is based on symbolic derivatives. And for us, the motivating application is when we work with a project called Service Synergy, where we study properties of behavior of web services based on their Swagger specifications and learning sort of on top of that what they're supposed to do. So we're essentially learning a model of the behavior. So let me just give you a definition of what this RLTL is, and then I'll show examples of it and sort of motivated slides. So first of all, we have regular expressions. So predicates from a given theory A, which formally is defined as an effective Boolean algebra. You have the empty word regex, union, intersection, concatenation, clean star, and complement. Then we have a combination with linear temporal logic formulas that would be next, until, and release, plus the Boolean operators. And then we have the regular expression combination operators that talk, first two talk about the sup prefix of the input with the regular expression, and the formula phi is the suffix. This is why they're called suffix implications. And then I have closure formulas, weak closure, negative weak closure. And I want to draw attention to the two interesting ones are complement of regular expression and omega closure that are typically not supported by any other formalisms. We can also, so then there are also, of course, the shorthands for globally and finally as usual. And then I want to point out something that is very elegantly supported by derivatives. We don't talk about it in the paper, but I wanted to put it in the slide, which is, for example, adding new constructs, such as fusion. Fusion is a very interesting construct where it takes two languages and combines them by looking at the unifying element. So a word accepted by one regular expression R1 has to end with a letter that is then accepted by the regular expression R2. And this is commonly used in the context of PSL, so property specification language. And in the case of actually existential suffix implication and universal suffix implication, it also appears internally in the semantics. It's kind of an interesting sort of purely language theoretic notion that I haven't actually seen in regular expressions being used otherwise. So here are a few examples. Like in the pure LTL or modulo A fragment, you can say things like X is infinitely often positive, or X being positive is a stable property. It's finally globally positive, or things using extended regular expression. You can say things like X is even in all even positions. That is sort of one of the classical examples by Wolper that is cannot be expressed in LTL. And then there's another interesting one, which is all proper prefixes of this infinite word match the regular expression R, which is kind of a combination of two negations. First, you have the regular expression complement, and then and that sort of transitions with the suffix implication to bottom, which is a kind of a complement as well. And this really illustrates the power of complement. And the reason it works is that you really never actually construct the automata when you complement, but you defer, you propagate complement along the derivative itself, and delay it, so you work lazily. So just to give an idea of where this can be used is symbolic model checking in RLTL, which can describe high level as follows. So you want to show that a given non-deterministic Vicky word automata, I will define it later, will satisfy condition phi in RLTL. You first apply the symbolic derivatives to construct an alternating Vicky word automaton. At that point, you apply alternation elimination to get a non-deterministic keyboard automaton, and this algorithm is described in the paper. It's a generalization of Mayani Hayashi 84 algorithms lifted to modular theories. And then finally, you build a product, or per product, you also use a variant of this A algorithm. A is like Swedish pronunciation of the letter. And then here you can use classical algorithms. Beautifully, this 92 algorithm of nested depth first cycle detection is beautifully explained in the paper, and you can just essentially take it right there and put it in symbolic form, more or less as is. So some classical algorithms just work right out of the box. And of course, this whole thing can be incremental. All these steps can be joined into one because it's all actually lazily evolving automata, derivatives of formulas into automata. And I think the next 2 slides are going to be probably the most important slides of this talk to remember, which is sort of generic. So let us define what it means for a logic B to have a derivative function. So suppose that this logic is associated with a language semantic. So we talk about some words over some alphabet sigma, and we say that the set of words modeled by this formula is the language. Then we say that this logic has a derivative function when there exists for all formulas and all elements a mapping raw from phi and A to another formula such that the AW is in the language of phi and only W is in the language of the derivative of phi. So you saw already the definition of derivative from the last talk. I mean, the semantic definition. So this is the key here. So 2 examples. For finite words, you have the classical definition of Brzozowski derivatives for extended regular expressions. And this would be an example. So here, the D plus is just, one or more sequence of digits. So, and in the case of LTL, the rho would be precisely the LTL to the alternating Buki automata translation given by Vardy in 95. Exactly. So there is really no difference. So, for example, if you take a formula such as globally x is always positive and remains even until divisible by 3, then of course this is now a formula in an infinite alphabet, which is quite typical in many applications. And you would typically do predicate abstraction and work pieces of it. But here you don't need to do that. You just work modular theory. So here, the alphabet itself is essentially interpretations of all the variables mapping to values in integers. So symbolic derivative of a logic now is essentially a partial evaluation of the concrete function with respect to a given formula. Again, note, for all elements, the term that is created is an if then else term, a nested if then else term, so that if you apply to the element, it evaluates to what the concrete derivative function would do. So for example, returning to the previous example, you would have 2 cases. Either the derivative, either it is a digit or it isn't a digit, in which case, if it isn't, you reject. Or you have a formula in LTL, in which case you will get 3 cases. I'm not going to go into details here, but you get, again, examples of how these leaves you would evaluate, follow the path according to what value x has. So transition terms have built up their own algebras. It's induced from A and B. So both A and B are sort of Boolean algebras, and the transition term is a new Boolean algebra that has its own rewrite rules that are really key. So when you operate operations in them, you often simplify them aggressively. So here would be an example where suppose you have this transition term, this nested if then else term that has some subterm in it, like a leaf or a subterm. Well, then you can apply the given Boolean law that applies to all Boolean algebras. You can simplify to F. We can essentially eliminate the disjunction. The same applies to G conjoined with the top element. Then now we can take the next phase, which is cleaning or simplifying this transition term even more by using the modulo A aspect of it, which here would be, for example, that if x and y are integers, then it is impossible that 0 is less than x, and y is greater or equal to, and x is less than y. So this branch is unsatisfiable, which means we can simplify the transition term to this one. But now the condition y greater or equal to becomes completely irrelevant, so we can just shortcut and eliminate it to this term. So that kind of illustrates a very common pattern that occurs in working with algorithms that work with these transition terms as a combined sort of combination of two algebras. So using this notion, we can now define alternating Büchi automata that I mentioned earlier as essentially 5 tuple that has finite number of states, initial state combination, and the mapping from states to transition terms whose leaves now are these Boolean combinations. And there is a final set of states. So here would be an example, and this would be the concrete representation as expressions, if and else expressions. Okay. So we also mentioned a little bit about non-deterministic Büchi, which essentially are a variant of this where conjunction is disallowed. So your initial state is a disjunction, and or the leaves are disjunctions as well, so don't allow conjunction. And we can sort of show examples of how sort of in the classical case, in the case of if we now repeated, take a fixed point of the derivatives, what kind of automata would we get? So here would be two examples, one in ERA, one in LTL. And here would be a kind of a picture that I showed earlier, but just to connect it to LTL here, it's a globally finally alpha and finally not alpha formula that results to this picture that you saw earlier. And if we now apply the AI algorithm here, you would get this 3-state Büchi automata, which really you can think of it as flattened form, as sort of a symbolic automata whose only accepting state is S0 and that has an infinite acceptance condition. Now, let me show you one example of the existential suffix implication and how derivatives are combined. And this would be essentially symbolic derivative functions for RTL combined with those of ERE in a single framework. And for example, if you would take a formula AB repeated at least once as a prefix condition, followed by something that is globally gamma, then you would get something like this. And another example would be, trace analysis, which I unfortunately don't have. And then time to go into. And the formalization in Lean, you can look in the artifact. And the thing I wanted to point out that the formalization in the math and Lean versions are really, really similar. So you can really follow what is in Lean as well as what is in the paper, I would say. And these are some future work items. Thank you.
Okay, do we have any questions from Marcus? We have one right in front. Let's go there first. Please, in front. Keep your hand raised so I can see who the other questions are. Okay.
Thanks for the talk. In the middle of the talk, you presented the pipeline to go from RLTLA to Büchi automata via alternating Büchi, so you need Miyano Hayashi for there. There has been a paper in 2015 about using partial derivatives to go straight from omega regular expression to Büchi automata by non-determinizing on the fly. Do you think you could also do that and avoid having the Miyano Hayashi in the middle?
Yes, I think that's possible, and it has to do with the normal forms of derivatives.
Yes.
So essentially, the mirror of normal form essentially is like a DNF normal form of the transition terms. Yes. If you work with those, you can often avoid the conjunction and directly get sort of a form that you're talking about. You're absolutely right.
Okay, good. Thanks a lot.
Yeah.
Oh, hi. Thank you. So I have a comment and a question. So first, I have been reading a lot of your and your collaborators' paper recently, and I really like them. I enjoy the vast amount of theory that you put out. But I realized one thing is that there's other part of other part of automata community which uses like bioalgebra technique, and I've seen a lot of overlap between you guys' work. It would be really nice to see how does this work connect. So that's the comment. And another thing is, so you mentioned like the cleaning part where you basically modulo the theory. And that, I think, recently I was trying to do that, and its structure is not too nice from a bioalgebra point of view. And so typically how people resolve that is to construct a automata directly without modular the theory. So every time you construct a transition, you modulo all the theory that you can modulo. Yeah, that's the question. Sorry. So have you considered that approach?
So I didn't quite understand the question here.
I'm not sure either. Algebras concept? Yeah, I'm not. Why don't we take that one?
Maybe we take that offline because I'm not familiar with bialgebras. First of all.
Yes, I think we're gonna. I'm sorry. We're gonna have to cut off time for questions to keep on time. Please come see Marcus after. But I do want to keep us on time. We have our last speaker. I want to give him full time. Yeah, fine. Okay. We're getting ready. We have our last talk of the session that Philippe will give on translation of temporal logic. And please take it away.
For the introduction. Can you hear me? Okay. Yeah, so I'm going to present you how we translate temporal logics efficiently for infinite state reactive synthesis. So why do we even care about infinite state reactive synthesis? So I mean, as we already seen this morning in the keynote, right, in synthesis in general, like there's a problem where you want to automatically generate some implementation from some kind of high-level specification that kind of describes how correct behavior of the system looks like. And one major historical direction has been program synthesis, as we've seen it in this morning. And in program synthesis, what you want to get is a classical program, in the sense a program that gets some inputs, does some computation, and produces some outputs. And that's why, like, usually a specification for such a classical program is via the relationship between the input and the outputs. And usually you have something like a grammar that defines how a well-formed program looks like. In some sense, right, you kind of, what you generate is some kind of like data transformation. And since you often have like some like data variables and so on that have like some integer types or something like that, you have an infinite state problem. The other direction is finite state reactive synthesis. There you want to generate a finite state controller. Think of something like a Mealy machine that runs over time and interacts with its environment. So it gets some input, produces some outputs, gets some inputs, produces some outputs. And that's why like one natural way of specifying such system is via temporal logics, right? And the other way is like, for example, via two-player games. And the main technique to do synthesis in this setting is via game solving. So either you have a game directly or you translate the temporal logic formula to a game and then you solve the game. But now if you think about it, many actual problems, they need both, right? You have both like this infinite state, so you want to work with data variables, you want to work with integers and so on. And at the same time, right, you have this aspect of abstract control and running over time, right, interacting with the environment. And since like temporal logics provide us like this high-level way of specifying things, we want to actually look at temporal logics in this context of infinite state synthesis. And that's why, like, recently this problem has attracted more attention, right? There's a wider body of work that has been done towards that, but very recently there has been like two approaches that work on an extension of LTL with like also with data, right? And what they do is, right, they take this extension, right, they abstract back to LTL, and then they use the finite state synthesis problem. Similarly, like there have been like ways of doing symbolic game solving, where you take like the finite state game solving algorithm, and then lift it symbolically to work also in the infinite state, to handle the data that you have symbolically. However, like both of these kind of approaches, they have the problem that they kind of lift this finite state problem kind of to the infinite state problem, and then in an infinite state problem, you have like phenomena that you don't really have in the finite state. So they are like, this can be limited. That's why at last year's POPL, we introduced like a dedicated technique to kind of tackle this infinite state game aspect. So and as you can see, right, there have been other things in the meantime, right? So there have been improvements on the game solving side for the infinite state problems. But of course, as I already told you, right, we want to actually also be able to work with logic. And that's why in this work we looked at how to efficiently translate these temporal logics that talk about this infinite state space to symbolic games. Okay, just to quickly, I always mentioned like how nice logic is. Just a quick example to really make the point, right? This is like an LTL formula that tells you if infinitely often A holds, then infinitely often B, and infinitely often C have to hold, right? So this is like very nice to write, but if you want to write like a game or automaton, it might look like that, right? So you really don't want to write the lower one if you can write the upper one, right? Okay, so this is like now our logic that we work with. We call it reactive program linear temporal logic. So like you have of course you have Boolean operators and you have the standard temporal operators that you know from LTL. Right, if you don't know, right, you have, for example, the next operator, which tells that something they talk about time, that something has to hold at the next step. The globally operator that tells something has to always hold, or the eventually operator that tells you something has to hold at some point, right? And then we have predicates. So predicates are quantifier-free first-order logic formulas over some state variables, some input variables that come from the environment, and next state variables, right? So we have from some state, and we want to be able to relate the current state with the next state. Yeah, and if you know some state, right, the inputs are chosen by the environment, and the next state variables are chosen by the system, right? So there you have this interaction between the system and the environment. And through synthesis, what we do, we translate. We take such a formula, we translate it to a game, and then we want to solve it. So the solving aspect is kind of already covered by kind of previous works. So in this work, we really want to really focus on this translation aspect. So now there's a way to actually directly translate such a formula to like a symbolic game by using the translation over LTL. So what we do, let's take our example formula where we say, okay, we have some state variable x that should always be incremented, and infinitely often it should be greater than 0. Now we can replace those two predicates by propositions and get the LTL formula. Then we can use a standard construction to get like an automaton, like in this case a Bücher automaton for this formula. And then we can do kind of the back translation, right? We replace these predicates back by, so the propositions backed by the predicates, and then we get this, and then we can get a game out of this. Here it's a one-player game, but like if you would have inputs, it would be basically the same. And now I claim that we have, during this translation process, we have actually lost some kind of information. So why is that? Well, like now if you just look at this formula, just think about it, right? I mean, this is somewhat redundant, right? Why? Well, if we always increment x, then at some point, x will be greater than 0, and once it is greater than 0, well, it will always stay greater than 0. So it will also be infinitely often greater than 0. So in some sense, we could drop this right-hand part, right? I think this is fairly obvious in this formula, but I claim it's not very clear in this game, right? And if you think about it, this is still a simple example, right? If you get to something more complex, it might be even less clear. So the question is now, how can we apply this reasoning to games? Okay, so that's where our method kicks in. What am I doing? Okay, we start with a temporal formula, and then of course, we do this direct translation to get a symbolic game. And what we also do is we construct some kind of monitor. You can imagine it's something similar to automaton, but it's not an automaton. And this monitor uses some kind of theory information and this temporal structure of the original specification. And with that, it can use for some finite prefix, it can give us a verdict. And this verdict, right, we can use, right, we will construct a product from a monitor and a symbolic game to get an enhanced game. And this verdict will help us to get a smaller game and to kind of simplify the winning condition, such that like if we then solve the game, right, it will be hopefully simpler to solve. Okay, now how do we construct this monitor? Let's go back to an example. So this is like a variation of our previous example. Instead of adding 1, we add d, and this d should initially be greater than 0, and from this point on, it should not change. Okay, so when we do this by doing some expansion and applying some rules. So we start our initial state of our monitor is this formula, and we have, what's important to note, we have these phi sets that kind of are things that we track that kind of always hold, right? Or initially we know that d should always stay the same. Okay, and now we can apply a rule. What we can see is like if d always stays the same and initially d is greater than 0, well then it's an invariant, right? So it will always
stay greater than 0. You can check that with an SMT query. And now we can add this information here that D will be greater than 0. Okay. Then we can compute kind of the next state, right? What happens after one step? For example, if D is smaller or equal than 0, right, then this whole formula becomes true. If it's greater than 0, but we don't keep it the same, formula becomes false. And otherwise, right, like the second part here now becomes relevant. So we add x prime equals x plus d. We add this to the things that have to always hold. And now infinitely often x should be greater than 0. Okay. Now here we can apply a second rule. So what you can see is, right, if d is greater than 0, and we always add d to x, right? So we always add at least 1. So we know that, like similar to our previous example, at some point x will be greater than 0, right? And this is a bit more complex check. Now this is kind of a fixed point computation, but with this we can derive that also from this point on, like x should be, or eventually x should be greater than 0. Okay. Now, if you look at that, right, this part now is under globally. So infinitely often x should be greater than 0. So in some sense, this part now here is redundant, right? And now we can also remove that and get the simpler formula. Yeah, and then we can like add the missing transitions, right? And here it's important to note if d stays the same and we always add d to x, right, you will always stay in this part. Now the second step is to actually add this verdict that makes kind of the power of the monitor. So like if the formula is true or false, right, we know that the system will win for sure or lose for sure, so we get an unsafe or valid verdict. Then we have this safety verdict, and like this, what you can see, this formula without the derived parts is a safety formula, if you know what that means. But what's important to note here, right, it's fine for the system to, if it always stays in these blue parts, right, the system will win. So this is why this is a safety part. It's sufficient to stay here. Okay. So this is how we construct a monitor. And now we have these verdicts, these 4 different verdicts. And also, and now we can construct a product. What's also important to note, right, this monitor construction is completely independent on how we constructed the symbolic game or how we will later use it. So it's like, if you would improve that, right, you could still use this approach. Okay, so how do we combine that? So let's go back to our example. So we had our monitor here, and really the thing I want to highlight for this example, once we are in the safety part and this blue part, we want to stay here. Then we build this direct translated game, which looks something like that. And here, right, the goal is to infinitely often visit one of those 2 locations. And now we can construct a product, and this product will look like that. And now it's here important to note, right here we had a part where we had to alternate, right, and infinitely often do that. Now here, this is kind of, the monitor has told us this is a safety part, so it suffices if we can just stay here, right? And so we get some easier winning condition, right? Because, I mean, it's a safety condition, and it's kind of easier to solve. Okay, so we also evaluated this, because I claim this made stuff easier, but we also wanted to check it. So we built a prototype that uses Spot to translate the LTL formulas to automata. Because for the reasoning, we use Z3 as the SMT solver. As the underlying game solver, we use the game solver that we created for last year's POPL. And to these fixed points, right, we use MuVal, which is a tool for computing for solving fixed point equations. And we compared them to the other approaches that exist to handle these temporal logics with data, namely Raboni and Temos, which are these both like abstraction-based approaches that I mentioned earlier, and of course also the direct translation, just to see how this compares. And then as benchmarks, we used literature benchmarks as well as new benchmarks that encode some kind of more complex behavior, because those were many of them were still kind of simple. Okay, so this is an excerpt from our evaluation table. Here we have the literature benchmark. So as you can see, right, usually this monitor stuff adds an overhead over the direct translation in these cases, right? Because you have to construct it, you have to build a product. It might make the stuff even a bit also larger in some sense. Also, like in some cases, right, this can fail because this propositional translation from LTL to automata might make the symbolic game just too big. But like in the cases where you get more complex scenarios, right, this monitor approach can be very beneficial, and these abstraction-based approaches and the direct approach, they just fail, right? Because you really want this additional reasoning. Okay, so to conclude, I hope that I convinced you that looking at this, at the temporal logics in the context of infinite state synthesis is very interesting because they provide us with this higher level of abstraction to kind of efficiently specify things. And we've seen that like actually doing already reasoning on this higher level structure, which has like this like more high level connection, already reasoning there can be beneficial for the overall synthesis process. And for that, I showed you our monitor-based approach, which allows us to solve the games later than more efficiently. Okay. Thank you for your attention.
Thank you very much. Question in the front.
Good talk. I really like the monitor approach. But I'm not quite familiar with the game literature on those games. So for the verdicts you mentioned, like are those common concept that has already been explored, or like they're new to this work?
What vertices do you mean?
Verdicts like the safety, unsafe, valid.
Okay, so I mean, the application of this verdict to this kind of game solving, this is kind of the main contribution of our work. Right? In some sense, you could even construct a monitor in a different way, right? I mean, you could still do this product, right? Because it's just as long as the properties are satisfied, it would still work in some sense.
I see. Thanks.
Question here and then in the back.
Great talk. I have this kind of curiosity question. Have you thought about coming up with a notation for benchmarking? So because obviously you use SMT in this context, you use LTL. Have you thought about sort of standardizing sort of notation? This is something I thought about, but I haven't seen anybody done that. Also for PSL.
This is currently work in progress. We have like a deadline in 1.5 weeks. We're writing a tool, and that contains exactly that.
Awesome. So one question, where would you place the work on LTL modular theories, the reactive synthesis for that in your classification, reduction, some set of tools, and symbolic tools on the other hand?
I mean, it's not like those things are, like strictly separated, right? So I would probably, I think it's something in between, right? It's not like also like for abstraction-based things and symbolic things. I mean, there are lots of techniques that kind of jump from one to the other, right? So it's not like I would say that you can always strictly classify in one of the categories. Does it answer your question, or?
And the other question is, in your example, you were using d prime equals d somewhere, but d is an environment control variable.
No. In this case, like this was also like some state, right?
In your formula, you have d prime equals d.
Yes.
D remains the same for it, but d is environment, right?
No. In this case, d is also state. This formula also doesn't have like an environment imposed. I mean, just to make the example simpler, because right, if you get environment, it gets more complex.
Then it's super simple. You just choose d 0, 0 less than 0, that's false, and then you're fine.
No, like usually in our semantics, like the initial values of the system are chosen by the environment. So the initial state, right, you have to satisfy that for all initial states. But if you want to like have proper initial state, you need to have like an initialization step, right?
I think that is time, and thank you again for your talk. Thanks to all the speakers. It is lunchtime now, and lunch is at the ballroom. What?
No, don't switch.
Okay. All right. Perfect. Okay. Thanks for the introduction. Sorry for the voice. I have young kids at home, so I'm just getting over my about 20th cold of the season. Don't worry, I'm not contagious anymore, but my voice sounds awful. Okay. So this is some work that I did with one of my students, Joseph Lunderville. And what is this talk about? Well, kind of on one level, what this talk is about is the integration of circuit optimizations into these hybrid quantum classical toolchains that we're seeing more and more. So what's happening in the quantum computing space right now is that most compilers, most toolchains are moving to this model where we have interleaved classical and quantum computation, all in the same kind of representation. Right? And we haven't been able to really figure out how to integrate those circuit optimizations well into these tool chains yet. But kind of on a more philosophical or conceptual level, right, what this talk is about is the interaction between classical control and quantum data. Right? And we take this kind of novel approach where instead of considering quantum data flow, which is the flow of quantum data through one of these programs, we're instead considering quantum data flow, right? Which is classical data that's flowing in a quantum manner. Right? And to illustrate what I mean by this, let's consider one of these kind of hybrid programs where we have classical branching control and quantum operations corresponding to these white boxes. Right? So in the quantum data flow kind of point of view, we imagine the data flowing into and out of these white boxes as quantum states. Right? But the problem with this is that these quantum states have exponential size. So then when it gets to a join point, right, we can't really do too much interesting analysis because we can't break into these exponential size states if we want to keep things tractable. Right? But the thing is, if we peek inside these white boxes, there's a lot there's a lot of structure that we can use to kind of do a little bit more interesting analysis. In particular, inside these white boxes, we have all of this classical data flowing in superposition, right? So we take the approach of flattening this all, right, into just the classical domain, and we consider just the classical data flowing through one of these programs, right? It's just flowing in two different ways, out of superposition and in superposition, right? But what this allows us to do is to use classical techniques to actually do the program analysis. Okay. So just a quick overview of the quantum circuit model for those of you who are unfamiliar. If we have an n-qubit quantum state, right, what that is a superposition of the classical n-bit states, which I'm using lowercase boldface x to denote. Right? So that makes a quantum state a vector in a 2 to the n dimensional complex vector space, because the amplitudes are complex values. Right? So now if we have an n-qubit quantum unitary, that's a linear transformation on that state space, c to the 2 to the n. Right? And specifically, it's a unitary linear operator. So that means, among other things, it's invertible. Okay. And then a quantum program is often viewed as a sequence of these gates. Right? So we have a circuit diagram over here. The horizontal lines correspond to the qubits, and then these boxes are gates that are operating on the qubits. Okay. So circuit optimizations are an important part of quantum compilers because we really need to get the resources down in order for quantum computing to actually be useful in practice. Right? And there are a couple of different methods that we can use to optimize quantum circuits. One of them is rewrite-based. So we have a library or database of circuit equalities, right? And then when we have a circuit that we want to optimize, we just search for instances of left-hand sides of these rewrite rules, right, from the database, and then replace them with the right-hand side. Simple stuff. Another type of circuit optimization that I tend to work more in is what I would call semantic-based optimizations. So in this kind of viewpoint, instead we take the original circuit, right? We compute its semantics in some sort of tractable semantic model. Things like phase polynomials, and I've lost my mouse. Yeah, okay, yeah. Phase polynomials or polyexponentials or the ZX calculus, right? And then we go from that semantic model and we synthesize a new, more efficient circuit from the semantics directly. And to kind of illustrate this approach, we can consider the quantum phase folding optimization, which is kind of a standard optimization that we do in quantum compilers. The goal here is to merge or cancel out diagonal gates, because those are the most expensive to implement in fault-tolerant quantum computing contexts. So in kind of a rewrite-based approach, we might imagine taking this circuit on the left here. That consists of 2 T-gates and a swap gate in the center. And we might commute the T-gate through the swap gate along this line, this curved line, right? At which point now it's adjacent to a T-dagger gate. And we can use that rewrite rule or equation from the previous slide to just cancel both them out, right? Leaving only the swap gate. Now, the semantic-based approaches succeed because what they do is they mod out by these commutations so that you don't actually have to apply them, right? So it becomes a much more tractable optimization problem. And specifically, in the standard semantic-based approaches, all 3 of these circuits would have the exact same representation, right? So you compute the semantics of the circuit on the left-hand side. You see that semantically it's just a swap gate, right? You synthesize it as a swap gate, leaving out the T-gates. Now, the problem with these semantic-based approaches is they don't really scale to the real world, right? Because in the real world, we don't just have a quantum circuit. We have a classical computer that's communicating with the quantum computer, doing classical computation, right? Sending out gates to the quantum computer, right? And sending this back in kind of a feedback loop, right? And if we try to apply the semantic-based approaches to these kind of real-world quantum programs, we have kind of a problem because there's a mismatch between the 2 semantics. We don't have sensible ways of kind of integrating or unifying the semantics of the classical and the quantum computer, at least from the point of view of circuit optimization, right? And to give you an example of one of these kind of real-world programs that we actually see in real quantum code these days, we have this paradigm of repeat until success circuits, where we'll have a loop, right, that repeatedly creates some sort of state, does some sort of measurement, and then when we get a particular measurement result, we know we will have implemented the correct transformation, right, so we exit the loop. So in this particular case, this repeat until success circuit is implementing a diagonal gate. And now, at face value, right, we can't really analyze this circuit using standard circuit optimization methods because it's not really a circuit. It's a quantum classical program, right? But because we know that when we exit that while loop, we will have implemented a diagonal gate, what we can actually do is we can commute this T gate, which is also diagonal, through the while loop, right? And then cancel it out with the T dagger gate. Okay? So the problem is, how do we formalize these kinds of optimizations? And it turns out that formalizing these types of optimizations was really kind of the crux of this work. Once we had the correct formalization, the rest of it just kind of fell out pretty naturally, right? So the way we formalized it was by developing this notion of the classical semantics of a circuit. So the classical semantics of the circuit, we're saying, is the non-zero transitions from classical input states x, right, to classical output states x prime, right? So in particular, in quantum kind of parlance, we would say that the inner product of x prime and u of x is non-zero, right? So now, if we have a relation on classical n-bit strings, right, pairs of classical n-bit strings, that includes the classical semantics, right, we have this simple condition that allows us to figure out exactly when we can take a T-gate on one side of the computation, move it to the other side, right? And specifically, if every pair in that relation satisfies the fact that the jth qubit in the output is equal to the ith qubit in the input, right? Now we can move a T-gate from the ith qubit of the input to the jth qubit of the output. And we see an example of that happening here, right, where we have some sort of quantum circuit or quantum process, and the second qubit of the output is always equal to the first qubit of the input. So we can take that T-gate and just slide it through this process, right, onto the second qubit in the output. Okay. So now we don't just want to optimize circuits, right? We want to optimize programs. That was the whole point of this, right? And it turns out that if we formalize the classical semantics of these circuits in this way, it extends to quantum programs in a really simple way, right? So we used a program model where we consider non-deterministic quantum while programs. So basically, regular expressions over a set of actions that are quantum, set of quantum actions, right? So with this program model, right, we can define the classical semantics of a program as just the union of all the non-zero transitions for any particular program run, right? Any particular program run is just a linear operator, so we can define its classical semantics. Then we just take the union over all these runs. So then, in that sense, it turns out that the classical semantics is really just equal to the relational semantics of regular expressions. Okay, so we have our classical semantics. Now we want to approximate that classical semantics so we can actually do this program optimization, right? How do we do that? Well, one of the first things that we can notice is that standard quantum gates that we often use all implement affine classical transformations. So for example, the X gate, right, sends a classical state X to the classical state 1 plus X, right? And then we can also have branching classical or quantum transformations, right? So the Hadamard gate, for example, branches on a classical value X, right, to all the possible classical values Y. Right? So that means no relation between the input and the output of the Hadamard gate holds. Okay, but this kind of suggests that what we should do is we want to abstract these gates, and we can abstract these gates precisely as affine subspaces over the pre and the post state, right? So that's exactly what we do. And this notation here with the angled brackets, I'm just using to denote the smallest affine subspace satisfying those relations. Okay. So at this point, right, we have basically regular expressions, right? We have affine subspace semantics, and we're trying to compute an abstraction of the entire program as an affine subspace. We already know how to do that. This is a problem that was solved by Carr in 1976, among others, over the years, right? It's known as affine relational analysis. So we basically just reuse these techniques, right? In particular, we reuse a compositional version of affine relational analysis, where basically we just compute this affine subspace compositionally by composing in sequenced affine subspaces using relational composition, and then taking the affine hull for the union. Right? But the interesting thing about this is if we compute the affine subspace, right, corresponding to the program in this particular way, we actually get these interesting loop invariants that we can use to do some non-trivial program optimization. So for example, this loop here that just repeatedly swaps the 2 qubits, it satisfies the invariant that the sum of the 2 bits is never changed, right? So that means if we have on the left-hand side a phase rotation conditional on the sum of those 2 qubits, we can actually commute that through that loop. In this case, canceling out with this other phase rotation on the right-hand side of the circuit. Okay? Okay. So what if we need more precision, though, right? So if we take that circuit from the previous slide and replace the CNOT gates with Toffoli gates, which are the quantum version of the AND gates, right? Now we can still do this optimization because that loop leaves the product of the 2 bits invariant as well as the sum, right? But the problem is the strongest affine loop invariant in this case isn't strong enough to prove that the product of the 2 bits is unchanged, right? So if we want to do this optimization, we can't use our affine subspace domain. We need something that allows us to do nonlinear reasoning, right? But it turns out that there are techniques existing that we can reuse in this particular case too. So in particular, we can replace affine subspaces with affine varieties, right? And affine relations with polynomial ideals, right? And then use Grosvenor basis computations to actually implement the domain operators, right? So I don't want to talk too much about this. I want to get to some other stuff. But the main interesting thing in this particular case, it actually turns out that because we're working over a finite field, we actually get all polynomial relations, right, when doing this type of analysis. And it's because of a very esoteric form of Hilbert-Strong Nullstellensatz for finite fields, which states that the radical polynomial ideal over a finite field is just equal to the ideal plus the ideal generated by the field equations. So that was really neat, I thought. OK. But the catch, right? The catch is that sequential composition is not precise. Not only is it not precise, it's very much not precise. Because in quantum programs, we use interference intrinsically to do most of the interesting computation, including nonlinear classical computation, right? So if we're going to actually generate interesting nonlinear relations, we need some way of dealing with this interference, which our classical domain can't deal with by nature, right? Because we don't have interference in the classical domain. So our approach to this is to treat circuits precisely, which we then use to extract precise transition relations for those circuit blocks. And the way we do this is by using something called a symbolic path integral. So symbolic path integrals basically take symbolic classical transition and add symbolic amplitudes on top of that, right, to give us an exact representation of a quantum computation. And the thing is, if we have a symbolic path integral, we can immediately get a polynomial transition ideal straight from that over-approximates the classical semantics. Now, at face value, that polynomial transition ideal won't be any more precise than the compositional thing, right? But the key is, with the symbolic path integral, we have this theory of rewriting. We can use the theory of rewriting these path integrals to actually eliminate some of these infeasible transitions to give us a more precise abstraction transition ideal. OK, just blazing ahead here. So we implemented this in the quantum circuit optimizer Feynman on quantum programming language OpenQASM 3. And we found that it does actually find really interesting non-trivial optimizations of these quantum programs, right? But the key thing, because we don't have too many of these hybrid programs, key thing is that this allows easy and deep integration of the phase folding optimization in compilers for these hybrid workflows, right? And the other interesting thing that came out of this is that we found that using the relational approach and extending the relational approach to include nonlinear relations, we actually got a strictly stronger phase folding approach than existing approaches, right? Because now we're including nonlinear relations, where existing approaches only include linear relations, right? So that allowed us to, just for strict circuits, actually find some interesting optimizations that previous automated tools hadn't been able to discover yet. Right? So this is one particular instance that was known to be an optimization by hand, but no automated circuit optimizer had been able to find it, because it requires nonlinear classical reasoning. OK, and I'm out of time. So the main thing that I just wanted to say as a takeaway for this is that you can think of quantum data flow really as classical data flowing in superposition. When you think of quantum data in this way, right, now you can reuse all of these classical techniques to do interesting analysis of quantum programs. OK, and I'll leave it at that.
So we have time for a couple questions. If anyone. Oh, right there.
Hello. Yeah. Hi. Do you have the polynomial? Do you have a degree, a maximum degree that you need to consider, or the degree is unbounded in general?
So we actually did experiments in two particular cases with degrees bounded at 2 and unbounded degrees. Because obviously, if we consider unbounded degrees, then things kind of blow up a little bit. We found that most of the optimizations occur at degree 2. That's because of the use of the Toffoli gate, which is a degree 2 classical transformation, right? So that was kind of our thinking, and that did turn out to be the case. But in some particular cases, we do actually need those higher degree relations. Like there was one circuit that does floating point renormalization, and you can do the optimization using integer reasoning, right? But to do the integer reasoning at the bit level, we need higher degree polynomial relations. So yeah, extending to unbounded allowed us to get that optimization.
Oh,
Yeah, so I know you were mentioning the abstraction process. So how exactly does the partial order, or what's the ordering defined in the abstraction?
So the ordering is just subset ordering, right? So like if we're talking about the affine subspace domain, right?
Yeah.
The ordering is just
subspace inclusion?
Yeah.
Okay, got it. Thank you.
Okay, we have time for one last question. Yep. And can we get the remote speaker set up, or?
Thank you. I'm really excited about what this means for being able to do optimizations across, hybrid programs. I'm just curious about a specific thing. So you said that you had the chart with loop invariants. Are those inferred, or these are things that you identify as loop invariants?
Then they're inferred loop invariants.
Yeah. Okay, let's thank Matthew again. And our next speaker is going to be remote. I hope. What's up? Oh, hey, could the remote speaker, if they're online, yes, can you please start? Yes, sorry. So,
stop sharing and then reshare, because this is something that I've seen was not working.
Okay. Could you stop sharing and then start and reshare your screen? That might resolve the issue. Right? Oh, good, good. Ah, very good. Okay, so our next speaker is going to be Ying-T, who's going to be talking about, again, automating equational proofs. And with that, take it away. We can't hear you right now. Are you muted, unmuted? Okay. Do you guys have a... Jinxed it. I don't really want to switch presenters because I don't want to get off schedule. So I hate to get off schedule, but I think we might move on to the next talk temporarily, and we'll try and get this talk working right after this, okay? So In that case, our next speaker is actually going to be Andrea, who's going to be talking about doing type-based. Oh yeah, if you put on the mic. So he's going to be talking about doing type-based resource estimation. And before he gets started, I'll note that Andrea is on the job market this year. So if you're looking to hire someone, you should definitely talk to him.
Can you hear me? Okay. So let's get this up. Okay. All right. So thank you for the introduction. I would like to start this talk with 2 questions. First question is, why do we care about quantum computing at all? And in my opinion, the answer to that question is that we do because quantum computing is really nice. In the sense that over the past 30 years, this field of research has shown us time and again how quantum algorithms can vastly outperform classical ones, sometimes even achieving to tackle classical intractable problems. And contributions in this sense really span dozens of algorithms with far-reaching applications in many different fields. Which brings us to the second question. If this is the case, then where are these far-reaching applications? Like, why don't we see them out there in the wild, in the real world? And the answer to that question is that quantum computing is also really, really hard, in the sense that building, operating, and maintaining quantum hardware is extremely expensive and technically challenging, and therefore the quantum computers that we have are very limited in terms of computational resources and also in terms of reliability. Which means that although we do have really nice quantum algorithms, it's usually extremely hard to run them on the quantum computers that we have. Which means that we must be very careful with the resource requirements of algorithms, and we need to be very careful when we analyze the resource requirements of these algorithms. And this need is what motivates ultimately this work. But before we get into that, a little bit of basics. I'm sure you all now know what a quantum circuit is after Matthew's talk. But for the sake of this talk, you can just think of quantum circuits as diagrams such as this one. If we want to reason about the resource requirements of the computations associated to a quantum circuit, we must look at the circuit size. And there are varying notions of circuit size. For example, the width of a circuit is defined as the maximum number of wires that are active at any point in the circuit and corresponds to basically the memory requirements of the corresponding quantum computation. Whereas the gate count of the circuit is defined on the number of gates in the circuit and represents a sort of runtime requirement of the computation. A more refined metric in this sense is depth, which is defined as the maximum number of gates encountered on any path from an input to an output of the circuit, and this represents a sort of parallel runtime requirement of the quantum computation. And I told you that quantum computers are relatively limited, and this means that they can only run circuits up to a relatively small size. But what's more interesting is that different architectures, that is, different technologies, actually vary wildly in terms of what which of these metrics is the actual bottleneck of the computation. So for example, you could have an architecture that runs a very wide circuit because it has many qubits, but cannot run a deep computation because its qubits are not reliable. Or you could have an architecture that implements error correction, and so it has a few very robust logical qubits and can run deep circuits, but not wide circuits. And of course, there are tools to estimate, to check the size of a circuit and to optimize the size of a circuit. But let's look at how this translates to the analysis of quantum algorithms. Because of course, like a quantum algorithm is not implemented by a single circuit, but rather by a family of circuits, which contains a different circuit for every possible input size to the algorithm. The problem here is that as the input size grows, so does the size of the circuit that represents the applicable computation. And this means that if you're given a quantum architecture, there comes a point where the input size becomes too big for the quantum architecture to run, to actually execute the corresponding circuit. And what we want to know when we're talking about the resource requirements of a quantum algorithm is we want to know where this cutoff point is exactly. So what is the maximum input size that we can run the algorithm on a given architecture? Of course, this is a problem that cannot be solved by looking at the individual circuit. We must look at the circuit family as a whole, and specifically at what generates the circuit family, which usually is a program written in a domain-specific language called the Quantum Circuit Description Language, or QCDL, which runs on a classical computer and produces different members of the circuit family depending on some classical parameters, such as, for example, the size of the input. And so what we want really is static analysis techniques that can take as input one of these programs and output upper bounds on the size of the circuits that these programs build. These upper bounds should be parametric, for example, on the size of the input, and they should also be concrete, so as to have close control over the resources. And our contribution is precisely in this sense, and our target language is the Kuiper language. So Kuiper is a higher-order functional quantum QCDL embedded in Haskell. It is designed with the goal of being scalable and practical, which means that it is designed with the intent in mind of implementing real-world quantum algorithms, which translate to circuits that are very big and very complex. The theory of Kuiper is usually studied through a family of languages that are based on the Proto-Kuiper calculus, which in a nutshell is a linear effectual lambda calculus with bespoke constructs to describe and manipulate circuits. What I mean by that is that a Proto-Kuiper term is always meant to be executed together with a quantum circuit, which provides the wires that the term can manipulate and append gates to. These wires are identified by special values which we call wire labels, or just labels. And the circuit built by a term M can be boxed and turned into a piece of data that we call a boxed circuit. And this is relevant because we can copy boxed circuits and reuse them in describing more complex circuits by applying these boxed circuits to the underlying circuit. So for example, a term such as this one applies the Hadamard gate represented by a boxed circuit H to a qubit labeled Q0. And if we have a circuit with one such qubit labeled Q0, we can run this configuration, and what apply H to Q0 does is emit a Hadamard gate to the circuit and evaluate it to the output wire label of the gate. Okay, so this was Proto-Kuiper in a nutshell. Proto-Kuiper's type system is really nice in that it guarantees many safety guarantees at compile time, but it does pretty much nothing in terms of resource analysis. So what we did was we extended the Proto-Kuiper type system with type refinements and effects to obtain a calculus that we call the resource-aware Proto-Kuiper, or Proto-Kuiper array. And what we did was we annotated the types of Proto-Kuiper with quantitative information regarding the size of the circuits built by programs of that type. So for example, we have the type of functions that build circuits of size at most I in the spirit of types and effects. We have the type for circuits of size at most I, and we have dependent sized lists. And all of these annotations are what we call index terms, come from a language of what we call index terms or indices. And they are basically arithmetic expressions on natural numbers and index variables, which are a special kind of variable that types and effects are allowed to depend on. Speaking of effects, Proto-Kuiper array revolves around a typing judgment of this form, which tells us that for all assignments of the natural numbers to the index variables in theta, under typing context gamma and label context q, term M as type A and builds a circuit of size at most I. Here q is what we call a label context and contains the wire labels that are made available by the underlying circuit. But more importantly, theta is a set of index variables which represent the classical parameters of the circuit building process, such as, for example, the input size of the circuit. And because I can depend on these variables, the effect annotation is allowed to depend on these variables, we effectively have that I represents a concrete parametric upper bound on the size of the circuits described by M, which is exactly what we wanted. So this is nice. You will notice that I used a very vague notion of size in these couple slides, and this is because our type system is actually agnostic to the actual size metric being used for analysis, being analyzed. Specifically, we want to be as generic as possible, so we endow the language of indices with what we call abstract resource operators, which basically represent the evolution of an unknown size metric under certain conditions. For example, I star j, which we pronounce usually I sequence j, describes the size of a circuit obtained by composing in sequence a circuit of size I and a circuit of size j. And this is an example of how we use these abstract operators to carry out a generic resource analysis. In a let expression, if M builds a circuit of size I and N builds a circuit of size j, then the overall let expression builds a circuit of size I parallel the size of the wires that are not consumed by M sequence j. Okay, and this generic approach allows us to, depending on how we interpret these abstract operators, allows us to analyze various metrics, for example, width and gate count. It doesn't allow us, however, to deal with depth for the simple reason that, on one hand, gate count and width are what we call global size metrics. That is, they are properties of circuits as a whole, and thus are very amenable to a compositional treatment with effects. On the other hand, depth is not a global metric. It is what we call a local metric, in the sense that depth is a property of individual wires at the fundamental level, as we already saw in the introduction. Of course, we can take the maximum of the depth of all the wires in a circuit to obtain the depth of the overall circuit, but this is just an aggregation of a property that is fundamentally a property of wires. So how do we deal with this? What we do is we extend our system of type refinements, and we annotate wire types with information regarding the local metrics associated to the corresponding wire. So for example, if we are talking about depth, qubit 0 would be the type of a qubit wire at depth 0. So for example, a freshly initialized qubit. If we take a single qubit gate, it might have a type like this one, which tells us that it takes as input a qubit at depth d and outputs a qubit at depth d plus 1 for any d. And you can see how this use of index variables allows us to express local metrics in a functional fashion. And this is something that is pervasive in our work. In particular, the final form of our tapping judgment includes a context containing the index variables that we use to encode the functions in the judgments. And what we do is we annotate the wire types in Q, which we are the wire labels that come from the underlying circuit and which become the input of the circuit built by M. We annotate the wire types in Q with variables in Xi, representing the unknown local metric associated to the inputs of the circuit built by M. And we annotate the wire types in A, which represent the outputs of the circuit built by M, with indices built from the same variables. So we can achieve a form of dependency and express local metrics as a function. Of course, we want to be as generic as possible with local metrics also, which is why we extend the collection of abstract resource operators with a new operator for local metrics. And these symbols, these abstract operators, are interpreted by what we call a resource metric interpretation, or an RMI. An RMI becomes a parameter of the type derivation, and different RMIs define different instances of protoQuiper array, which derive different judgments and thus are capable of analyzing different kinds of resources, different notions of circuit size. Talking about correctness, the actual size of a circuit is given to us via a function defined recursively on the structure of circuits, which we call a recursive circuit metric, or RCM. And we say that the prototype array instance is correct with respect to an underlying RCM mu, when basically the upper bounds that it derives for a term m are sound over approximations of the actual size of the circuit built by m as dictated by mu. And the general result that we have in this sense is that the prototype array instance obtained from an RMI T is correct with respect to an RCM mu if T is coherent with mu. What does this mean? We say, sorry, that an RMI T is coherent with an RCM mu when a small set of inequalities hold that basically tell us that T over approximates the recursive definition of mu. Such as, for example, the actual size of the empty circuit is over approximated by the null size abstract index, and so on and so forth. Unfortunately, I do not have enough time to go into details about coherence. Besides the theoretical results, we also have a Haskell implementation of prototype arrays type system in the form of an open source static analysis tool named Cura. Cura takes as input a program written in a variant of prototyper. In this case, in this example, this is an implementation. This program implements the QFT, or quantum Fourier transform algorithm, as a function. And Cura gives us a type for this function, which tells us something about the size of the circuits it builds. This type is very, in this case, we asked Cura for a width and depth analysis. And what Cura tells us through this type is that for every input size n, this function takes as input a list of n qubits, builds a circuit of width at most n, and returns n qubits. And as for depth, the same type tells us that for every input depth d, this function takes as input n qubits at depth d, and returns n qubits, where the ith qubit is at depth d plus n plus I. And if you run if you do a couple of computations with pen and paper, you'll find that these bounds are not only sound in this case, but they're also exact for the QFT. And Cura is capable of deriving these bounds automatically, or mostly automatically, thanks to SMT solvers. In conclusion, our contribution is a type and effect system that can derive concrete parametric upper bounds on the size of the circuits built by a QCDL program, a proof of total correctness for this type system, and an implementation in the form of the Cura tool. What remains to be done is find a better, come up with a denotational semantics for prototype array. A denotational semantics is something that all prototype variants, mostly all prototype variants have, and we still don't have one. And also developing a more extensive benchmark of the Cura tool. So implementing more algorithms and verifying more algorithms with our tool. Before I conclude, I want to briefly mention that I very recently finished my PhD and I'm currently on the job market. So I really look forward to discussing potential work opportunities with fellow researchers here at POPL in the following days. And with this, I'm done. Thank you so much for your attention.
So we have time for one or two quick questions. Raise your hand right there. I have one. The SMT solver can derive bounds mostly automatically. What was the mostly caveat there?
The mostly is that we still rely on some annotations in the source code, especially for like local metrics. Global metrics, we can mostly defer everything to the SMT solver, but with the local metrics, we have to like keep track of some things in the code. So we haven't encountered yet instances where the SMT solver hangs, but this still relies on quite some annotations in the code. Not really, because there are like different ways of expressing the same resource requirements, and so there isn't a notion of principal type.
How do you choose which alternative in your logical relations?
In some occasions, they are like equivalent, so it doesn't matter. Otherwise, I do not really have an answer for this, because I haven't looked into what kind of type is actually returned when there isn't a principal type.
So actually, I think we're running a little bit behind because of our technical snafus. So let's thank Andrea again. I see our final speaker. Once again, I'm happy to reintroduce Ying T, who's going to be talking about automating equational proofs in Dirac notation. So please go right ahead.
Okay, this time I hope you hear me clearly. I thought I would lose this chance, but they fixed the issue in the last minute. That was dramatic. Okay, our work is about Dirac notation. And what is Dirac notation? Here are some examples. In 1939, Paul Dirac proposed his notation to express linear algebra formulae in a compact and convenient way. And we know that quantum states live in Hilbert spaces. So Dirac notation soon become the working language for quantum mechanics, quantum computation, and quantum information. And we use Bra and Kit to represent the vectors in Hilbert space and the dual space. We also use the scalar and operator, linear operator in our notation. For example, here the first expression represents the superposition state for a qubit system. And in general, the language itself is quite free and casual, sometimes ambiguous. And the valid transformation depends on the reasoning of its semantics. And moreover, we can give the matrix interpretation to its meaning. For example, the basis 0 and basis 1 of the qubit system can be represented by column vectors. And the results of inner product and outer product are represented by this and calculated in the matrix way. So here is an example of a quantum information lemma that is expressed as an equation. Assume we have two subsystems. They are in the Hilbert space of HV, and they are in the maximally entangled state. And assume we have an operator M, which is in HV. And the fact is, if you apply M on the first subsystem, the result is equivalent to applying the transpose of M on the second subsystem, no matter how the two subsystems are separated. So how do we prove it? By equational reasoning. The left-hand side is transformed in this way. We unfold the definition and push terms into the sum. This is by the bilinearity of the product. And we rearrange the tensor and composition. Sometimes we need to insert the identity operator of identity matrix into the formula. So the right-hand side will be transformed into the same syntax using similar approach, so the equivalence is acknowledged. Such reasonings appear everywhere. For example, in theorem prover, you have to manually prove this. For example, in the verification of quantum programs. So an important question is, can we automate this procedure? So here is an analogy for the problem. The structure of the equivalence for Dirac notation is like a labyrinth. And finding the proof for the equivalence is like finding the solution trace. And our work aims to provide the guidance, or in another word, the understanding of the structure that can help to select the direction during proof. So the first step is to formally define what is Dirac notation. We work in universal algebra framework where we have a signature of function symbols, and each function symbols have their fixed arity. And we have a set of variables and basic concepts like substitution of variable and pattern matching are also defined. So here is our core language for Dirac notation. Core language means we don't consider a big operator sum that appears as in early examples. And we have 5 sorts. They are bases, scalars, ket, bra, and operator. Take ket as an example. It can be variable x or zero symbol or the basis cat, or it can be the adjoint of a bra, or it can be scaling, addition, operator cat, multiplication, or tensor product. One thing to note is it is a little bit different from the original casual direct notation, where we don't have separated symbols for different kinds of terms. Here we separate the symbols, meaning we have 3 multiplications. This is done deliberately because we want to disambiguate them, and we also relate our syntax with the common understanding of direct notation. So this is done by denotational semantics, which maps the syntax to its interpretation as set serial objects. For example, when we want to calculate the semantics of the tensor product of cats, we first calculate the semantics of K1 and K2 separately, and they are the vectors in the Hilbert space in the mathematical sense. And the whole denotational semantics is taken as the tensor product of the 2 vectors. So we have the formal language, and this is how we humans understand and reason about equivalence. But computer cannot do it in this way. What we need is a formal proof system. So we further on explore how we use equational logic to do this. Equational logic defines an equational relation that is compatible with substitution and term construction. And the substitution and construction are the elements or the language in universal algebra. And this is essentially the common sense, the formalization of the common sense of equivalence in algebra. And we have more axioms besides this in this logic to describe the language, the behavior of the language. These are the axioms for linear space, and we have more for other structures like tensor product and inner product. One thing to note is the denotational semantics can be considered as a model for the logic system, meaning if we prove that 2 terms are equivalent in using the logic, then their interpretation should be equivalent. This is what we want because we want to. Our goal is to prove the equivalence according to their interpretations. But the other way does not hold. So there are some equivalence that holds in denotational semantics, but they cannot be captured by these axioms. So the logic itself cannot be complete. And we can also consider how hard is a problem. We can provide 2 ways of thinking. One is if you have the concrete basis, meaning that you can do the decomposition, then you can reduce the equivalence problem of direct notation to the series of reals, which is decidable. And essentially, this is transforming the variables into their matrix interpretation and do the calculation. But this is impractical because the complexity depends on the dimension of Hilbert space, which can be quite high. And this is exactly why quantum computation cannot be efficiently simulated using classical computers. And another observation is because we have the set of equations as axioms. So if 2 terms are provable equivalent, then the writing trace can always be searched out. But again, this is not practical. So what is a practical way? We use the term writing as our technique. In general, term writing decides equivalence by normalizing the 2 terms and see whether the results have the same syntax. The normalization procedure is powered by matching and replacing using a set of rules. We use the special variant of term writing called AC term writing. And AC means we have associativity and commutativity in our axioms, and they cannot be decided using right rule, and many of them are obtained by assigning directions to the axioms. There are some intuition and heuristics in doing this. For example, we will prefer to transform linear algebra computation into scalar ones. And sometimes when we encounter tensor product structure during inner product, then we will want to decompose the tensor product. So what about the property of our algorithm? One is soundness, but soundness is obvious because all the writing rules comes from axioms. So the writing always preserve equivalence. And completeness is not that easy. So it can be obtained if you can prove that the writing system is confluent and termination. These are the two main technical contribution of our work. Termination means the writing of a term will have the result that cannot be written anymore. And confluence means if you start using the same term, then all the possible writing traits will result in the same syntax. So we want to prove this, at least for our core language. But this is not easy because we have a term writing system with more than 150 rules, and manually checking them is time-consuming and sometimes impossible. But the good news is we have the local confluence of AC term writing system is decidable. And termination of term writing system, it is not decidable, but we are fortunate. So we use two tools. One is called the SimWrite tool. And to be honest, term writing does not have a very thriving community for now. And this is the only tool that we find can do AC term writing. It is built 20 years ago. But anyway, it works. And it checked that all the critical pairs, meaning all the pair of writings that will diverge, will finally converge. So our system is confluent. And for termination, we use another famous tool called approve. And termination is confirmed by encoding our term writing system into it. So that's the story. We have a core language which covers most of the symbols in debug notation, and it is sound and complete. But there is one thing. We don't have big operator. So we further on extend the language with some. There are the syntax for set and syntax for the summation, and we also have the semantical explanation. But the problem is decidability of big operator is not well studied. So our rules are rather heuristic. They are not completeness guarantee, but instead they work very well in practice. So our work conclude in the implementation called Reactive. It is written in Mathematica. The reason of choice is we want the language to internally support term writing so that we can write it easily. And also we want there to be a computer algebra system for scalars that can deal with symbols like exponential or trigonometric functions. So Mathematica is the choice. And here is the raw code encoding the earlier example. You can see the first line, it defines the context. We have the operator n with the corresponding type. And the second line defines the maximally entangled state. The third line encodes the equation, and Reactive checks the equivalence automatically and confirms the result. That's how it works. We evaluate the implementation on an example benchmark. The examples comes from different sources. They come from the textbook and the CoQ project, which is a foundational formalization, CoQ formalization for quantum quantum computation. And we also take some equations as examples from a suitable recent paper. In general, the result is it works well, and the language is expressive, and most encoded examples are solved. To name some applications, the theory and implementation can serve as the solver for theorem provers. For example, if you want to prove equivalence in Cork, then you don't need to manually write all the proof scripts. Or it can serve as a solver, the backend for the verification tools of quantum programs, because you will need to check whether the assertions or the states are equivalent, and they are all written in direct notation. And to give you some sense, these are the examples we can do. And for example, and particularly here, the last one, we have the define symbol, meaning here tr trace means the trace of operator. It is not within our original language, but it can be defined using the functions in Mathematica and the direct notation we proposed. So the tool can also do some sort of abstract reasoning. And to conclude, you may also be interested in how the work is developed. We write down the rules, and again, there are 150 in total, and many comes from intuition. And we check the termination and confluence using the tool. Thank God we have the tool. And we do the implementation and check the example test suits. Usually there will be counterexamples, for example, critical pairs that will destroy the confluence, or there will be failed tests. So we have to look into the counterexamples and make modification to the rules. So the procedure just repeats again and again. And my feeling is the work is like manufacturing a processor. The only difference is we are using formal method and writing rules instead of hardware circuits. I think this is not a sustainable way. I mean, in the future, we will for sure require the decision procedure for a more complicated language. And by then, managing the rules manually is not a promising way. So can we do it in a better way? Can we find the guidance in the labyrinth in a better way? I think this is the next important question. And my talk ends here. Please tell me your comments or questions. Thank you for your attention.
Okay, we are running a bit behind, but we do have time for 1 or 2 questions if we have any.
Hi, yeah, thanks for the talk. You said that this system can be used in Coq to have, do automatic proofs rather than having to write them yourself. Is that something that you have actually existing with integration between the tool and like producing some sort of certificate?
Well, that's a very promoting topic, but it's the next story. So in theory, it's possible because the structure of turn writing is very simple, and you can implement it in Coq, or you can extract the writing trace and let Coq check the writing trace. These are possible.
Okay, yeah. So do you envision like essentially re-implementing the whole system inside Coq, or is there some way to get fast plus certificate?
Yeah, I'm working on a next generation of DirectDeck, which is written in C++ and emphasize on speed and efficiency. And also, we did some exploration to integrate it in Coq, but the difficulty is if you want high efficiency, then you have to do some optimization, and you have to let Coq also check this optimization. This can be quite hard.
Okay, we have one last question from Matthew.
Hi, thanks for the talk, really interesting. So I had a question about your syntax. Your syntax had a lot of different cases. It resembled like a concrete syntax instead of an abstract syntax. I imagine this is so that you can actually kind of finely tune the direction of the rewrite rules. But have you thought about kind of a simplified syntax, like either an abstract syntax and kind of giving the rules on the abstract syntax, or maybe like a typed syntax that kind of simplifies this thing a little bit?
Exactly. But here is the trade-off. So we stick with the concrete syntax because we want to use the naive term writing. Because naive term writing can be checked by the tools, and we get the nice properties. If you can also design the abstract syntax, but then you will need the type system and type checker, and there are some term writing rule will invoke the type checker, so the whole system will not be machine checkable. That's a problem.
Right. Yeah. Yeah. Okay. Thanks. Perfect.
Great. Let's thank the speaker one last time. So it's time for a break, but before everyone leaves, let's thank the student volunteers for getting the technical difficulties worked out. Very much appreciate it. Good. Thanks.
And I'll turn it over to him for talking about quantitative probabilistic relational Hoare logic.
Thank you for the introduction. This is a joint work with Martin Avanzini, Gilles Barthes, and Benjamin Grégoire. The main contribution of this work is a logic for reasoning about pairs of probabilistic programs in a quantitative way, which means that we are interested in finding upper bounds to mean values, probability values, and similarity metrics of pairs of programs that are written in imperative language with recursion and sampling instructions. While designing this logic, we had two goals. The first one was to be relatively complete for some classes of properties, and the other goal was to have a logic which is easy to use, so the user could compose proofs nicely, and we wanted the user to reason about probabilities only when it was strictly necessary. The applications of these logics are to cryptography, differential privacy, and machine learning, but I won't be able to cover any of these applications. You can find details in the paper. Before going to the main focus, I'd like to briefly introduce what you need to know about probabilistic programs for understanding this talk. So in this talk, we can take as probabilistic programs that are written in an ordinary imperative language, but that feature this instruction that sets the value of x to one of those between the braces with uniform probability. So for instance, if we have this program C that executes the command setting x to the uniform probability between 0 and 1, and we execute it on an initial state, we will have two transitions, one to a state where x is set to 1, one to a state where x is set to 0, with the same probability. If we add another sampling, the probability of the next sampling are independent of the probability of the first one, so we reach a total of 4 possible final states, each one with an associated probability of 1/4. So the output of the computation of a probabilistic program in this setting is a set of possible final states associated to a probability. On these distributions of final states, we are maybe interested in computing the expected value of some real valued function. So in this case, we may be interested in studying what is the expectation after the execution of the function x plus y. This value is given by the sum for all the possible 4 states of these terms, where the blue part is evaluation of the function on the term, and the green part is the probability of reaching that state, which in turn is the product of the probability of each transition. Expectations for us are important because our logic is meant to find upper bound to expected values. The reason why we decided to define this logic is to improve the expressiveness of another logic, which is PRHL, the probabilistic relational Hoare logics. In this logic, in PRHL, we have judgments that are relational because they talk about 2 programs at a time, and that are qualitative because the pre and the post conditions are 2 relations that can either be satisfied by a pair of states or not. The interpretation of this judgment is basically saying that if the initial states are related by R, there is a way to relate with S the final distributions. And the way we establish this is by requiring a coupling between the output of the program C and between the output distribution of the program D, whose support is included in S. So this means that if we sample from the coupling, we always obtain pairs that are in relation with S. But besides the definition of the interpretation of this logic, what is important to understand at this point of the presentation is that PRHL has been mechanized and has been widely used for proving correctness and security of many cryptographic applications. So you find those applications corresponding to the pink dots in the plot. But PRHL has 2 limitations. The first one is that the kind of judgments it has are not really suitable for reasoning about quantities. So for instance, if we want to reason about differential privacy, in PRHL we cannot do it nicely because we have pre and post conditions that are relations. To overcome these limitations, some logics have then been introduced in order to allow this kind of more quantitative reasoning. And another limitation of PRHL is that there are some judgments in PRHL that are valid but cannot be proven. Therefore, PRHL is incomplete. If we want to see an example of such a judgment, we can think of program equivalence. So in PRHL, we can express nicely program equivalence. For instance, the judgment that you see on top left of the screen says that the 2 programs evaluate on states that are related by R produces 2 equal final distributions, and these are characterizations. However, in some cases, using the PRHL proof system, this is something that we cannot show nicely. So for instance, if we take these two programs, we can observe that these two programs are computing the same distribution, which is the uniform distribution between 0, 1, and 2. The program on the left performs rejection sampling because it enters the loop, and then it exits the loop only when x is either 0, 1, or 2, while the program on the right samples from this distribution just by definition of the semantics of the sampling instruction. So for these two programs, we have this judgment, which says that on any initial input, the two programs compute the same output distribution. However, this is a judgment that we cannot show in PRHL. Therefore, we introduced our logic in order to achieve some form of completeness, in order to extend the expressibility of PRHL. We did it by changing the type of pre- and post-conditions that we are using in our judgments. So instead of having two relations, as for PRHL, now we are using two functions that are mapping a pair of states to a positive real. With this choice, we can now talk about quantitative properties. We also talk about expectation, because our semantics is basically expressing the fact that the value of the precondition evaluated on the two initial states is an upper bound to the expectation of the postcondition evaluated on some coupling mu of the two final distributions. And with this kind of judgment, we can already express some interesting quantitative property, such as, I went to the end, sorry. Such as, for instance, we can talk about expected values. This judgment is basically saying that when we execute x, which is sampling between the uniform distribution of 0 and 1, and when we execute that program that is setting y equal to 1, the expected value of x plus y will be upper bounded by 3/2. And this corresponds basically to the interpretation of the validity of this judgment. Another thing that we can do is reasoning about probabilities, because we can encode probabilistic events by means of this encoding to 0, 1 valued functions that are 1 only if the event holds and that are 0 otherwise. Then it turns out that the expected value of such an encoding is equal to the probability of the event that we are encoding. Therefore, the judgment that you see is basically saying that 1/2 is an upper bound that when we execute these two programs, the sum of x and y will be equal to 2. And another thing that we can do with our judgments is to put in the pre and in the post condition some logical variables that are variables that do not belong to the program variables of the two programs and that are universally quantified. This turns our judgments into schemas because they will be valid for every choice of f in this case. And for instance, the judgment that you see is telling us that the term on the left is an upper bound to the expectation of f of x plus y when we execute these two programs. And the nice thing about having logical variables is that the judgment is then valid for every choice that we do for the logical variables. And this extends the expressivity. Then we have a proof system for deriving our judgment. It is a horse-style proof system. I won't bother you with all the rules, just some key properties. The first one is compositionality. So we have this sequencing rule that it is composing these two proofs about two programs into a proof of the composition. And what I'd like you to observe is that if you're familiar with standard Hoare logic, you will notice that the pattern of the pre and the post condition is the same as in standard Hoare logic, which means that we can compose our judgments that are non-standard with some ease. And another thing that I'd like you to observe is that the sequencing rule, for instance, is not reasoning about probabilities. Indeed, the only rule that reasons about probabilities in our calculus is that for sampling. And what it does is also not so involved, because the goal of the rule is that of finding an upper bound to the expectation of phi. So the rule basically computes these expectations of phi for a given coupling of the two distributions and puts this value of the expectation in the precondition. Another property of this sampling rule is that it's comparing two structurally identical programs. So on one side we have a sampling, and on the other side we have another sampling. And if we only had this kind of rules, we could compare just programs that are structurally identical, and this would limit a bit the expressiveness of our calculus. So to overcome this limitation, we added also some rules that are one-sided, because they can be used to reason about one program by leaving the other unchanged. So in particular, we can use these rules on top of a sequencing rule, where on one side we add a skip, because as I wrote in the bottom of the slide, we're always allowed to add a skip before or after a program in our calculus. And then by applying one of these rules, we reason about one program, leaving the other unchanged. And this allows us to reason about two programs that are not structurally identical. Just before I go ahead, by looking to these rules, you will see, if you're familiar with standard Hoare logic, that they are quite similar to the corresponding rule in standard Hoare logic. Then our proof system has two key properties. The first one is soundness, which means that every judgment that we can prove is actually valid. And for the opposite direction, we have some form of relative completeness. Indeed, we were able to show that if C and D terminate with probability 1, every judgment that has this precise shape that you see, if it is valid, it is also provable. But what are we asking by asking that the judgment has precisely this shape? Well, we are asking that the postcondition is given as the sum of two functions, a function phi and a function psi, whose value depends only on the output of C and on the output of D, respectively. And this is the only condition that we need on the kind of judgment for provability. However, this theorem, stated like this, doesn't tell us much about what we can do with our logic. And you may wonder what we can actually do with this logic. So I have some corollaries I can discuss with you. The first one, which is, in my opinion, one of the most interesting, is that our logic is complete, it's relatively complete, for showing PRHL validity. Indeed, the judgment in PRHL that you see in the bottom of the slide is equivalent to the judgment of ERHL, our logic, that you see in the table. Therefore, the validity of one of those judgments corresponds to the validity of the other. And in addition, I'd like you to observe that the judgment that I put in the picture falls in the set of judgments that our logic is complete for. Therefore, let me rephrase this reasoning. If there is some property that is hold and that can be expressed by means of a PRHL judgment, well, our logic is complete for proving that property. As a corollary, we have completeness for program equivalence, because as we saw before, program equivalence can be expressed as a judgment in PRHL. And then we have also some other results that are more towards the quantitative side. So for instance, we have completeness for total variation. Total variation is a quantitative metric that expresses how much two distributions are different. And if some delta is an upper bound to the total variation of the outputs of the two programs, the judgment that you see in the table is valid, and vice versa. And you see that the encoding is, again, one of those encoding that our logic is complete for, which means that we can always find also the precise value of the total variation with our logics. And another thing that we can do is measuring the epsilon delta coefficient of epsilon delta differential privacy, because what you see in the bottom of the slide is the definition of epsilon delta differential privacy. A program is epsilon delta differential privacy when epsilon and delta somehow bound the amount of information that the program reveals on its input. And the statement that you see in the slide, that is precisely the definition of epsilon delta differential privacy, is equivalent to the one that you see in the table. Therefore, we have this one-to-one equivalence. And again, the encoding is some encoding that we are complete for. And finally, we're able to find a characterization also of Kantorovich distances. So Kantorovich distances are a generalization of distances between pairs of states to distances between distributions of states, defined as you see below. And when the big delta is the distance between the two states is bounded by h, the statement that you see below corresponds to the validity of the judgment in the picture, where f is a logical variable, so where f is universally quantified. And again, that judgment is one of those judgments that our logic is complete for. So in conclusion, I was a bit early. I hope I convinced you that our logic is a quantitative relational problem logic that is expressive and composes nicely. And we saw that it is sound and complete for some interesting properties, like the validity of PRHL judgments and measuring the epsilon delta differential privacy coefficient. And in the paper, you will find other contributions, like rules for reasoning about recursion, loops, and adversary that are a feature of PRHL that I didn't discuss, as well as some case studies. So thank you for your attention. I'm happy to take questions.
Hi, thanks for the talk. I have two quick questions. First, could you go back to the previous slide?
Yes.
So in the encoding of PRHL validity, where does S come from?
I didn't say it. S is a logical variable, so S is quantified universally. So we must be able to prove this for every possible choice of S, and the type of S is a set of states. Okay. This encoding, if I can comment a bit of it, comes out from the quantitative extension of the Strassens theorem, and therefore, from that, we get the validity of the corresponding judgment.
Okay, great, thanks. The second is, so I know from like weakest pre-expectation calculus that the upper lower bounds often come from the treatment of non-determinism. So if there's a non-determinism in the program, they either take infimum or supremum to correspond to demonic or angelic choice, and so that's why they often bound. In your case, well, is there non-determinism, and if not, where does the imprecision come from?
We don't have non-determinism, and the imprecision, I think it comes from the presence of the while. When you reason about a while, you need to find an upper bound to an invariant which is an upper bound, and there comes the imprecision. Otherwise, our rules are almost only doing weakest reasoning, so they are precisely
okay, great.
What
Thank
to
you.
expect. Thank you.
Great, we have time for a handful of other questions back there.
For PRHL validity, a more intuitive encoding to me was to have, in the post condition, have the intersection of the two sets you have, two events you have. Is this intuition correct?
Can you repeat?
Also, here in the post expectation, you have tau1 in S and tau plus tau2 not in TS.
Yes.
Is there also an intuitive encoding where you have tau1 in S and intersect with tau2 in TS?
I think there are multiple encoding of PRHL. Maybe the most intuitive one is the one where in the pre and in the post, you take the complement of the relations.
Okay. Okay. I guess my question is that are you encoding this way because for this to be complete, you need to sum up two things, each only using one of the program, and the other encoding not be complete.
Yes, that's the point. With this encoding, we can get easily completeness. Otherwise, we would need a rule that we have to switch from one encoding to the others.
Okay. Thanks.
Thank you for the question.
Okay, we probably have time for one more quick question. Right here.
Right there, I think.
Great.
Yeah, so I was wondering if you've thought about applications to quantum programs, right? Because this does seem like it's the kind of thing that would lead exactly into looking at kind of expectation values of observables, and I know that's
I'm not working on it personally, but I know for sure that Gilles Barthes is working on it. So
I figured that's why I was asking.
So you can ask him this question. Okay.
Thanks.
Thank you.
Okay, great. Well, let's thank our speaker. And Philip, would you like to? And our next speaker is Philip Hazelwater from Aarhus University, and he is going to be talking about approximate relational reasoning in higher order. No, I'm sorry. Yes, this is right. Approximate relational reasoning for higher order probabilistic programs.
All right, thank you. Can you hear me? Yes.
Okay, so I will talk about a proxys. A proxys is a relational higher order separation logic for reasoning about approximate program refinements. And the approximate here refers to the error probability that two programs compute different results. Approximate program equivalence has been studied for first-order languages, like we saw in the previous talk, but a proxys is the first logic that can handle a full randomized ML-like language. So that means that our programmers can allocate local states, use higher order functions, and abstract types, full recursion, and so on. So we achieve this by representing the error probability as a first-class separation logic resource. And as a consequence, a proxys supports powerful features of higher order separation logic, like invariants or user-definable ghost state. The error resources are manipulated through their own set of rules and don't interfere with the rest of the system otherwise. On top of the program logic of a proxys, we also developed a logical relation for proving program approximation and contextual equivalence. Thanks to the expressiveness of a proxys, we were able to verify some classic results from cryptography, as well as the correctness of probabilistic algorithms that were beyond the scope of previous logics. And the whole work has also been mechanized in ROC and Iris. So let's look at an example of something that we verified in a proxys. We can prove the security of an encryption scheme. Intuitively, we want to say that messages encrypted by the encrypt function look random to any adversary A who doesn't know the secret key K. We can phrase this security property as a game where the adversary is interacting either with the real implementation of encryption or with a function that returns random ciphertexts that don't actually depend on the message. This random function serves as a probabilistic specification for encryption. Because the adversary doesn't know if it is interacting with the implementation or the specification, we call these functions oracles. In the game, the adversary gets to pick up to Q messages to encrypt. The goal of the adversary is then to analyze the ciphertext that the oracle produces. A should return the Boolean true if it believes that it's interacting with the implementation, and false for the specification. What we want to prove in a proxys is that no program A can tell the implementation and the specification apart with error and with probability higher than epsilon. So what's the mathematical meaning of this intuition that encryption looks random? We want to show that the probability that the adversary can distinguish the two is some small error epsilon, which depends on the number of messages Q. And so the strength of our approach here is that we have an expressive language where we can define all of the different parts of that equation natively. So we don't need any ad hoc syntactic restrictions on the syntax of the adversary or special treatments of the oracles. We model the adversary as a higher order function that takes an oracle as input and produces a Boolean to indicate its guess. In a proxys, this equivalence up to epsilon is expressed as a program refinement. So under the assumption that we can make up to epsilon errors, A with the encryption refines A with the random ciphertexts. And both of the programs return the same Boolean B. So in particular, they both have the same probability of evaluating to true. I'll now explain the different components of this judgment and how the proof works. So building on some of our previous work, we extend separation logic with a new proposition for error probabilities. Intuitively, this up to epsilon turnstile P means that the proposition P holds up to probabilistic error epsilon. And because errors behave like a standard resource, we can be flexible about when we spend these credits. For example, we could store some credits in a data structure invariant and perform some amortized error reasoning. There are two essential laws for error credits. If we own the sum of two error credits, epsilon 1 and epsilon 2, then we can split it into separate resources. And if we have an error budget of 1, then we can derive anything, since any proposition holds up to error 1. I'll show you in a second why it's sometimes useful to prove a judgment with error 1. So the error budget can increase when we execute random samplings. For example, we can prove that with error 1/2, the flip instruction on the left here evaluates to true. There are two cases to consider. We allocate 0 credits to the branch where we get true, and we get error credit 1 in the false branch, which means that we can conclude that false is equal to true by the second law of error credits. This is sound because each case has probability 1/2, and the weighted sum of the credits adds up to 1/2, which is what we started out with. Okay, so now that we understand how error credits work, let's go back to the refinement that we want to show. So we will reason about the adversary and the oracle separately. To show that the encryption refines the specification, we will use our refinement logic. And because the results of encryption are not quite uniformly distributed, this is where we will use our error credits. We want to prove this approximate equivalence for all adversaries, so we have to assume that we don't a priori know the code of A. So how can we prove anything about it? Well, so the answer is that instead of reasoning about the concrete code, we will use the type of A to derive that we get the same results from both programs. So let's focus for a second on the proof about the oracles. The refinement satisfies the invariant that the counter for both oracles is set to the same value I, and that we have a certain number of error credits stored for future calls. Initially, we allocate the counters with I set to 0, and the number of credits is q squared over 2n. When we establish that the invariant holds at the beginning of our proof, we transfer ownership of all of the initial error credits into the invariant. And then after that, every invocation of the oracle preserves the invariant by incrementing I and consuming some error credits. So to increment the counters, we just use standard separation logic rules for references. And so this is a strength of the approach because we don't have to do anything probabilistic here. It's just the normal rule that you would expect. To split the error credits, we use the first law of error credits. And then we can spend some credits to reestablish the invariant for I plus 1. And the part of the credits that we split out is used to guarantee that the encryption samples a fresh nonce n that was not sampled before. So since the encryption function doesn't actually keep track of the nonces that we sampled, this freshness only holds up to some error. In Aproxys, we have a sampling rule for this kind of reasoning. So there are two key features to this approximate sampling rule. First, it allows us to assume that both of the random samplings, the left-hand side and the right-hand side, they both return the same n. And secondly, we get that n is fresh. So it's not in the list of previously of nonces that we've seen previously. Let's focus on that part. So we can visualize this rule by drawing the execution tree of rand n. Let's assume, for example, that the values 1 and 3 have not been sampled before, and 2 and n, on the other hand, they already occur in the list of nonces, so they're not fresh. But the sampling rule that distributes the error, we can assign credit 1 to the sampling outcomes that are not fresh. And with 1 error credit, we can prove any post condition. So in particular, we can show that 2 and n are fresh nonces. So to summarize, we have I sampling outcomes, which needs error credit 1. Each of these outcomes occurs with probability 1 over n. Since we had exactly I over n error credits to start, we can ignore all of the bad sampling outcomes. This is the core of the refinement argument about the oracles. Now let's focus on the adversary. So the code of A is unknown. So if we want to prove anything about it, we wouldn't even know which rules to apply. So instead, what we'll do is that we will leverage a language property, namely that all well-typed programs respect abstraction. So this language property can be captured by a logical relation. And this logical relation, in turn, is defined in terms of the refinement judgment that I've been showing you so far. What the logical relation allows us to do is that we can derive a relational judgment for A purely from its type signature. So what have we achieved so far? So we can derive approximate refinements for randomized ML programs. We can reason about unknown code using our logical relation. And by the adequacy of a proxys, that gives us the probabilistic bound that proves the security of our encryption scheme. So I do want to briefly mention another a different cool feature of our logical relation. So we can also use it to prove exact program refinements by showing that the error probabilities tend to 0 in the limit. So for this example, we'll assume that we can only sample powers of 2. So for instance, maybe your source of randomness only gives you a stream of bits, right? But the goal is that we want to sample from a uniform distribution over 3 elements. So the RS program on the left samples k out of 4 and returns k if it is smaller than 4 and starts over if k is 4. And what we want to prove is that the RS program should refine or be equivalent to just the program that's just ran 3 on the right-hand side. So we can, again, draw the state space of RS and of ran 3. So in one iteration of RS, we have probability 1/4 to get a result between 1 and 3. And we have probability 1/4 to recurse and start over. And as we iterate this process, we add a little bit of probability mass to the first 3 outcomes. But in the last case, we just start over. So the probability of getting a sequence of 4s goes down exponentially. If we keep iterating this, the probability of getting 1 to 3 converges to 1/3, just as we wanted. And the probability of getting an infinite sequence of 4s goes to 0. So this might appear simple if you do a sort of a pen and paper proof, but as we just saw in the previous talk, this kind of argument is actually challenging to formalize in a program logic. And our approach allows us to internalize this style of limiting argument in a proxys via the logical relation. So to prove this refinement in a proxys, the logical relation lets us assume that we have some amount of abstract small error credits, but we do get to assume that it's non-zero. On the first iteration of RS, we allocate all of the error credit to the last branch. Because this happens with probability 1/4, it's sound to assume that we get 4 times as many error credits in that branch. When we go back to the initial state, we now have 4 times as many error credits as we started with. But we also know that for any epsilon, there is a number of iterations n such that 4 to the n times epsilon is going to be larger than 1. So we could simply iterate this process n times, and we would end up with error 1. And so again, by the second law of error credits, that's going to allow us to conclude that the refinement actually holds exactly. So we have internalized this style of limiting arguments in the logical relation and applied it to this particular rejection sampler, but also to much more sophisticated examples. So in conclusion, we built an approximate logic for higher order probabilistic programs. We defined a typed logical relation for reasoning about unknown code and internalizing limiting arguments. The whole development is mechanized. And so if you want to find out more, then please go read the paper. So in particular, in the paper, we have quite a few more case studies. So in the previous talk, we saw mention of the PRF-PRP switching lemma. That's something that we formalized as well. So there are some more arguments from the security side, from the cryptography side. But we also managed to mechanize some proofs about efficient sampling strategies for data structures. So in particular, B trees, which are used in databases and file systems, we can just represent them as pointer manipulating programs in our language. And we can prove that efficient rejection samplers for B trees are equivalent to a naive implementation of sampling from B trees. And that again uses the limiting argument and the logical relation that we demonstrated. And also in the paper, we have the semantic model that we construct for this logic. I think that might also be interest of someone working on first-order logics, because we have some new coupling laws in there for combining approximate couplings. Right. Thank you.
So we have a few minutes for some questions. Right back over there.
Thank you for the great talk. Could you go back to the slide of the rejection sampler? Can you explain formally what would go wrong here if we, or where the argument would break down if we did too many recursive calls to the rejection sampler so that we would get some finite probability of non-termination?
Some finite probability of?
Right, so suppose we did 6 recursive calls in the else branch. Where would the argument break down?
I'm sorry, I'm struggling to hear you acoustically.
I'm wondering if, that's better.
Awesome, thank you.
I'm wondering where the argument would break down if we made too many recursive calls in the else branch.
Right. So the argument doesn't break down. The argument works because you can't keep taking the else branch. So this is a logic that allows you that in the limit, the two programs are equivalent, which is if you keep drawing out that the tree on the bottom right here, it keeps going, but there's the branch that keeps sampling 4 has measure 0. So the probability of actually looping is 0. So that's why it's sound to perform this kind of limiting argument.
So what if we did, let's say, RS, semicolon, RS, semicolon, RS, and that 6 times, let's say? Wouldn't there then be some positive probability of looping? Or maybe I'm confused.
So for any finite number of unfoldings, the error is going to be non-zero. That's true. But since the operational semantics of the language will just keep unfolding these recursive calls, right? Yeah. Yeah, you're still going to eventually get a good result, right? With probability 1. Maybe we can take this offline. I think this is.
Thank you very much. Very nice talk.
So we maybe have time for one more quick question.
So I was wondering what is the repercussion of assuming typing for the adversary, and if you can further constrain the adversary to have some limited computational power, for example, it being polynomial.
Yeah, excellent question, thank you. So the assumptions about the typing are very minor in my opinion, because we're not giving it any fancy type, we're just saying it treats the argument, the function that we supply it with, as a black box, which is exactly what a cryptographer would tell you. extending this to a computationally bounded adversary, yeah, work in progress. Ask me again in a year.
Okay, great. Well, that's our time. So let's thank our speaker, and we will pass to the next person. And our next speaker is Jack Lielkock from University of Oxford, and he's going to be talking about compositional imprecise probability.
All right, cool. Oh, cool. Do I have to just hold it like this? Yeah.
Here, try this one.
All right, cool. Thank you. All right, nice. Okay, great. All right, cool. Yep, hi everyone. So yep, I'm Jack. This is work done by myself and Sam Staten. So yeah. Oh, cool. So yeah, basically to give you the context of where we'll be during this talk. So yeah, we're in probabilistic programming, but in particular for world modeling. So here our programs have some kind of commands to talk about uncertainty, and we use them to basically have programs which describe like world phenomena, and then we can automatically perform inference in order to get some kind of statistical analysis. So yeah, this has seen successes in, say, like with the UK in order to predict the spread of COVID. So what we did in particular with probabilistic programming is we wanted to give a fully compositional account which combines both Bernoulli uncertainty with Knightian uncertainty. So what Bernoulli uncertainty is basically regular probabilistic uncertainty, where say you have two outcomes, say we have an urn with a red and a blue ball, and yeah, we pick a ball basically probabilistically from the urn, so we have equal odds chance between a red ball happening and a blue ball happening. Knightian uncertainty is a bit more of an epistemic uncertainty, where we can think of this as the urn on the right, where we know there's red and blue balls in the urn. We know that the urn is non-empty, but we have no idea what the distribution of balls or how many balls are in the urn. So we'll pick a ball out of it, and all we can really talk about is what the possible set of outcomes will be. We have no prior on what the distribution is. So the way we usually talk about this is via non-determinism. And then these two types of uncertainty together is what we call imprecise probability. So the way we actually did this in a programming language is we named the Knightian choices and managed this using graded monads. And we showed two things about the model we produced, is that they actually give a refined bound on the uncertainty compared to previous models. And it's basically the furthest we could push this kind of idea, because if we tried to push it any further, something will break, which I'll make clearer later. Yeah, so to give credit where credit is due, there's been a lot of interest, wider interest in probability and non-determinism and combinations of them. Some of them are here, but we are currently looking at the setting of imprecise probability, which is new and independent from all this. So yeah, let's first start off with to get an idea, a feel of what imprecise probability actually is. So if we take the Bayesian account of probability, we can think of basically a probability being the fair bet you would make given some kind of distribution or some kind of uncertainty about a world model. So we can think of this as, say, if we have three outputs from a system, say red, green, and blue, we can think of this as basically being a point in the simplex between these three outputs, which in this case is a triangle. So we can think of the point basically at red, so in this top left triangle here, the very top point, that basically represents 100% chance of red happening. The point halfway between green and blue, so P here, that basically represents equal odds chance between green and blue and impossibility of red. And then the point Q represents equal odd chance of everything. Imprecise probability is where we're now saying, okay, some of our probability or some of our uncertainty is no longer probabilistic. We don't know the distribution of it anymore. We just know the set of possible outcomes. And so instead of having a single fair bet that we could make, we have a set of possible bets that we could make based on the situation. It turns out this set will be convex in order to just be consistent with a regular world model, which goes down into the philosophy. But the way we could think of this, in the triangle in the top right here, is if we say, okay, in one situation, there's a 100% chance of red happening, and in another situation, there is an equal odd chance between green and blue happening. But then there is some kind of Knightian uncertainty which dictates between one of these two situations happening. And then this will be represented by the convex set between this point of 100% red happening and the point between equal odds green and blue, because the Knightian uncertainty is saying, okay, we don't know what the distribution is, so it could be anywhere between certainty of red, or certainty of the first situation, certainty of the second situation, or some kind of distribution between them. So yeah, imprecise probability has had a number of applications in statistics, economics, and engineering. It's recently popped up quite a bit in machine learning, which prompted us to look at it, say in conformal prediction and AI alignment. But yeah, to get into the guts of it, our first language for imprecise probability, we're going to start with just a few simple constructs. So we're going to have if then else statements, so basically a way to condition on Booleans and continue with one program if it's true and one program if it's false. We're going to have let bindings, so we run a program T, bind the value to X, and then continue with U, which may or may not reference X. And then we're going to have two commands which induce the two uncertainties that we have. So we have Bernoulli, which we can think of as a fair Bernoulli trial. So we have an urn with a red ball and a blue ball in it. And basically, when we call this command, we're going to randomly sample from the urn. If it's red, we return true. If it's blue, we return false. And then we have a command knight, which we can think of as given an urn on the right, which we know is not empty and has red and blue balls, but we have no idea what the distribution is. So when we call this command, we pick a ball out. If it's red, we return true. If it's blue, we return false. But yeah, we don't know what the distribution on this is. And we get a new urn each time we recall this command, so there's no way to figure out or to slowly converge on what the actual distribution of the urns are. So yeah, how can we actually start talking about imprecise probabilities with this language? So to just give you a few examples or a feel for what we'll be talking about, yeah, we can start with a very simple program in this language, which is the top left one here, where we sample from a Bernoulli, or we do a Bernoulli choice, and then based on that choice, we return green or blue. So because there's no Knightian uncertainty, we just have a single point. There's no convex sets to worry about. And yeah, it is exactly the point, which is halfway between green and blue because it's a fair trial. If we increase complexity a little bit, so now we have one Knightian choice, and based on what the result of the Bernoulli choice is, we will condition on the Knightian choice and return red, green, or blue in this second logic here, in the top right, sorry. The way we can interpret this program as this actual convex set or imprecise probability is we can look at the two extreme values of the Knightian choice. So on one hand, X is going to be certainly true. And if this is the case, it doesn't matter what Z is, we will get red with 100% certainty. On the other hand, X is certainly false. And in this case, we'll get 50% chance green and 50% chance blue based on the Bernoulli trial. And because X can be any convex set of these extreme, distributions, we get the convex set between this certainty of red and equal odds green and blue. And then we can increase complexity a little bit more, where we have the same program, but now we choose two Knightian choices, and the only difference is we condition on a different Knightian choice in the second branch. And now, because the Knightian choices are decoupled, we can look at the four extreme values given by the permutations of certainty of true attached to X, certainty of false attached to X, certainty of true attached to Y, certainty of false attached to Y. And these give us the four extreme values in this diamond here. And that's, generates, these convex sets of probabilities. So what kind of properties do we actually want our language to hold? Well, given we're talking about languages which actually model probabilistic programs for real-world modeling, first of all, we want our language to be commutative. So if we have two programs T and U, which don't reference each other, return values which are attached to X and Y, and then we continue with V, which does some logic on X and Y, then it shouldn't matter if we run T first or if we run U first. So we can think of this as if we pull one ball out of an urn and then a second ball out of an urn without looking at either one, and then we look at them and do some logic, it should be the same as pulling the other ball out first and then that ball, because they're completely independent. And same with, this is also the case with affinity. So if we pull a ball out of an urn, don't look at it, toss it away, and then continue with some program logic, well, basically it should be the same as never having pulled that ball out of the urn in the first place, because nothing in our program mattered on it. So this allows us to talk about our programs as data flow diagrams, which is very common in probabilistic programming for modeling. And the second piece of desirability we want is standard equational reasoning about if-then-else statements. So basically, if we do the same let binding in both branches of an if statement, because we're talking about world modeling, so only one of these branches will be executed, we should be able to hoist this let statement out of the if statement, so long as it doesn't interact with B, because in both cases, the let statement will only be executed once. So what ends up being the actual problem? Well, one model that actually supports convex power sets of distributions is the convex power set monad. But the problem is it's actually not commutative. So we have this function down the bottom here, which we pass a Bernoulli value to x and a Knightian value to y. It actually matters which Bernoulli or Knightian value we sample first in the interpretation in the convex power set monad, and so it doesn't actually give us a reasonable account of imprecise probability. And in fact, no semantic model works, because we have this paradoxical program here where we basically sample two Knightian choices on each branch. And the paradox arises in whether they're the same Knightian choice or whether they're different Knightian choices. And in each interpretation, we get the left or right convex power set here. And basically the Desiro data basically says there's no way we can actually distinguish these. So there's no way to actually talk about imprecise probabilities in this semantic model. So the way we actually solve this is just to attach a label to the Knightian choices. So in the first case here, we label both Knightian choices with the same name, and therefore we get the convex power set where they're both correlated. And in the second one, we attach them with different names, and because now they're independent choices, we get the wider non-deterministic set of outcomes here. And we can no longer equate these two programs because we can no longer hoist the let statement out of the second program. So how do we give an actual semantic model for this? Well, the way we do this is via graded monads. So we take a reader monad transformer of the finite distributions monad. So you can think of the set A here as being the set of Knightian choices, or the set of names for the Knightian choices we have. So 2 to the A is the set of all possible non-deterministic branches we can take. And so this reader monad is saying, OK, you give me one possible non-deterministic branch, and I'll give you the distribution, the resulting distribution based on that non-deterministic branch that you took. So we generalize this 2 to the A to arbitrary sets B, so talk about non-deterministic branches. And then we can actually recover the convex power set from this model by basically looking at the image of this function and taking the convex hull. And this is actually given to us by a canonical Khan extension. So it's a very natural way to go from one model to the other. So yeah, this is the, I guess, semi-formal definition. And this is how we actually interpret the Bernoulli commands and Knightian commands in our model. I won't go into the details here, but I guess the main point is that it was critical to use graded monads here, because they give a way to semantically talk about error usage. And this meant we could actually keep track of which non-deterministic branches were assigned to, which non-deterministic branches were used in which parts of the program. And so when we composed programs together, either functionally or monoidally, we actually have a way to talk about how we bring these non-deterministic branches. And so this is given to us by the graded monad multiplication. All right, so what did we actually show about this model? Well, the first one is that we actually get improved uncertainty bounds when we model within our framework. So we had this mapping where we take our monad and we take the image, and it gives us a convex power set. In fact, this actually induces an Oplax functor between the two Kleisli categories of the two monads. And what this means is basically if we compose programs in our framework and then map them across to the convex power set framework, we actually get refined bounds as opposed to when we map each program across individually and compose them together in that framework. And that's basically to do with we're keeping track of the non-deterministic branches, so we can do a little more about, we can talk, we have a little more refinement about how we use them. And secondly, it turns out there's kind of more stuff in our model than as opposed to the convex power set model, in that when we take this kind of mapping across, a few things get mapped to the same value. So we have more stuff in our model, which maybe we don't want because, it's strictly larger than what we actually want to talk about. So can we quotient it any further? And the answer turns out to be no, because we'll either break the connection with imprecise probability or we'll compromise the compositional structure. Yeah, so to just give a conclusion, what we did was use named Knightian choices, which we managed via graded monads to give a fully compositional account of Bernoulli uncertainty with Knightian uncertainty in a programming language. We showed this gave refined bound on uncertainty in our models. And it was also the best possible way, the best we could do with this methodology. For future work, we're interested in looking at iteration and infinite dimensional structures, because currently we only support finitely generated convex power sets, but we'd like to support, larger ones. And looking at function spaces, and of course, implementation and inference with these, with non-determinism is a non-trivial problem, which we want to look at. Thank you.
Okay, so we have time for several questions. First over here in the second row. And is our last speaker in the room by the chance? Okay, great.
Mm-hmm. Well, because that's what you would expect when you're talking about world modeling, right? If you do two different, if you do two different samples which are independent from each other, then what I guess your language says versus what you're trying to model is different. Mm-hmm. Right. I mean, there's lots of, I guess, intuitions you could have between combinations of probability and non-determinism. So maybe the one you're talking about is a bit more like, the actual distributivity law, where you kind of have a more like demonic non-determinism, where it has all possible scenarios enumerated when you take that, when you distribute one over the other. But here we're, I guess, less interested in that law, because we want to be able to talk about, these things commuting with each other, because when you plug, when you want to like plug these programs together, you don't want to have to worry about which program comes first and these sorts of things. You just want composition.
Okay, great. We probably have time for one more question.
Mm-hmm.
There are others who use interval value probability. So my question is whether the semantics that you have given, whether it is sensitive to how you represent imprecision.
Well, when you talk about interval valued probability, that is also convex sets, right?
Yes, but what about ranges of probabilities?
Right, so we built our work based off, there is a big community of imprecise probability people who, there's like a book by Wally, which is seen as the Bible, and it has a very, the nice thing about this type of imprecise probability is there's a lot of different kind of angles you can view from it, and one is these convex power sets, but the other is these I guess it's more like philosophical views as coherent kind of bets you could make. We haven't really looked at, I guess, well, it depends what the other imprecise models are. So can't tell you whether it will work in those systems until, I know what the systems are. So, as in, yes, we give the semantics in convex sets, so
Okay, great. Thanks. We're right at time. Maybe we can continue these stimulating conversations afterwards. But let's thank our speaker and well done. Last speaker. And finally, we have Satif VR from MPI SWS, and he will be talking about sound and complete proof rules for probabilistic termination. Yes.
All right. Okay. So, hi, everyone. I'm Satya, and I'm here to talk about sound and complete proof rules for probabilistic termination. This is joint work with my advisor, Rupak, and we're both affiliated with the Max Planck Institute for Software Systems. All right? And before I get into the meat of our work, let me start with the mention of our program model. Well, we include the basic imperative programming constructs like while loops, if conditions, and so on. And we allow our program variables to take on rational numbers. In addition, we allow for finitely branching probabilistic and non-deterministic choice. This means we can have single instructions where you can increment or decrement a program variable x with equal probability, or you can non-deterministically either increment x, decrement x, or increment y. All right? However, we do not allow for random sampling or for unbounded non-deterministic branching. This means we cannot uniformly sample a number between 0 and 1 and assign it to a program variable x. Similarly, we cannot non-deterministically assign any natural number to a program variable x either. All right? So in this model, we're interested in the termination question. And what is termination in a probabilistic sense? Well, we studied two notions of termination. The first is what we call the qualitative notion of termination, where we ask whether the probability with which a program terminates is 1. And the second notion is the quantitative notion, where we ask for proofs of lower bounds and upper bounds on the probability of termination. Now, note the asterisks over there. That's because of non-determinism. Because we resolve non-determinism demonically, the probability of termination of a program is interpreted to be the smallest possible probability across all possible resolutions of non-determinism. All right? So our program model is obviously Turing complete, meaning that these questions are undecidable. And the way we plan on answering these questions is to use proof rules for termination. And what are these proof rules? Well, proof rules are simply a collection of formal conditions written in a formal program logic that, if met by an input program, implies its termination. How they work is that they kind of encode the certificates of the program's termination as conditions in a formal program logic. The classical example of a proof rule for termination would be the ranking functions. These are just functions that decrease by at least 1 at each execution step. You can kind of see that in this particular very simple while loop over here, the simple function that outputs x is a ranking function. All right? To properly capture probabilistic termination, we want these proof rules to be both sound and complete. Soundness means that if we find certificates matching the proof rule for a particular input program, that means that that program definitely does terminate, right? And completeness means that if you have a program that definitely terminates, then there will exist some certificates that match the proof rule for the program, right? So we want both soundness and completeness. And for non-probabilistic programs, the ranking functions that I mentioned earlier are already sound and complete for termination. Unfortunately, for probabilistic programs, the current state of literature is that we don't really have completeness. For qualitative termination, the closest thing we have is completeness in this case of finite state programs. This is work by Annabel McIver and Carol Morgan in 2005. And in fact, the closest thing we have, the state of the art, by again, Annabelle McIver and a few others at POPL 2018, was believed to be incomplete, even by the authors of that rule itself, right? Even though there are no counterexamples, they still believe the rule was incomplete. Things aren't great for quantitative termination either. For the case of lower bounds, we had a proposed proof rule by Chatterjee and a few others in 2022. This rule was proposed and proved to be complete, but unfortunately, this completeness proof has a small bug. We have shown a small counterexample to their completeness in our paper. So at the end of it all, we don't really have a complete proof rule for probabilistic termination, and our contributions is to give that. We show the first sound and relatively complete proof rules for probabilistic termination. Now, I've been talking about soundness and completeness. Well, what is relative completeness? Well, in addition to completeness, we also show that for all terminating programs, there will exist certificates of termination that can be encoded in the program logic, meaning that they can be expressed in the program logic as well. All right? This is important. This is necessary to fully reduce the problem of termination to a problem of program logic validity. Right? Now, again, there's an asterisk over here. That's because we've shown, honestly, to even our surprise, that the prior state-of-the-art rule was also complete. Okay. So I don't have a lot of time in this talk. So I'm going to focus in the rest of the talk on qualitative termination. All right? I will derive our proof rule for qualitative termination, which was also called almost sure termination. That's what AST stands for. And I will derive our proof rule for qualitative termination by analyzing these 3 example programs. The first is a simple coin flipper. It repeatedly flips a coin until the coin lands tails. The second and third are random walkers that navigate the integer number line. The middle one is unbiased. The last one is biased away from the origin. Both these random walkers stop when they hit the origin. All right? And how I will derive our proof rule is, well, I'll start with an earlier proof rule, and I'll try to kind of fix it so that it can actually apply for all 3 of these programs. All right? And what is this earlier proof rule? Well, this is the proof rule by Annabelle McIver and Carol Morgan that I mentioned earlier that was, well, complete for finite state systems, right? This is called the variant rule, and it generalizes the ranking functions that I talked about earlier as well. How does that work? Well, you take the ranking functions, they must decrease at each execution step. The variant functions must also decrease at each execution step with a minimum probability amount. And because it must decrease at each execution step with just a minimum probability, there is a probability with which it can increase. So let's just bound the variant rule to make it sound. All right? Let me be a bit more precise. In addition to finding the function itself, you also have to find an epsilon so that u will decrease with probability at least epsilon at each execution step. This is the variant rule, and you can see its operation in the coin flipper. As long as you have just the function u that is 1 when the coin lands heads and 0 when the coin lands tails, this function will decrease by 1 with probability at least half at each step. All right, and this function over here certifies the termination of the coin flipper. Now, the variant rule is unfortunately incomplete. And this is something that is witnessed by the symmetric one-dimensional random walker, which is almost surely terminating, but cannot be shown so by just using the variant rule. And this is because you can kind of see that the candidate variant rule, if you were to try to build a variant for this, you would notice that the candidate variant rule that you had filled, which just outputs the value of x at the program state, is unbounded. And this is just because, well, the integer number line is unbounded. It will reduce with probability at least half at each step, but it is unbounded, so we can't use the variant rule here. But can we get away with this? Can we get away with an unbounded variant? Well, no. because unbounded variants are unsound. And this is, again, witnessed by the asymmetric random walker, for which this unbounded variant would actually imply AST, because it would still reduce, but with probability at least 1/3 at each execution step. All right, so what do we have? We have a variant rule. That's pretty nice. It generalizes an earlier rule that we used to use for non-probabilistic systems, but it seems to be unbounded for certain programs. And the difference seems to lie somewhere between the asymmetric and symmetric random walker. All right, so let's go a little deeper into this difference. This is just a symmetric random walker in a more picturesque way. And let's be a bit creative. Let's put a wall to the right of the random walker. And how the wall works is that when the walker hits the wall, he stops moving, he stops walking. So yeah, in this case, if you remember the earlier candidate variant that we had, it's now bounded by the wall, by the position of the wall. Therefore, this walled-off random walker is definitely terminating. This is not incredibly surprising news, but this is something that we do have. But a cooler thing is that the probability with which you hit the wall grows smaller the further away the wall is. In fact, for any possible epsilon, there is a position for the wall so that the probability with which you actually reach the wall is less than epsilon. This is a very nice observation, and the even cooler part is that this is not true for the asymmetric random walker. We have seemed to have found a property that holds for a symmetric terminating random walker, but not for the asymmetric one. This is very nice. But this is not even the coolest part. The even cooler part is that this generalizes for all terminating programs. It turns out that you can take a terminating program, order its states. And if you manage to do this, you can always show that the probability of reaching states far to the right of where you currently are is very small. So from here, if you start from the state in the middle, which is like indexed n, there will exist an m. For an epsilon, there will exist an m, so that the probability of reaching states indexed m, m+1, m+2, and so on, is less than epsilon. And because of this, because this is an indexing, and the rest of the states must be indexed values less than m, meaning there are finitely many of them, meaning that any variant that you could possibly create for them will automatically just be bounded. All right? And this is something that is true, and this observation is something that we use heavily in our completeness proof. All right? How do we use this observation, though? Well, we use supermartingales to witness this observation. And these are simply functions that, in expectation, do not increase at each execution step. All right? For the symmetric random walker, the simple function that just outputs x at each execution, at each state, is a supermartingale, because in expectation, the next step, you are going to increase x with probability half and decrease x with the same probability. So in expectation, you don't actually change the value of v after a step. So this is a supermartingale. All right? And how do supermartingales work? Well, it turns out that the probability with which a program's execution increases a supermartingale from a low value L to a high value H is bounded above by L by H under certain conditions that we actually incorporate into a proof rule. All right? To make it a bit clearer, in the case of the walled-off random walker, the supermartingale kind of shows that the probability with which you reach the wall is less than n by m, meaning that for an epsilon, all you have to do is find a value of m so that n by m is less than epsilon. And since m is not bounded, we can definitely always do that. Now, we have not really used a supermartingale to show termination. We've only been using the variance to show termination, right? The cool part here is that the variant is bounded when the supermartingale is bounded. If you have a collection of states within which a supermartingale is bounded, the variant will also be bounded. And it is possible to show that because of all the observations we've seen so far, you cannot really come up with a super martingale and a variant such that this particular property will hold for the asymmetric random walker. Okay? So let's summarize. What do we know? We know that with the bounded variant, we have almost sure termination. We know that with unbounded variants, we don't really have anything. But if we have a unbounded variant that is bounded when an associated super martingale is bounded, we seem to have almost sure termination. And this third point is exactly our proof rule for almost sure termination. We want a variant, which is both of these, and a super martingale, which is this, such that both the variant and the super martingale are 0 only at terminal states. These 2 points just mean, this point just means V is a super martingale, this means U is a variant, such that when the super martingale is bounded, if it's bounded by a real number R, then the variant must be bounded by some number HR, right? In a collection of states where the super martingale is bounded, the variant will also be bounded. Now, for a technical reason, we can kind of move this epsilon a bit down, and we'll get a sound and complete proof rule for almost sure termination. All right? And to summarize our work, in our paper, we have shown a new sound and complete proof rule for almost sure termination, and we've shown that the earlier state-of-the-art proof rule by Annabelle McIver and a few others is also complete using our completeness arguments. We also have a couple of sound and complete proof rules for quantitative termination that also use super martingales and variants. And for future work, we're going to try to include random sampling in the program model and still see if we can maintain completeness. All right? Thank you for listening. I'm happy to take questions.
Great, so we have time for 2 questions. Right here.
Can you say something about the expected running time?
Not with these proof rules. I mean, for the expected running time, they do exist existing sound and complete proof rules for them. I think they just use what is called a ranking super martingale, which is just a super martingale that in expectation reduces by a minimum amount in each step.
Okay, thanks.
Couple. Let's go to the right there, right in front.
Great talk. I was wondering the rule from the previous paper that you showed is complete. Can you tell us what differences there are? Is it stronger assumptions than yours?
It's actually quite interesting. So in our paper we have a super martingale and a variant, right? Over there in their paper they have a function that is both a super martingale and a variant at the same time. So it is a super martingale that in addition must decrease by a minimum amount at each step. And as you keep going down, you have to keep decreasing by like larger and larger amounts.
Thanks for the talk. So you say you don't support sampling, but I mean with just the choice operator and while loops, you can already
You can approximate it, but you don't. Yeah, but you can approximate sampling to an arbitrary precision, but I don't know if you can actually.
Yeah, I don't know if you can do anything, but you can certainly encode some discrete distributions like geometric distributions.
Of course.
So do you have any intuition of what the challenges would be to actually have a sampling? Well, also, were you talking about discrete sampling only, and then if
no, I mean continuous sampling.
Okay, so then, so then of course there's challenges. Thank
it's
you.
just maybe let's talk about this offline. I mean, there is I can talk about this for a long time.
Sure.
Okay, great. We maybe have time for one more quick question if we do. If not, no.
Your probability must be a constant, or I can have 1 over x in this example?
You can have 1 over x. It's okay. Not sure it'll be complete though. terminating though.
All right, great. Well, that wraps up the end of our session. Let's thank our final speaker.
for attending this session. And then we will have our first speaker, Marco, for presenting the paper, Universal Composability is Robust Compilation. Marco, please go ahead.
Hello. Thanks for having me. So let's start with a couple disclaimers. I tried to move the content of the slides a bit up. So apologies for the online viewers if this is not completely filling your screen. Hopefully everybody can see the salient bits of the talk. But the real disclaimer for this talk is, well, this is joint work with a bunch of people, Robert Kuhneman, Riyad Wabi, and Ethan Cecchetti. And well, they are all cryptographers, and I'm not. And this work actually brings together two different topics. One, universal composability that comes from the crypto field, and one, robust compilation that comes from programming language security. And the disclaimer really is, none of my cryptographer colleagues are in the room, so if there are any hard cryptography questions, I'll have to take them offline because they haven't turned me into a cryptographer just yet. So let's start with a magic trick. So how many people here, raise your hand if you know about universal composability, if you've heard about it? Good. Now, keep your hands raised if you have done a universal composability proof. Excellent. Keep your hands raised if you have read any universal composability proof. Good. And keep your hands raised if you believe any universal composability proof that you read. Now, spoiler, there are 0 plus epsilon hands raised, and the magic succeeded. And ideally, I would have just written 0, but my cryptographer's colleague taught me to put epsilons here and there. So there could have been some of us that actually believe in UC proofs. But that actually brings me into the motivation for this work, because you see, universal composability is really neat, but it's also really hard to believe, okay? And when we started this work 6 years ago, one of the things we wanted to do is, well, we should be able to provide better assurances for UC proofs, and hopefully by the end of this talk, I'll be able to have convinced at least some of you that there are ways to perform more believable UC proofs. So in order to get there, let's start with a bit of background. Again, this work brings together two fields. Let's start with universal composability. Now, UC is the gold standard for proving security of protocols under concurrent composition. Cryptographic protocols, like the big ones like TLS, they are built from smaller building blocks. And in order to prove security of the bigger protocols, UC tells you that it's sufficient to prove security in UC terms of the smaller building blocks, and by the composition theorem, then you get security of the bigger protocol that you have. And it's great, so this notion is really great because it then overcomes the problem of when do protocols compose, what is happening concurrently, and what could break their security properties when interoperating concurrently with arbitrary other pieces of code. Now, UC exists in many flavors. It was originally devised in the beginning of the 2000s, and recently, close to the 2019s, there were a few other versions like ILC and IUC. And in the work that we've done, we have provided axioms that formalize the essence of UC. Some of the formal details are more closely geared towards the newer notions like SOCI and IUC, but in essence, we believe that our axioms capture any flavor of universal composability. Now, what does universal composability talk about? Well, one of the first things is protocols, pi in orange, which are, well, the concrete protocols that are supposed to run. And in this very poor quality screenshot, there's the 1-bit commitment protocol where essentially two parties agree on a committed bit by sharing some form of hash. Now, the second element that is key to UC is functionalities. If you will, they are abstract specifications for protocols, and they use abstract notions in order to provide the same guarantees of their protocol counterparts. And functionalities are identified with a green F. Now, both of these elements, pi's and f's, they interact with attackers. There are concrete attackers A's and simulators S that you could see as sort of corrupting parties that try to break the security of the protocol, essentially, at hand. And all of these, pi's, f's, A's, and S's, are all interactive Turing machines. And these interactive Turing machines, indeed, they run the orange ones are called the real world elements, and the green ones are the ideal world elements. And whenever they run in the interact, their interaction is witnessed by an environment Z, which is sort of an objective witness. And the goal of universal composability is for the environment not to be able to distinguish whether it is observing the real world or whether it is observing the ideal world. If that succeeds, then the protocol you see realizes the functionality, and you're good. Now, visually, we could see UC in these sort of like two triangles that capture the interactions of the real and the ideal world as witnessed by the environment. And formally, you know, universal composability, we can state it as the protocol UC realizes a functionality if for all attackers there exists a simulator, such as for all environments, the real world execution is indistinguishable, the double squig arrow, from the ideal world execution. And the thing that I'm telling you so far is called perfect UC, because right now we are in a Dolev-Yao attacker model, and everything you find in the paper is with respect to perfect UC, so perfect crypto, which we know is not actually sufficient. But if you wonder, there are computational notions of universal composability, and everything I'm going to tell you about, and everything that you will read in this paper, hopefully, if you read it, is actually, we've done it for computational UC as well, which was a work that was presented last summer. So this is one of the cases in which the follow-up work has been accepted before the original work, which is funky, if you guess. But just know that whatever you're going to hear also holds for computational UC, okay? So that's as much as I want to go into UC details. Let me tell you a bit more about robust compilation then, the other half of the picture. Now, robust compilation is a work that we've done a few years ago, 2019, and we were looking for criteria that would tell us when are compilers secure in terms of what kind of security properties do they preserve. And research, we came up with a bunch of definitions, which we organized in this lattice. And each element in this lattice has a formal statement that you can prove for your compiler. And if you prove it, you will be able to know that your compiler preserves arbitrary safety properties robustly, or arbitrary trace properties. Or if you're into security, like non-interference kind of style security, you could have a tool-hyper safety preservation compiler, and so forth. And for the purpose of this talk, we are going to use the definition for robust hyperproperty preserving compilation, which goes roughly as follows. In this world, we don't have interactive Turing machines. We have, we are in PL land. So we have arbitrary source and target languages, S and T. And a compiler is RHC if it is able to take any partial program P, compile it down, link it with any target level attacker A in such a way that their traces, their security relevant observables, according to the target operational semantics, are the same as those that the original source program P is able to produce when linked against a source level attacker. And for the PL audience that I expect you to be, perhaps this notation is somewhat new because P's are partial programs. The A's are just program contexts, and typically, so the bow tie operator, it typically gets written between square brackets. But this just means link a partial program with the program context. And the squig arrow is run these two according to the language semantics. And in this case, we need to have an enriched semantics, enriched with traces, so observable events that are meaningful from a security perspective. Now, if these traces are the same between the target level interactions with the target level attacker and the compiled program, and the source level interactions between the source level attacker and the source program, then your compiler preserves hyperproperties robustly. Okay, and this is the formal statement. So compiler is RHC if for all programs, for all target attackers, exists a source attacker, such as for all traces. The target level interactions yields the trace if and only if the source level interactions yields the same trace. Does this look familiar? Well, actually, let's put the two statements side by side and actually there should be a visual correspondence that is sort of available here, right? Because both statements talk about two worlds, which are these sort of like two sub-triangles, if you wish, and an equivalence between these two worlds. On the UC side, on the left-hand side, we have the real world, and on the left-hand side, we have the ideal world. In secure compilation, in robust compilation, we have target languages and source languages. And in fact, if we analyze all of the two triangles and the elements in the triangles, there's a striking correspondence. We have that protocols are compiled programs, and on the right-hand side of the left triangle, we have real attackers, and on the right-hand side, we have target-level attackers. Now, the interesting thing here is that these are also, they're both universally quantified, and barring the universally quantified program, they are the first element of the attackers that comes universally quantified. Now, if we then take a look at the rightmost triangle of both systems, in the ideal world, on the bottom left, we have ideal functionalities, which correspond to source-level programs, which interact with simulators, or in the robust compilation world, source-level attackers. And when we take a look at the formal statements, well, the simulators and the attacker, they are both existentially quantified, and they come right after the universally quantified target-level attacker. Then what about the simulator, so the environment and the traces? Well, again, they are the last universally quantified entity in our formal statement. And essentially, they are, if you will, the objective witness in both worlds that whatever happens in the real or target and whatever happens in the ideal or source world coincide. You know, the environment tells us that they coincide by them being indistinguishable, and the traces tell us that, you know, the security behavior coincides. Now, this is the connection that this paper is about, and we've Isabelled it, so we are pretty confident it's true. There is a connection between all of the elements I was talking about, but there are some elements which, you know, if you squint, there's like, well, some things are they exist on one side of the world, but not in the other. For example, compilers. In fact, in PL, we often have these nice inductively defined compilers on the source level syntax, whereas in universal composability, we don't really have a compiler that translates an ideal functionality down to a protocol. There's typically just what you could call it a human translation or a human correspondence between the two. And so there are some elements which indeed require a bit of craftiness in the Isabellization, but, well, you know, this holds, so yay. But so, besides yay, why should you care that this connection holds? Now, we've seen that two things are essentially the same, they have the same spirit at heart. Well, there should be benefits for both worlds. And on one side, so for the robust compilation world, well, you could prove robustive compilation via UC proofs. And interestingly enough, this was this sort of half of the correspondence is something that other people had discovered in the Viaduct paper at PLDI-21. But this is not the part of the benefits that you will find in the paper because, well, while we believe there might be some, we haven't delved too much into these kind of benefits. Instead, we've delved more into what benefits are there for universal composability. And during these years, I remember once I was talking with Michael Hicks, and he was like, the Curry-Howard isomorphism gives us eventually, Coq and theorem provers. What does your correspondence give us? Well, our correspondence gives us mechanization of UC proofs via program analysis tools. And in this work, we've used DeepSec. In the computational UC work that I mentioned, we've used CryptoVerif. We have planned to use other tools such as Squirrel. And one of the reviewers was very kind to point out, look, this is kind of already known. Like computer-aided cryptographers kind of already do that. But with our connection, you get the formal guarantees that actually, when you can indeed use these tools to derive UC proofs, and what you get are actually UC proofs. Okay. So how do you go on and then use this to mechanize UC proofs? Let me give you an example from the paper where we mechanized the one-bit commitment protocol. So the first thing is, well, you take a protocol, and hopefully there already is an ideal functionality, and you code them up as DeepSec process. Easy. Then you start building typically the simulator for UC, and which is the missing ideal process, if you will. And the nice thing is that the vast majority of its code, I think a good 90% of its code, can be done using two things. One is back translation proof techniques, which is a proof technique that we borrow from the secure compilation literature, and that helps us in the development of the simulator. And this is almost automatable, okay? And the second thing is we have ported the dummy attacker theorem from the UC literature into our connection, and that lets us simplify the amount of essential processes that we need to code up in DeepSec. Finally, there is still some fun left, okay? So this procedure does not yield the full UC proof, as in universal composability and as well in robust compilation. There is some creativity required in order to put the security argument in the proof somewhere, okay? And well, the fun part is still there for us, although, all the rest of the tedious, the boilerplate is sort of taken care of by, the second step. And then in the third step, we had to, add 4 lines to the DeepSec processes that would encode the security reasoning that make the proof go through. For simplicity, we wrap all of these processes with an environment that acts as a proxy and essentially regulates the scheduler for DeepSec so that we can keep track precisely of whenever messages are coming in from the DeepSec environment or attacker and into our processes. And then finally, we need to add missing lines, because when I was doing this proof, it was all nice and well until almost the last point, and then DeepSec was telling me, well, these are not equivalent. I'm like, no, they should be. And then I go back to my cryptographer's friend, and I'm like, look, DeepSec is complaining. And they're like, oh, yeah, of course it's complaining, because in an adaptive attacker setting, you cannot have a commitment protocol that retains both the binding and the hiding property. So of course the proof cannot go through. And so I went back and I gave up on the hiding property and added another couple of lines of code, and then DeepSec was fine. Then at that point, the proof was able to go through, and then we had the first mechanized proof of universal composability for the one-bit commitment protocol in the adaptive corruption setting. So what more will you find in the 64 pages that this paper is built of? Well, you'll find the axiomatization of the UC semantics, the isabelization of the connection that I presented. We then have formalized the condition to use this connection indeed with arbitrary languages, right? Because indeed this connection, in order to use this connection, for example, for DeepSec, we needed to instantiate some axioms to make sure that the DeepSec language would be okay to be used in our connection, because they need to respect some composition, some very simple axioms. We have formalized composition action because in the UC literature there are various composition operators for composing protocols, composing attackers, etc. Whereas typically in PL we just have linking of modules and we are happy. And then we have the mechanization of the UC proof for one-bit commitment, both for the static and for the adaptive corruption system. And then, because it's a journal first, we could pack it with a lot of insights that we've developed throughout the years. And let me finish with one of those, well, which goes as this. A security proof between interactive Turing machines is a UC proof, whereas a security proof between arbitrary languages is a robust compilation proof. So that's it for me. I'll be happy to take questions now.
Okay, thank you for the great talk, but we may just have time for maybe 1 or 2 questions. Any questions from the audience?
Hi, so this is great stuff. I Can you say a little bit more about? Can you say a little bit more about what happens when you go to the computational setting?
Well, one thing is this is not sufficient anymore when you go to the computational setting. Like all the nice work that we'd done here was not sufficient. So we needed to bring RHC to a computational setting and essentially talk about, essentially we have hyperproperties which have a notion of poly time something. I don't remember which one. I think they have a notion of polytime contexts, and essentially, yeah, you need to bake the polytime arguments into the hyperproperties that you want to preserve. You get a new element, which you haven't actually related to anything in this lattice, so it goes somewhere on this slide, and then it works. But then again, that's the CSF 24 paper. More details there. But so that was the main change.
Thank you.
Do you like if this combination is this connection between the security and comparison is extensible? Like in case of the Curry-House isomorphism, there was like more extensible application of the isomorphism. So do you think any like extensible application of this similarity?
Yeah, that's a good point. I'm not sure. Or rather, well, there is a section at the end of the paper where there were alternative definitions to UC for this kind of composability, and indeed we had found out that, or rather, we have conjectured, and some of these I think we've proven in the past years that some of these alternatives relate, for example, just to trace property preservation or just to robust safety property preservation. But it's also, these other alternatives are not as, for what I could see, they weren't as widespread as you see, so we didn't focus as much, in proving a connection between those alternatives and these statements. Again, I don't know the full crypto literature, so if there's any real cryptographer in the room that wants to prove me wrong, please stand up. But yeah, so I guess that's the closest analogy I can see.
Okay, thank you for all the questions. So our next speaker is Isabella, and then the paper is about adversities in abstract interpretation, accommodating robustness by abstract interpretation.
Can you hear me? Okay. Okay, thank you. In this work, I will present an approach for modeling robustness for classifiers by abstract interpretation, in particular robustness against adversarial attacks. So let's start from the motivation of this work. In the context of classifier, we have this problem of adversarial attacks. We will see in a moment the intuitive meaning of this kind of attacks. But anyway, it is an issue, security issue. And there is, in the literature, we found only an informal way of characterizing this kind of attacks. But anyway, a solution wasn't necessary. So during the years, several solutions were provided. But these solutions were given just based on this informal idea of what adversarial attacks were. And each one of these techniques, these are only examples of works where at least an informal way of describing what an adversarial attack is. In these techniques, usually the problem was that they were providing a technique for proving a property, for guaranteeing security against something that was not really formally specified. And in this context, some issues arise. In particular, for example, can we prove any relation between these techniques? I mean, if I have to decide which kind of technique to use for a specific application, how can I decide which is the best one for my context of application? And this is quite difficult whenever we have a definition which is informal, and each one of these techniques indeed enforce in different ways the same idea. Another issue is, for example, whether soundness is provable. I mean, how can I decide whether the notion I'm trying to enforce is indeed satisfied? And the problem is that since we don't have a unique formal characterization of this kind of attacks, it is hard just to understand whether we are really enforcing a universal, a generic notion of attack, and how we can really prove formally this aspect. So the way we choose is different. We try to provide a general formal model, a model which is as general as possible, just to capture these ideas and to have just a point of a reference point in order to attack these problems, to face these problems about relations or about soundness of these of different techniques that we can find in the literature. So what we propose is like a framework where we can, in some way, define, recognize as instances most of the techniques that exist in the literature, and at the same time, we can define some variants of the model that we provide in order to capture different features of the fields of application where we want to model the problem of adversarial attacks. So this is the context in which we move. And so let's start introducing precisely the problem. So we are in the context of classifiers. So what is a classifier that we consider? We have, for example, a CAM that captures images, and the classifier has to decide which is the main subject of the image. So in this case, it says that it is a pedestrian. What is an adversarial attack? We have this image, we have our classifier that tells us which is the subject. For example, in this case, it recognizes that it is a road sign. But the problem is that we have also, the classifier may depend on the definition of the image. So if we add some noise to the image, and this is what an adversarial attack may do, then we can deceive the classifier, inducing the classifier to classify with the wrong subject. So for example, in this case, it says that it is a traffic light, which is completely wrong. And this is the context. So we try to model formally this notion. And in particular, we consider an image, X is an image, and we take the set of a set of possible perturbation of this original image. And in this case, what we require is that whenever we have a class of the original image, then we require that also the class associated with the perturbation must be precisely the same. And this has to happen for all the possible images in the same class of perturbation. So this indeed captures the problem from a very simple and formal point of view, but in the moment that we can formalize the notion, this model can allow us also to understand whether this notion really captures all the possible situations that we can have in real cases. And indeed, for example, it can be in some conditions too strong, because if we have a perturbated image with a different class, then we would say that robustness is not satisfied. But maybe the two classes provided share some property that is acceptable. I mean, for example, if we have two images, an image of an animal, and the perturbation induces a classifier to classify the image with a different animal, but anyway an animal, maybe it is acceptable. So we want to capture also this information. Let's see an example. So suppose we have this road sign. Clearly, the right image is the giveaway classification, but maybe with a perturbation, it provides a different giveaway road sign. And clearly, there is a mistake, but anyway, both the signs are giveaway road signs, and both they induce the car to slow down. So maybe it is acceptable to have this kind of error in the classification. So the model is that we consider an abstraction, a property in the output classification. And in this case, what we require is that the perturbation, we are considering the abstraction of the class, so the general class that it represents. And we require that all the images that the perturbated image provide at least a class in the same abstraction. And this has to hold for all the possible images in the perturbation. Again, this does not capture completely the idea because it can be, again, too strong since we have introduced an abstraction, but we are not really exploiting the hierarchy structure that typically we have in an abstraction. So for example, if we have that a perturbated image provides a class, a different abstract class, but we clearly don't have absolute robustness, but maybe this abstract class is more precise, is more contained in the class of the original image. And so maybe it can be acceptable again. So let's see again an example. Suppose to consider the images in terms of the actions that they induce on a car, for example. In this case, suppose the original image clearly is the giveaway, so it induces the action slow down or stop. And if we make a perturbation of the image, then the classifier is induced to say that it is a stop. In this case, the stop induces an action which is included in the actions of the original image, and it may be acceptable because the car makes precise, at least a more restrictive action. So the model of this situation is what we call hierarchy-aware absolute robustness. And in this case, what we require is that the images in the perturbation must provide an abstraction which is at least contained in the original abstract class. And therefore, we require the property holds whenever for all the images inside the same perturbation, we have at least an element which is contained in the original class. Again, this is not the last step of our framework, because in this case, what happens is that we have a property that strongly depends on the center of perturbation, so on the choice of x. For example, if we just swap the rows of the two images, then the property doesn't hold anymore, since the original image is now contained in the abstraction of the perturbation. And clearly, this is doesn't satisfy the property, but also, if you have a class which is not comparable, clearly the perturbation, the property is not satisfied. So again, let's see an example where this may be a problem. Suppose to have a classifier that decides which direction the car has to take. And in this case, suppose that it is acceptable from the image to take the direction, one of these three directions. It is acceptable to take one of these directions, but it is not acceptable to take the right direction. And in this case, as you can notice, the acceptable situations are not comparable. So we provide a new notion, which we call coherence, in which we require that, again, we consider the abstract property of the classification. And in this case, we accept as coherent a system, a classifier, when the perturbated image provides a class, an abstract class, which has a list upper bound that is below the top. What does it mean? It means that in some way the abstraction, the output abstraction of the classes represents the degree of error that we are accepting in the classification. And the top for us means that we are just losing, we are mixing classes that we don't want to confuse, to mix. So for example, as you will see in the experiment, if we have an animal and a means of transport, then we don't want to just have a mixture, an error that takes one in the other. And this is interesting because it makes really a regional property. So now coherence is a form of robustness which is on a region of values and not on a single value. So, and this holds whenever it requires that for all the values, the image in the same perturbation, the least upper bound of all the abstract classes that we have remain below the top, so it doesn't lose any information about the class. So the whole framework that we defined is this set of 4 definitions. We started defining the robustness. Then we allow a controlled error in the classification, so we admit an abstraction of the output classification. Then we introduce an exploitation of the hierarchy structure of the abstraction. And finally, we make the property a regional property with coherence. There is an implication relation between all these notions, so clearly concrete is stronger than abstract, stronger than hierarchy aware, and in some condition it is stronger than coherence, which indeed usually they are not comparable. And also, whenever the abstraction has not a really structural a really hierarchical structure, then also the inverse implications hold. So this means that it is really important to move towards this kind of characterization of robustness whenever we really have an hierarchical structure of the output observation of classes. We validated this notion. In particular, we started from the ATH robustness analyzer for deep neural networks, and we added the possibility to check hierarchy-aware and coherence, just to experiment very quickly. In this case, we are in the MNIST data set, and which are images of numbers. And for X1, and the output error that we allow is just to obtain a number which is less or equal than the original number. And in this case, for the image X1 can be classified as 4. Since 4 is less than 9, then it is acceptable. On the other side, then the image X2 can be classified as 3, and this is not acceptable because 3 is not less or equal than 2. Another experiment on cipher 10. In this case, we are in coherence, so we have an abstraction of the output which has all the means of transports, which can be confused. There can be an error in the decision which is the precise means of transport that it is represented. And on the other side, we have all the animals. So, for example, in the image X1, the ship can be confused with an airplane. Since both are means of transport, that's OK. We don't reach the top. On the other side, we have a frog, but the classification can recognize it as a truck, which is a means of transport. So we have two values whose least upper bound is the top, because we don't want to confuse this kind of images. So this is the framework. In the paper, we have also several characterizations of the domains and these properties. But anyway, which is the connection with programming languages? We have several properties in language-based security, in particular abstract non-interference, which is strongly connected with and inspired abstract robustness, and also the recently proposed local abstract non-interference. And there are several notions in static analysis, again, very strongly connected with this notion, in particular completeness, but also the recently introduced notion of adequacy, which was inspired in the opposite direction from coherence. So concluding, what is an ongoing work? We are defining a notion of approximate coherence, because coherence as it is, what we propose here is not a new technique for enforcing robustness. We are not saying that we made something better than others. It's just a model providing a different perspective on a problem, and a way of looking at this problem in a formal way for making possible to compare and to better understand the problem of robustness against adversarial attacks. Among these notions, we think that coherence is the most interesting one because it is the really new notion and provides really a different way of looking at the problem. And the problem is that it is defined on a concrete classified execution, which usually is too costly or uncomputable. And indeed, we face this problem in the implementation in Iran. So we are defining a new notion of approximate coherence, which is given directly in terms of the approximated execution of a neural network. So in this case, we perturb regions instead of values. And this can be important in safety because usually when safety is not satisfied, they make a refinement process, which is really costly. And if we are able to reduce the alarms due to a more precise representation of the problem, we can reduce this kind of refinement iterations. Finally, as future works, we would like to investigate the sensitivity. We can study the sensitivity of sensors against adversarial attacks. So how, by perturbing only some sensor, we have a different observation of the output. We can drive the design of class abstraction in finding out which are the actions that we can ignore since they are with low probability, as in the picture. And we also would like to understand whether it is possible to make classifier abstract robust, maybe by defining or exploiting a form of abstract training. That's all. Thank you very much.
Okay, thank you for the great presentation. Any questions from the audience? Here. Yeah, you can go ahead.
I was just wondering how fast it runs, how long it takes to compute one of these sets for a given input.
Sorry, I didn't understand.
How fast does it run?
How?
Can you hear? How fast?
Fast? What?
Yeah. Like, so say I wanted to put this on a car. I get an image, and I want to compute the set of the robustified set of things. Could I run it in real time? Does it take milliseconds? Does it take seconds?
The complexity of IRAN of the ATH, we don't add any complexity.
Okay. Is it like milliseconds? Is it seconds? Is it minutes?
Well, I have the table. I don't know. I mean, I have in the paper there are all the times, and it's acceptable time, really.
Okay.
I don't remember the seconds really, but
okay.
It's computable in acceptable time.
Okay, I may have another question. So in those coherence properties, you typically need to have a substructure, right? Like some classification may belong to the same high-level class, but what if you have a classification problem, those substructures are not that apparent? So in this case, would this coherence property still be useful?
So you have a hierarchy anyway. I mean,
like you need to identify a hierarchy, right, in order to utilize those kind of coherence
properties. To have a significant property, you need a hierarchy, yes.
Okay, so basically, you need to analyze those hierarchy first in your first step.
I mean, at the moment, we have a hierarchy as part of the design. So it's the analyst, the analyzer, and the analyst in particular, that understand the problem and characterize the hierarchy that provides the kind of error that I'm accepting. One of the future work is to drive the design of this hierarchy from the problem. And that's open question.
Yeah, sounds good. Thank you. Let's thank our speaker again.